So I think we can get started. So welcome everyone to this CSCS course, GPU programming with Julia. So we'd like to thank you for your interest in our program, and I'd like to thank also Sam for organizing this. So I'm not the speaker. I'm Guilherme. You should have received an email from me. I'm just organizing the things behind the scenes. The actual trainers are Sam and Tim, and also we're going to have Harman, which is one of our Julia experts at CSCS as well, who will be supporting us during the event. So this will take place as a regular Zoom meeting where you can interact with the trainer at any point in time. Then be aware that this is being recorded. We can, of course, later on we are going to edit the videos and maybe remove the parts that are not relevant for the others, but be aware that this course is being recorded since we had many other people that were interested in joining the course, but we had all the seats booked. So
thanks for the introduction. Yeah, so hello everybody. I welcome you to this GPU Programming with Julia course. It is the first time that we do that at CSCS. We had before at User Lab Day presentations and things like that, but it's the first actual course. And I'm really excited that besides that I will give a first part. At day 3 and 4, we will have Tim Besar, who is a lead developer of CUDA.jl, who will talk and has prepared some hands-on exercises and so on. Yeah, then so the course, as I just said, will go over the 4 days, but only in the afternoons. But I guess as it is all on the internet, is still already quite a long time. We will start every day at 1:30. Then afterwards, I guess it depends on the level of each of you. If it takes you more time to solve these exercises, or maybe less. Yeah. In general, I would say it would rather take you less time. There is a lot of text. I try to really explain a lot of things. So it's not about writing a lot of code. It is about understanding and experimenting. Now that said, it is mostly about really trying to do something relevant for HPC, for supercomputing. And I did not at all try to cover all possible features and things like that. Really not at all. For this, there is enough resources around. And then Tim, I guess he will present a lot of the latest features of CUDA.jl. He is the right person to do that anyway. He will give you really a lot of information in that respect. Yeah, so then let me start with the slides. I have first made a little introduction, and which will be the slides, and afterwards we will go into Jupyter, and there I will go through the first notebook with you, and then the 2 other notebooks will be the hands-on. But the idea is that the most of the lecture is actually hands-on, and we will try to support you the best, which is not an obvious thing, obviously, at distance, but I think we should just try to imagine we are like in a big room and try to act in that way, the way we would act in a big room in order to communicate. Okay, All right, so you say, I want to start solving really large problems on a GPU supercomputer. What is the first step? I do here a little bit like a sketch introduction, like not something very serious in the sense of the way it's presented, yeah? But the content is obviously something I strongly believe in. So what is the first step when you want to do supercomputing? Then people typically would say, like here, Peter in the front row, parallelize your code. And then, but next to Peter, I imagine this virtual classroom here is Sophie, who says, for a successful parallelization, we first want to find an algorithm suited for massively scalable distributed parallelization. And so the solution is often something like iterative algorithms with few global communication. And an example are stencil methods using the pseudo-transit method in addition. And so in this course here, we will do exercises with stencil applications. Once I have a suited algorithm, what is the second step? So again, Peter says, parallelize your code. And I would say, of course, it's not wrong, right? Of course, you have to do that. But I think to be productive, we first want to solve the two-language problem and then make prototype and parallelized production code become one. Because it is more and more important that we're also productive, not only that we have a fast code and it's very hard to maintain it, to further develop, etc. And so when we talk about the two-language problem, we mean what is represented here. We have on the left a prototype, which is written, for example, in MATLAB, in Python, or whatever. On the right side, the production code, which is in C typically, or C++, or Fortran. And then we have this costly cycle to always develop something new in a prototype, and then translate it to the production code, then go back to the prototype, develop something new, etc. And so this is something that we would like to get rid of, ideally, right? And so a solution is obviously a language that can be used for both. And Julia is such a language. So Julia is simple and high level, interactive, has a low development cost, and is fast. Now you say fast and interactive, that kind of doesn't go together. And Julia is compiled, yet only shortly before you use it the first time. And so guess what? In this course, we will do exercises with Julia. Once I have a single Julia code for prototyping and production, what is the third step? So Peter says none. And Sophie says, we want to try to evaluate the achieved performance in an absolute manner in order to get an idea of how much room for improvement there is. And this is not only important in science, this is maybe even more important in industry. You want to know if it's worth to spend 1 year to try to improve something, or let's say 3 months, or if you know that you're already nearly at the best you can be, then why should you invest time, right? Because time is as important as performance. I mean, with time, I mean time of human people, right? Developers. So to do that, we need to address the performance evaluation problem. Traditionally, performance was evaluated with flops, obviously, because this was the bottleneck of things. Yeah? But now, meanwhile, this has drastically changed. The amount of flops that we can do per byte or per number read from main memory has grown exponentially. And so, well, you can see that around maybe 2005 or whatever the year is, we have hit what people call the memory wall. So from that point on, we have the memory access speed has become the bottleneck for many applications, and it's not anymore the amount of floating point operations you can do per second. And so as a result, the solution can be memory throughput-based performance evaluation. And now we have developed an effective memory throughput metric for partial differential equation solvers, but we will do exercises in this course, well, with this effective memory throughput metric, but we will also see in one exercise in the fourth notebook tomorrow that we can actually modify this a little bit, and we will have it. We will also have an effective memory throughput metric for a totally different problem. So I believe this kind of thinking, this kind of metrics is useful in many, many applications. So now here is the agenda for the day one. I introduced 3 problems. Now I'm going through this introduction notebook I talked about before. There we will look at main memory access, or even more simply put, memory copy. Then we have an exercise notebook on data transfer optimizations. And when I say transfer, I did that intentionally. Normally when people think about transfer, I think, well, it's about transferring my data from my home to CSCS, for example. But I intentionally use this word to say, well, it's all about transfer of data on every level, from transferring data, let's say from CERN to CSCS, up to transferring it in the end from the main memory to the processor, or between the different cache, etc., in the memory hierarchy. Yeah, then so the second notebook will be again on the data transfer optimizations with shared memory. Then you will see what that is if you don't know. Well, I hope you don't know, because else you will have less to learn. All right. Then all the exercises are done with CUDA.jl. There are, Julia, of course, many higher level packages. And for stencil HPC computations, there is parallel stencil.jl. So now let's go to the Jupyter notebook. The introduction notebook is then about GPU computing and performance assessment. So everybody, I'm starting, yeah? So the goal of this introduction notebook is to tackle GPU architecture and kernel programming basics and GPU computing and performance assessment. I will go always cell by cell through it, so you see also where I am. Now let us instantiate this, the needed requirement first. So about that, you see that in the Git repo, you will have these 2 files in addition, which define a certain requirement, a certain kind of packages, certain versions of packages, which we're going to use in here. But in the essence, we are using CUDA, we're using plots, the package plots to create plots. Yeah, we are using another package called benchmark tools, which facilitates a lot to do benchmarking. And all the other things, this is just to try to make sure that you won't run into problems. I mean, to have this fixed environment is just to try to make sure that you don't run into problems, which of course can happen anyway. All right, so GPU architecture and kernel programming basics. So we get started with a brief overview of the NVIDIA GPU architecture, how to program it. The NVIDIA general purpose GPUs we will use in this course can be programmed using the CUDA language extension. CUDA is accessible in Julia via CUDA.jl, which exposes most of the native CUDA features to the Julia ecosystem. Note, however, that CUDA.jl does not use NVCC, the NVIDIA compiler, which we would use, for example, in C. But it compiles like other Julia code just ahead of time with LLVM, the compiler infrastructure.
Samuel, maybe one question. Can you maybe zoom in a little bit on the notebook?
Okay.
Not a lot, but a little bit.
Like that or more?
Yeah, I think that's perfect.
Yeah, then now, first let's distinguish among CPU, GPU hardware application, and CUDA. There are these terms host and device that you run into immediately when you start programming with CUDA. So the host is the system CPU, and the system memory linked to the CPU is the host memory. And then the GPU is called the device. And so we will have functions, for example, like set device and things like that, right? So this is what, because the GPU is called device. And the GPU memory is called the device memory. Then the GPU hardware is composed of global memory, L2 and a lot of streaming multiprocessors, which are normally abbreviated as SMs. And so each of these SMs contains a lot of units for computations, which are called so-called CUDA cores by NVIDIA. But these CUDA cores are not at all like a core on a CPU. But anyway, and then you have, in addition, registers. You have a L1 cache, and you can have also read-only memory. Now, of course, all the stuff that I just said, this is about a kind of current state of things. In future, it will be different, right? We can have maybe a third layer of cache, whatever, yeah. But right now, with this, with these GPUs that we work here, this is what we have. Then the CUDA programming model provides an abstraction of GPU architecture that acts as a bridge between an application and its possible implementation on GPU hardware. Now, we're getting to the really like the practical things here. So in the CUDA programming model, we have blocks of threads which compose a grid. So this, to have this mental image clear is absolutely necessary for CUDA programming and for all the exercises. So in most of the things that we're going to do, we will map one thread to each cell of the 2D Cartesian domain, because we're going to use mostly 2D. And so this figure here depicts the relation between the CUDA domain. So here, get the CUDA programming model, and the 2D Cartesian domain, which is essentially like the arrays, right? You have arrays of different sizes, but let's assume that the arrays are all the same size, or we look just at one array at the moment. And so in this figure, it's called finite difference domain because this came out of a finite difference course, this figure. But essentially, it's, you could say more generally, it's 2D Cartesian domain. And so you can see that yeah, let's look a little bit more at what we see in this figure, because this is really fundamental. So we have this grid, which is constituted of blocks, which are kind of aligned in a Cartesian domain. The blocks are distributed and referenced like with indexes, just like you know it from math, right? X and Y. And so we have here block ID Y is this direction of this coordinate system, and block ID X is this direction. So this defines the coordinate system, let's say, of the grid, yeah. And then each block again inside itself has then a coordinate system, which is with thread ID x.x and thread ID y thread ID x.y. And then in addition, we have the block dim here, which will give us the weight of the block. And we have that in x direction, we have that in y direction. Yeah. And then now the most important thing, okay, now this is kind of the mental image that we have on CUDA, right? And in the model, how does that map now to this array here, let's say? So we will have a block will map to, let's say, a block of 4 by 3 threads will map to a block of 4 by 3 threads, 4 by 3 cells. Yeah. Sorry, one more time to be clear. A block by 4 by 3 threads will map to a block of 4 by 3 cells of the array. And so, for example, this thread here in red will map exactly to this here. And for example, the one below would map to this one below. All right. So this is the most straightforward way to do things, and there are other ways, right? But we'll start with this one. And then we see, okay, we'll continue. So the indices ix and iy replace the loop indices over dimension x and y in a traditional CPU way of programming, yeah? And provide kind of vectorized mapping of these threads to array cells, and really this to have these threads just map there continuously. This is what will give us good GPU performance in a simple way to put it. So we will come back to this later. Then in the CUDA programming model, so yeah, what I just told you, we have these blocks in red, the threads, which contain the threads, and this composes the gradient. I told you already, sorry. Then now we will okay, so I think I told you everything I wanted. Now, how does this relate to the GPU hardware? So all threads of a block are guaranteed to be executed concurrently on an SM, and therefore share the resources of the SM. As I told you before, the resources are registers, L1 cache, or as you say, also shared memory. So it is very important what threads are run together on an SM. To remind you, SM is a processor in the end, right? It's a streaming processor, and the GPU has a lot of them. Then we will see later that the performance of a GPU application is highly sensitive to the optimal choice of the thread, block, and grid layout, the so-called kernel launch parameters. Writing a Julia function then with so-called kernel, copying an array from A to B with the layout from above, from this figure, yeah. It's really, you know, this figure used here. So we have 4x3 threads, like here, 4x3, blocks 2x2, so 2x2. So we said that, then we can compute an X and Y, which is the length of the array here. So this would be this would be an X here in the horizontal, and Y, the number of grid cells in the vertical. So we can compute this and X and Y from the thread blocks in order to have something that matches. Yeah, you can of course also do it just the other way around. First define an X and Y and then compute the thread and blocks. That is what we will do afterwards, but just to show that they're just related. You just have to make them match. It doesn't matter which one you compute based on which one. Yeah. All right. So then we allocate two arrays with the size that we just computed, and then we have a function copy defined up here, which we call, and we use now these so-called kernel launch parameters, as I said above. Yeah. And the function copy itself uses indexes ix and iy, which are computed based exactly on this diagram here above. So this diagram is really the thing that you need to understand, and then everything is good. And so this ix and iy computed based on that, and that they are exactly these indices here in this array. So for example, ix is 8 up here, 1, 2, 3, 4, 5, 6, 7, 8, and 6 here. All right. So I know this is a very rough start for someone who has not much experience, but this is the essential thing you need to learn and digest and to exercise with. Yeah. Okay, then now when we want to play with GPUs, there are certain rules, let's call them, right? They're given by the hardware. So the physical limits, right, behind that, not just made up rules. They're for a reason. So we can have on current GPUs normally maximum 1024 threads per block, and the maximum number of blocks, however, is huge. So you don't run into a problem with that. You run out first of device memory normally, and yeah, as I already said before, so the CUDA model itself uses a Cartesian topology, if you want to call it like that, yeah? And it allows you to use 1D, 2D, or 3D indexes here. So this allows you to set this grid and blocks up in a 1D, 2D, or 3D Cartesian way. And so this makes it very simple to work with 1D, 2D, 3D arrays then. Okay, so that was this like quick start for CUDA. We will now get into like the first practical thing. So for those who had already seen everything, or already known everything, I hope that now you will get some new information here with these experiments. Yeah. So I will have to execute the cells. Okay. All right. I will quickly restart the kernel just to be sure that everything will be fine. All right. So now we can really get started with the experimental part. So GPU computing and performance assessment. The goal is here in this introduction to learn the basics of benchmarking, to learn to compute achieved memory throughput. So throughput, it means like the amount of data you put through, right? You put through your buses, and well, to say to you how if you imagine like a channel between main memory and processor, the amount of memory you put through this channel. Yeah. Then we want to learn about the fundamental parameters determining memory throughput, establish the peak performance throughput of your GPU, and learn about GPU array and kernel programming on the way. So in order to get started, we need to connect to a machine that has GPU. Oh, sorry, there's something else still here. You already have that by now, I guess. You have already connected to Jupyter by now. And so you have access to a GPU. Yeah, then note that the values that are reported sometimes here in these notebooks, they are for the NVIDIA P100, which we have here at CSCS, which you are using now. But if you would use run this notebook on another GPU, another computer, then they should be more or less analog, but it will not always be proportional, yeah? because some fine-tuned strategy on one system will not always work equally well on the future or past architectures. All right, so to get started, we will use the packages CUDA and benchmark tools, and to create this little performance laboratory here. And then scientific application performance. So as I mentioned a bit in the introduction, where I showed this graph with the memory wall, the memory access speed is really something essential now. So the performance of most scientific applications nowadays is bound by the memory access speed, what's so-called memory bound, and not anymore by the speed of computations, but the speed of computations can be done, which are applications which are so-called compute bound. Now, the reason for that is that modern GPUs and CPUs can do many more computation in a given amount of time than they can access numbers from memory, which is already a bit shown in this graph in a way, right? Now, this imbalance can be quantified. And that is really an awesome thing. So we can quantify this balance by dividing the computation peak performance, which you can express, for example, in gigaflops per second. We can divide that by the memory access peak performance. So we have here the ratio for the P100 GPU. We have the computation peak performance, and below the memory access peak performance. Then we can multiply this by the size of a number in bytes. So it means the size that one number that you use in math, right, for your calculations, the size that this number actually occupies in memory. Yeah? And so typically people use so-called double precision, which uses 8 bytes per number. So we have to multiply this here by this 8. And then we have been able to quantify this imbalance. So it means now this 58 here means that we can do 58 floating point operations per number read from memory with this hardware. Imagine that, yeah? 58 operations for just one number. We normally don't do that. Now, I computed this based on the theoretical peak performance values as the vendor specify them, and you can find them here. It was taken from this sheet. Now, as a consequence of this, that we can do so many floating point operations per number read from main memory, we can consider the floating point operations for free now in this lecture, and for many applications when you're developing, because we work in the memory bounded regime. Now, let us start with investigating the performance of different ways to express and launch GPU memory copies. So we will wrap all of these memory copies in functions to enable the Julia compiler to optimize best. That is something Julia specific for the just-in-time or just ahead of time compilation. Now, there exists already a function copy2, which permits to copy data from one pre-allocated array to another. And thus we start with analyzing this function's performance. Sorry for that, that shouldn't be here. So, to this purpose, we allocate 2 arrays and benchmark the function using benchmark tools. Now, it's very important that to know, for those who are new to Julia, if you run a function the first time, or some operation or some, yeah, whatever, when you run something for the first time, it can take a lot of time. And so you might think, well, Julia is slow, but this is just because the first time it has to compile things. But then from the second time on, it will be fast. So it is not as responsive as maybe Python, etc. for the first time, right? But in the same time, I mean, what we gain here is that we have a language you can use for supercomputing in the same time. Now you see, I did so this benchmarking here, yeah, of the copy to function, and you get the range. Okay, so let me explain what benchmark tools does. So it launches many samples, it launches the function many times simply, yeah? and it measures each time how much time it takes. And so these are called time samples. And then you get here the minimum and maximum values that this function took, sometimes more, sometimes less, right? And then you can see here the distribution of the runtime. And you will always have a right skewed distribution. Why? Because the hardware will not just by accident run faster than what it can, right? It can run slower because there happened something that slowed it down. For example, on the network, it can be network congestion or file system issues, and a shared file system, etc. And here in Julia, we have something else. It's the garbage collector, which will collect the garbage, right? The free memory again, etc. And so when this gets activated, it can slow down things momentaneously. And so that is why we have always the minimum is really just like when everything runs perfect, no disturbance, and the median is not far away from that normally, and the maximum can be far away from that. But the essential thing is, I would say, the median to really know if an application normally, or a function normally runs well with the performance you expect. And the minimum, if you want to find out what is the peak performance, etc. Also, it shows you if there was some memory allocated, and in general, when you do HPC, you don't want to have allocations, at least not of large arrays. You want to pre-allocate everything. Now, one practical thing, when you use this benchmark, you need to use this $sign here to interpolate variables from the outside of this expression into it. So here we have the array A and B interpolated that way into this benchmark expression. Then another note, CUDA zeros or round, etc. If you don't specify the data type, like here, then it will by default allocate float 32, so single precision. All right. I already explained the distribution. If you want to learn something more about these estimators, you can see on the Julia documentation, on the benchmark tools documentation, on this link. And there is, of course, also a lot of literature on how to measure how to benchmark and what estimators to use and so on. Now, using this BLAPS macro instead of benchmark like above, we can directly just get the minimum. And this is what we're going to use now in all these exercises. All right, so let's take a step back. So I did here benchmark this copy tool, right? I allocated two arrays of size 32 by 32 and did a benchmark. Now, what does it tell me? I have this number. Is that now fast or slow, right? It tells us basically nothing. So, well, except the only thing it tells us, it doesn't take an awful lot of time, right? It didn't take hours. It wasn't blocked. Yeah? But so, of course, we don't want to stop here. But we want to figure out how good the achieved performance was. So to this aim, we compute the total memory throughput, which I call T-tot. And this we will note in gigabyte per second. And so this total memory throughput, so the total amount of data I can put through the channel, is defined by the volume of the copied data divided by the time spent. When I said the amount of data I can put through the channel, I refer again to the mental image, right, between the main memory and the processor, how fast I can move things there through the channel. Now, so T-tot will be 2 times this expression, 2 times y, because we have 2 arrays, right? Let's say we have to read one array and write in another. So we have 2 array operations, 2 full array operations. Then we divide by 1E9 for the gigabyte here, the giga of it, the giga. And we multiply by the array size and by the amount of space one number occupies in memory. And finally, we divide by the time. So up, I did not yet execute this, sorry. All right, so then we computed T-tot is 2.4, or 2, let's say, 2 gigabytes per second. So we want to compare now this T-tot with the known peak memory throughput, T-peak, which is found, for example, in scientific or vendor publications. And for the NVIDIA Tesla P100 GPU that we have here, it is 559 according to this source here that you find on this link. you see it is massively below, right? 2 versus 559. Now, the achievable peak memory throughput is usually significantly lower than the theoretical peak bandwidth announced by the vendor, which is 732, as I noted before. Yeah, so we have this difference here. Note as well that 1 gigabyte is 1 in 9 bytes, as in the publication where we got this from here, this source. All right, now we found here T tot to be orders of magnitude below T peak, and this is to be expected because we're copying a very small array. And CPUs need to move a lot of data in order to move them fast. Now let us determine how T tot behaves with increasing array sizes. Now, I decided I will not actually execute everything because it will take maybe a bit too much time if you're right now listening to me. I have it already executed, so we can just look at what we have done before. So when this is executed, you can execute it yourself afterwards. Yeah? So when this is executed, it will print one line after the other here. So first NX and Y 32, we get T tot 2. It was just what we measured here before. This is just the same thing. And then you see here the results with increasing size of NX and then Y. And you see how the total memory throughput increases until it kind of settles at the maximum. And now, if you compare against this peak memory throughput, we're already quite close, right? Now, when I did this notebook and I ran it, kind of each thing independently, I got a bit higher numbers. With, I don't know exactly, with the interactive things, etc. Sometimes you get a little bit lower numbers. But this is only pretty negligible. So, yeah, the lesson to learn is the same. So we got here 517, while the peak is supposed to be 559. Now, why could that be? Well, copy2 is a function that needs to work like for every possible case, for every possible hardware. I mean, you can expect to really work one function to work perfect for every hardware and every case. I mean, with case, I mean different array sizes, etc. You want to have something that works good in all cases. In a general function like that. While however, in high performance computing, we are basically just interested in solving big problems, right? So we're most interested in how fast it can do things with large arrays. Now, furthermore, we know that the best performance is obtained with large arrays. So here, and this is actually arrays of the order of gigabytes. We will use the array size for which we obtain the best results for the remainder of this performance experiments. So I did here find max of all these throughputs that were stored here. Yeah? We pushed every time the t dot into these throughputs arrays initialized here. So we find the maximum, and then this array size, we use it then. And so we have found our nx and ny, which is, I think, the largest one of these here. Yeah, the largest one is the best. All right. Now, GPU array programming. Let us now create our own memory copy function using GPU array programming. And we can write a memory copy simply as A equals B with this dot here. Yeah? And this is really the important thing in Julia, dots everywhere. Besides that, it looks pretty much, very much like MATLAB or NumPy, but we need to have a lot of dots. Or if you don't want to have them, you can use a macro, which is just an at followed by a dot, which you put at the beginning of the line, and then you don't have to write the dots. This is noted somewhere else, not here. It's noted as a note somewhere later. So A equals B with the dot will copy every element of B into A. And note, if you do A equals B without a dot, then it will not do a mem copy, but it will instead make an alias, make A an alias of B. So it means it will just point to the same data, and then A and B become the same. So if you change B, it will at the same time also change A. And if you change A, it will at the same time change B because they have become the same. Yeah? Okay. Note that with Julia, we can use this macro inbounds to avoid that array bounds checking is performed, which slows down things a lot. Well, when you want to do high performance computing, if you do just make it work computing, if you have to do something where performance doesn't matter, then probably often it will not even matter. But here for HPC, it matters a lot. Now, honestly, I don't use this inbound normally when I do something, because I instead just do Julia check bounds no at the moment when I want to run the code fast. And when I don't do that, then I actually want to have this bound check, right? So Julia allows to globally activate and deactivate the bound check. And for me, this is the most magnificent thing. I don't want to hard code that I have no bound checks. Yeah? But we can do that with this inbounds macro. And for the purpose of this course, I added them. And yeah, in order not to have to kind of get out and do a check bounds no, or make a special kernel for it or something. Yeah. All right. So that's the story of the inbounds. And so here we also benchmark this GPU array programming function, and we get then the following t tot, total throughput of 493, which you see, well, before we had 517, it's only a little bit below, right? But let's say it's only memory copy in the same time. What is a little, but not, yeah, up to you to decide. But I don't want to say that this is like bad result for this cheap array programming, right? Not at all. Just want to say that we need to use something else for HPC. Cheap array programming is absolutely awesome to do, as I said before, things when it just has to work, or for HPC to do pre-processing, post-processing, initialization of things, or in the code things where it's not exactly performance critical. So this is magnificent that we can have this nice simple syntax everywhere, and only where it really matters, where it's performance critical, to do more complicated things. Okay. Now, so the few experiments that we have done now so far, they show that memory copy with maximal possible performance TPEAK is apparently not a completely trivial task. And so we will now use TPU kernel programming to try to get closer to this TPEAK. And so a memory copy kernel can be written like that. I have explained that already above at the beginning. This whole block and thread story to get the IX and IY. And so in order to copy the entire array B to A, we need to launch the kernel such that the above indices IX and Y map exactly to each array cell. Because we launch it with too few threads, then it will not copy all cells. If we launch it with too many threads, then it will try to read out of bounds of these arrays. Read or write out of bounds. Now, therefore, we need to have exactly block 1 times thread 1 equal nx, and block 2 times thread 2 equal ny. So we will first try the simplest possible option, using only one thread per block. So you see, one thread, that's why I have here 1, 1. And the blocks are then simply an X and Y. So here it is absolutely trivial to see that we run one block, each containing one thread per cell that we want to read from the array. Okay, then we have already seen how to launch that. They're still the same. And then here we have the total memory throughput, 9.5 BOF. It's very low, right? Still orders of magnitude below the TPEAK. And so we need to take into account that a single thread cannot run independently, completely independently, but threads are launched in small groups within a block, and they are called warps. A warp consists of 32 threads on current GPUs, and so they must always be together. They are one team. They cannot work as lonely workers. They work together as a team of 32. Else they don't work well, right? They just do their job, but they don't do it well. So, and furthermore, these warps, they should access contiguous memory for best performance. So you send your 32 all together to grab together 32 numbers in a row. That's the ideal thing. Now, we therefore retry using 32 threads. So one warp per block as follows. So here, 32. And then for the computing in the block, we divide by the number of threads. You see this little symbol here is divide, but it does an integer division. But pay attention, it will not round each integer. If it is it will just it will just get to the next closest integer. Well, what's it called? Yeah, just cut it off. It does not round or something, and it will not create a float. So it only works if you have pair numbers. Within pair numbers, you will get here wrong computations. All right, so 32 divided by the number of threads we have. So, sorry, nx divided by 32 will be the number of blocks that we use here. And then we get this number, 302. You remember T peak was 559, so we're not even at half. So we're still doing something very wrong. Now, note for simplicity, the number of threads here was set explicitly to 32, but in future, of course, the warp size could be different, right? We never know what future brings to us. Right now, we have 32, but you can get this value with this attribute, this device attribute warp size. Okay, so T tot is still far below T peak, and so I said before that we do something fundamentally wrong. I mean fundamentally wrong for this GPU. It actually, for example, Tim Besar, who will do the second part, he said that he got with this, he got already good performance. Yeah. So it depends absolutely which GPU you use to test. So this could already be good with this number of threads, 32. Now for this GPU, what we can do is to increase the number of threads per block, bring it closer to this maximum of 1024 that I mentioned in the beginning. Yeah? Now we're starting to play with the rules that I mentioned in the beginning. So we have maximum 1024 threads per block, which we get here with this device attribute to have it more work with also other GPUs, which have different numbers here, maybe. So we get these max threads, and then we do again experiment. No, not again. We do now a different experiment than before. We increase the number of threads like this, from 32 to 1024, and we get these values. And you see already with 64 threads, we get a very good performance for this memory copy, which is already higher than the copy-to function that we saw at the beginning. So we are closer to this 559 that we found in literature. Now you should observe that beyond a certain minimum number of threads per block, so here 64 with the Tesla P100, T tot is quite close to T peak. And then which exact thread block configuration leads exactly to the best T tot depends on the GPU. Now we'll do something else. Now we just increased the number of threads over X, in the X dimension. We'll do also in the Y dimension. But we will keep in the X dimension 32 threads in order to make sure that these warps are sent, this team, the one warp, this team of 32 threads are sent together to grab a contiguous part of numbers in the memory. And then you see, okay, you have your 32 threads in X, and in Y, we increase it and we get even better performance than before. But the most important thing here is that the thread block accesses are now not anymore just 1D, like a line, but we have now a 2D block that we address with each thread block. To show that maybe on this figure, when we had only threads in X dimension, it means we went only along a line. So a thread would, for example, access here 32 or 1024 or whatever amount of cells all in one line. But now, as we also increase the number of threads in Y dimension, we access now a block as is shown here. So a block that will have 32, will access 32 elements in X direction, and the second number that is there of threads in Y direction. I'll go back. All right. So why is this important? Because, for example, for computing derivatives, etc., it will allow us to have more of the data that we need to compute these derivatives at the same time on the processor. So far we experimented with memory copy in the strict sense, but we can. So I mean, in the strict sense, I mean copy one array from one place to the other, right? But when we do computations in reality, then we often want to read more than we want to write. I think typically we do that. We read more data than we produce output. So we will therefore also do a few experiments on another commonly used benchmark case, where we read two arrays and write only one. And so we modify the previous kernel to take a third array C as input and add it to B. The rest is identical. So we just have here this plus C in addition. Then we test exactly as for the previous kernel, how T-tot behaves with an increasing number of threads per blocks in Y dimension, and keep it fixed to 32 in X dimension. So here you see 32 in X fixed, and on Y we increase it. And now here you see the result. So, and note that when we compute T-tot, we now need to use here a 3, while before it was a 2, because we have now 3 full array operations. 1, 2 reads, and 1 write. Yeah, makes 3. Okay. Now, if we compare the best method T-tot to the T-peak, then it's even a little bit higher than we get from this publication. We have 561, and there it was 559. I mean, this is excellent. We know we have achieved what we need to achieve.
Sorry, can I ask a question?
Yes.
I don't understand so well why the performance seems to decrease with number of threads at a certain point, and I think we also saw that in the previous benchmark. Decrease slightly, but seems to also happen in my machine or in my my tests.
Yes, the more you increase the number of threads here, when you have 32 by 32, the more the number of blocks will decrease, right? These are two different kinds of parallelization, of concurrency. One is on the processors, the threads which are actually on the processor. We have a lot of threads on the processor, you have a lot of parallelization on the processor. But if you have less threads on the processor, then you have more blocks which run independently of each other. And this is another kind of parallelization. And then these are very complex things, many parameters which play together, which decide which is exactly the best thread block configuration. I think Tim will in the last part he will discuss a bit the occupancy API, where he will explain how many threads one can maximally run with a certain kernel, etc., and all the things that are in play there. Yeah, but so in the end, what we see is for memory copy, after we have a certain amount of threads, in fact here we have 64 threads or more, then we're fine. And the rest are little things which will be always different for each GPU and so on. Yeah, is that okay? I'm sure the team will give you some more explanations.
Thanks.
In the last part. Okay. Where have I been? Okay, so now, as I said before, we are 2 GB per second higher than what we got in the publication. That means just we have essentially the same, right? And it's excellent. Now, the T-peak that was reported in publication was obtained with a slightly different kernel, which multiplies C with this color in addition. Here, you see, we added that here, scalar S times C. That is the only difference that they did in the publication. And so we also quickly do that here, just to be complete. But we know already, because of the introduction I gave, we can do 58 operations, floating point operations per number read from memory. It won't matter to do a multiplication by a scalar. We already know that before running it. And we see, in fact, in the end, yes, we still have the same result. We took here the best thread block configuration from the previous experiment, and so we get still 561. Now, there should be no significant difference between T-tot of this kernel and the previous one, even on other GPUs, because of what I just explained. Now, finally, let us check also the triad performance with GPU array programming. So I modified this above memory copy to add also the multiplication here and the third array. Yeah. It's exactly equivalent to this, and equivalent to what they did in the publication. And then we get now 520 with GPU array programming. With this very high level way of expressing, we get very close to the peak performance. Now, here comes the note that I know from earlier that I wanted to tell you. Note that in this memory copy function, use everywhere dots to fuse vectorized operations and avoid any allocations of temporary arrays. You can see more information here. So again, here we have these dots everywhere to be sure that all of this will be run in one single kernel and not one kernel and then it creates a temporary array and then another kernel and so on. Yeah. All right, so congratulations, you successfully made it through this memory copy kernel experiments. And I hope even advanced people found it interesting and that for not so advanced, it was not too difficult. And so at the end here, just print the best array size that we obtained and the best number of threads, which we then reuse in the next in the exercise notebooks. Now, let me tell you here, we often get actually with 32/8, we get better results than with 32/16. Maybe not for the mem copy, but at least for example, the stencil applications later. So if you want, you can in the notebook just type in 32/8. You don't need to really type what we got here. Up to you. You can strictly follow like the flow of this notebook and type exactly this, or you can say, no, okay, take 32/8. It doesn't really matter. All right. So with this, I conclude this part. And now you can get started with the notebooks. Hello again. Another quick remark. I just saw that Hazel, yeah, he asked something related to running out of memory. And you need to be aware that in these notebooks, we work really quite at the limit of the GPU memory because the arrays are like 2 GB big, and we use 2, 3, up to 5 of them, and the GPU has 16 GB of memory. So that's why they are pre-allocated at the beginning, and you're not supposed to allocate then more of them. But if you do, and you run out of memory, I guess the best thing to do is just to restart the kernel and then try to just allocate the arrays once that you need and then only work with the pre-allocated arrays. I mean, this is a particularity of this workshop, of this working in Jupyter, working interactively. Normally, you don't have that, right? You would have your code, you allocate what you need and you run it. But here, working like this interactively, we have to pay attention to that. As Jupyter is kind of a sequence of all you do, and all gets stored into memory until you restart the kernel. Oh, wait, or you can also, like it is done in one of the notebooks, you can do CUDA unsafe free to delete, to free some arrays. So this you can that way manually free things if you want. Welcome to the second day of the GPU Julia computing course. I will immediately share my screen. Okay, that looks good. So yeah, this is day 2. Again with me, and tomorrow and the day after tomorrow will be with Tim Besar. For those who had maybe not been here yesterday, he is the lead developer of CUDA.jl, and he works at Julia Computing Inc. now. Okay, so I will get, like yesterday, I will get started with a quick introduction. And then afterwards we head back to the Jupyter, just like yesterday. There's a difference in the agenda. I will be showing more things, solutions, but I will show that at the end of this introduction. Okay, so yesterday I made this really like sketchy introduction, like yeah, a bit provocative or whatever you want to call it. And so I just take up the first point from yesterday. So when I want to start solving large problems with GPU supercomputers, what is the first step? And so yesterday I said, okay, well, here Peter in the front row said parallelize your code, and Sophie said, well, for a successful parallelization, we first want to find an algorithm that is suited for massively scalable distributed parallelization. And I didn't discuss that yesterday yet because we didn't talk about distributed parallelization. So we will come back to this point here. So a solution to these problems are iterative algorithms with few global communication, as I told you yesterday, with, for example, stencil-based methods and pseudo-transient method in order to create an iterative algorithm is a solution. And so now today we're going to look in the last part of the exercises into how we can create multi-GPU applications. And this in general, whether CPU or GPU, what you have is normally a global problem that you want to decompose in local problems in order, well, to solve each of these local problems on one CPU or GPU. And I believe this is quite true for any kind of application that you want to run at scale with distributed parallelization. Now, what you here see is one kind when you have stencil applications. And so here we have, I'll show you the mouse. You have the global grid on the left, which would be like the global problem, right? And on the right, we have it decomposed the whole thing into 4 pieces. And then we do so-called halo updates after every iteration in order to be able to compute each of these pieces correctly. And so, like in modular's words, you could say, for example, the problem 1 here defines the upper local boundary conditions of the problem 3 here, yeah, and so on. Now, in multi-GPU or multi-CPU, data locality is super important, not only to get very good performance on a single GPU or CPU, but also it will enable to form local problems that depend only on the neighboring processes at most, right? And you will hopefully have very few global communication. So when you have very local algorithms that use only the data just around them to compute something like stencils, then this is all in the same time also very good for large-scale parallelization, not only to have something fast on one CPU or GPU. The exercises that we're going to look at, we will use what I call implicit domain decomposition. Implicit domain decomposition, what do I mean with that? We don't define the global problem and then decompose it into small problems, but we define the local problem and then just create many of them, which implicitly defines then the global problem. So we define what we have here on the right and repeat them a couple of times in each dimension, and this will create the global problem. So here, for example, we defined one little local problem and repeated it 2 times in X dimension and 2 times in Y dimension. And then what we do is we code what happens on one GPU. And this makes it very simple to do everything. Now, the advantages, the most important advantages are that we can easily choose the local problem size such that we obtain maximal single GPU performance. You saw yesterday that already for mem copy, and just as well in the exercises, you need to have a certain size of certain array size in order to get big performance on GPUs. And so with this approach, we can just take the best array size that works for our problem and work with that. And then domain decomposition is trivial. Now, so with this approach, we did some scaling tests, and we have some code in Julia which corresponds to code that was written in C. A 3D porovistoelastic two-phase flow. And so you see on the bottom, you see the scaling of this CUDA.c code, and on the top, the scaling of the Julia code. But the dashed line is only like extended. These are real measurement points. And so this Julia code uses CSCS, which uses it's CUDA.jl backend, and implicit global grid.jl with MPI.jl backend. So you see what we're all looking at in these courses. If at the end of the course you say, well, maybe I don't want to go in this level of detail, you can also work with more higher level packages in Julia. And yeah, so you see here we have a really great scaling result up to more than 5,000 GPUs here. With Julia, so far we did only up to 1,000. And so, yeah, but more, yeah, there is a little difference here, but this is basically just because the Julia distributed parallelization, we optimized it more before running it. The other one was not with optimal parameters, so we would have to redo that. So let's zoom in here to the actual measured data, and you see, yeah, it's just very good. For those who are not familiar with parallel efficiency, so when you have, for example, here like 95%, then it means that with 1,000 GPUs here, it runs on each GPU at 95% of the performance that it runs when you use only one GPU. So this is kind of the overhead of the communication that slows it down here, for example, by 5%. Now I did this quick introduction, distributed parallelization, and I will have a look at the solutions day one with you and walk through the notebooks. Then the next thing will be to do exercise 3 and 4. Exercise 3 is again on data transfer optimizations, like I said yesterday. So data transfer in the large sense, right? And I said yesterday, everything is moving some data from somewhere to somewhere else, and whether it is from your home to CSCS, or from CERN to CSCS, or then from memory to a processor, it's all just move around the data, and that is what costs. And so it will be with register control. We cannot control registers like 100%, but we can kind of steer it, and then also with shared memory. Then exercise 4 is an introduction to distributed parallelization of CPU and GPU. And fine, at the end of the day, I will go through the solutions of exercise 3 and 4. Now, yesterday all exercises were with CUDA, and now it's all with CUDA and the API in the JL. Then for well, again, like yesterday, it will be all in Jupyter. And for the API exercises, it's actually very simple to run them. So these are the steps that you will have to do. So when you want to run an API mini app, create an additional server in Jupyter with 4 nodes, or maybe less, so we have to maybe coordinate that we don't run out of nodes, yeah? Open a terminal in Jupyter and do, for example, this command here, srun -n2, n is the number of nodes, so 2 nodes, and then the small n2 means 2 processes. So we have 1 process per GPU, right? And then Julia, and then the name of the mini app. And then it's important that after that you will close the additional server again, because as I just said, else we maybe don't have enough nodes. Or well, sure, if everybody wants to run use 4 GPU nodes at the same time, then we don't have enough. But you should only, the moment when you want to run it, create a server, run it, and close it again. But so this way, you don't have to do any SSH to CSS or whatever. You can just stay in Jupyter. Okay, so let's do just 3 minutes break, and then I will go through the solutions. Okay, so the idea of this exercise yesterday was to learn how to minimize redundant main memory transfers and understand its importance, understand the limits of the total memory throughput metric for performance evaluation, learn how to compute the effective memory throughput and understand its interest, and learn some GPU array and kernel programming on the way. So like yesterday, we create a little performance laboratory. And it's important that the first time when you run something, the first time when you open such a notebook, you don't only do activate, but also instantiate, like in the notebook number 1, in order to install the packages that are missing. Then, so we had this diffusion code here, which you certainly could understand with all these comments. And then, so the function to compute an actual time step was still missing, and it was then written like this. And this was already given, and you saw that here we used everywhere views to avoid allocations of temporary arrays. Yeah, that's the one important part. And we use already everywhere dots to fuse vectorized operations. That's and avoid any allocations of temporary arrays. And this is really fundamental when you work with GPU arrays in GPU array programming. And so, as I said yesterday, this macro at dot allows you to avoid all these explicit dots. Then here we used macros instead of functions to enable a nice syntax. And in particular, the macros can also be on the left side of an equal sign. Right? You cannot have a function call on the left side of an equal sign, yeah, of an assignment, I mean. And then I hope, well, that you ran this thing and you saw that, right? And then so the task 1 was then to benchmark that thing. And so we had to set the large array size, like you found in the memory copy notebook, the introduction notebook. And then you got hopefully about this performance. Now, here we just save this in order to have later on still these values. And as I told you yesterday, we work with such big arrays, so we need to free things, as we are just in one Jupyter session, and so we need to make sure that we don't run out of memory. Now, I mean, I don't want to spend too much time, so I will not go through everything that is already written here, right? I'll just try to say some additional things. Stop, you can immediately interrupt me. I think that's the best. If I pass on something that you would have wanted to know something more about, that was not clear. Yes, can you?
Yes, I have a question about the solution. Why is it 11 times 1 over the
Why is, sorry?
Can you go up a bit into the first solution? Yeah. Here, the throughput T tot LB, why is it 11 times?
Okay. Yeah. All right, so thank you for that question. That's the most relevant question here, definitely. So when you try to figure out what is the total memory throughput, so meaning all the data that was like sent through the channel between main memory and processor, then you need to think about what full array accesses are made. So we can just count here how many full array accesses we have, meaning here we have 4 write, all right? We write to 4 different arrays. So I've already 4. And here we have then a couple of reads. So let's count that. We have 1, 2, 3, 4, 5, 6, and 7. So we have 4 plus 7, meaning 11, right? We have 11 full array accesses. We don't care about the scalars at all. And so I mean, to solve this, it's not possible here to do that with less than these 11 array accesses. It's just required to do these computations. The processor cannot do the computations if it doesn't get the data. It's as simple as that, right? And now you ask maybe, but why I cannot reuse in this line, in the second line, the temperature array already read here. That is because each TPU array statement will create an independent kernel. And so these kernels don't know anything about each other, and so they cannot reuse data from the other kernel. Yeah, that's the reason. Then why, another important point, you maybe wondered, why does it say T.LB, yeah? Lower bound? Why not just T.? Why not just the total memory throughput? The thing is that we have here some derivatives, so we need to access more than one value at a time when we do this computation here, for example. We need to access neighbors of this array QTX in order to do these stencil computations, and so it could well be that for certain arrays we need actually to read them more than once, or part of them you need them to read more than once, and so this 11 full array reads is just a lower bound, but in reality maybe we have to read a bit more than that, yeah? And that is exactly one of the big objectives in the later exercises, is to try to reduce these more than that reads. We want to eliminate them as much as possible. We want to read things only once and then keep it in on-chip memory to do all the computations. Yes, I see you raised hand again.
Yes, hello. You said there were 11 reads, but
Yes.
the macros access the array twice. Where do we count this as one? Like if you see the macro d_xi, it accesses the array A twice due to the subtraction.
Yes, exactly. That's what I tried to say before. To do this difference, we access it twice, but when we do a difference between neighboring values and things go well, then we can do that with the data already in the cache, or more generally in the on-chip memory. Yeah? So we ideally we don't have to read them at the whole array twice, but we can read it and do the computations between the neighboring cells immediately while the data is still on the processor. Was that clear?
Yes, thank you very much.
Okay. So that was the first exercise, I would say, essentially. Then okay. Then I tell you here, well, we don't need to actually have all these arrays here, because they are just intermediate results. Yeah, all that we need to have in the end is the temperature updated. So we want to remove them. Yeah, and so here I explain you how we can remove them. With GPU array programming, simply mathematically, we can just substitute things into the equation, and we get then this temperature update rule. And then this is for constant and scalar lambda, the same thing in the end as you would find in Wikipedia when you search heat diffusion equation. And but we use then this here now for the following exercise, because we don't want to simplify the computations done in the first exercise, but solely optimize data transfer, so that we really have something to compare against, that we really see the effect of optimizing data transfer without changing the computation. Yeah? Okay, and so then we remove this array, as I said, right? And we have to do something now. We have to introduce a second array for temperature, T2, because else, when you do the derivatives of T, and in the same time you write to T, then everything gets messed up, and you will right, when you do the derivatives, you will compute some things with old values, something with new, while we want to compute all the derivatives just with old values. So instead of writing directly to the same array, we write to this second array, and then at the end of the iterations, we just swap the pointers. So this is aliases. So we just say now T is now called T2 and T2 is now called T. And this does not perform any array copy. All right, then so the second task was then to write in a single GPU array programming statement, which goes over multiple lines, as you see here. It was to write exactly this new update rule here. Yeah? And by the way, if I don't see all the participants at the same time, so if someone raises his hand, I'm not sure I'm really seeing that. Yeah. So if that happens, you can also write into the general Slack chat to let me know if there's a question. Yeah? All right, so the idea was then to program this new temperature update rule here, and you see I put it here in comments on the side, so you really see how it matches to, and it's essentially just these these macros here written explicitly directly in here, yeah, as a good exercise to understand what are the arrays that are used and what parts of it at what time. Yeah? And so, as we have now everything in one single statement, we know that the GP array programming will automatically transform this into one single kernel, as long as we use these dots absolutely everywhere. Yeah? Maybe they would not be needed exactly everywhere, but to be clear, I may put them absolutely everywhere, these little dots. Yeah. And so this gets one kernel, and then we get afterwards to the performance evaluation, and you see performance is well, not awesome, but still we got a speed up, yeah, over the previous over the first version. So actually, the t-tot, the total throughput is lower than before. Nevertheless, we have a speed up, right? So you think maybe that's crazy, right? But yeah, so before we got 384, and now we have only 200 and something. But that's exactly what I wanted to show you here. We don't care really, or we shouldn't care about how much data we achieve to move through if it is redundant moves of data. If we move data that will not be needed to move, right? This we don't want to count when we do performance evaluation, because in the end, what matters is the runtime. So we got here a speed up of 2, yeah, to run twice as fast. Now we want to continue here, so we save these numbers here in order to compare against later. Now, so the next step was then to rewrite this function using GPU kernel programming. And so this could look like this. So we have a main function here, the diffusion step function, I mean, yeah, which is called in the main code here. So we have to rewrite this. Okay, and so what this function does is just set threads and blocks in the appropriate way, and then call update temperature, which is the actual kernel that does this temperature update. And so you see here, this is pretty much the same thing as before. These 2 lines are pretty much the same thing as these 4 lines, just written more condensed. And now we use here, it is just written saying what is done to every element, yeah? We say how one element of the temperature is computed, while before we said how the whole array is computed. Well, here the whole array without the boundaries, yeah? But essentially the whole array. Here we specify everything with whole arrays, and here we specify everything element by element. But else it's exactly the same. And then, so if you did that right, then you got, again, the exactly same simulation. And so then we wanted to evaluate again the performance of this. And first, if you look at the time that it took, it was now 5 times less than before. We have a nearly 5 times speed up compared to before. So we do exactly the same computations as in the very first task, but it's 5 times faster. Yeah. Now, it's 5 times faster because we optimized the data transfers by removing these unnecessary intermediate arrays. Yeah. And in addition, well, we wrote the kernel before we had just TP array programming. Okay, and so you also see the total throughput lower bound is a bit better than before, but this makes only up for 1.3 of the performance increase, while we have a performance increase of factor 5. So I mean, this clearly shows that a metric like that, which just tells you how much data you move around, doesn't really help us to evaluate performance. I mean, globally, it can help you when you're working, trying to improve something as one aspect of everything, right? But to really get a global image of the performance, it is not good. And so, as we observe that, we want to say, we want to recall the reflections that I made here earlier, that well, there are so many arrays that would not be needed to read. At the beginning, we said, okay, we have 11 reads that are absolutely needed to do in the way we wrote it before, but we managed now to do the same thing, such that we only have 3 full array accesses. If you look here, we write to the temperature array, we read the temperature array, and we read the heat capacity array. And all this other stuff, this repeated, this access of neighbors from temperature array, this ideally will not cost us anything. Ideally, this can all be done with data that's already read in when we read this. Yeah, I mean, done with data is already read into the processor, so on the cache, on the memory, on the processor. Yeah, so we figured out we need only really 3 main memory accesses, ideally, right? And so we can say we define an effective memory throughput, TF, which should be defined that way. Now, when I said ideally only 3, this would be, let's say, in some kind of ideal world, but it's not quite true. We still, for these derivatives, there will still be some little amount of things that we'll have to read maybe twice from the main memory. But let's say this should be nearly irrelevant. And that's exactly what this TF is about. We want to define a lower bound well, we want to define what happens ideally, but then we still know that the upper bound of TF, we cannot exactly achieve it. The T peak is not exactly realistic as something to obtain when you compute TF. And so, yeah, so go back to this, how is it computed, this effective memory throughput? So we define the effective memory access, main memory access, which is 2 times the unknown fields, so temperature array, 2 times the temperature array, plus 1 time the known fields. Why 2 times the unknown? Because we have to read and write the temperature field. Why 1 times only the heat capacity array? Because we have to only read it. And so we get, as I said before, 3 full memory array accesses, which we absolutely for sure have to do, and hopefully not much more, right? And so now, as we know how much we have to do, definitely we can divide that by the time that we spent, and so we have an effective memory throughput. We have something that tells us how much data we have to move. We moved per second. That makes sense, let's say, or data that we absolutely need to move. Yeah. Now, yeah, T peak is something that is measured, for example, by the stream benchmark for CPUs, as found in this reference, and there have been a lot of follow-ups for that, etc. And so this source that I gave you yesterday, when we looked at the T peak of our hardware, this is something, a follow-up from Stream. It's called Bubble Stream, where they use many different languages and then programming models and etc. And they see what can we get maximally as a peak throughput. Yeah, there are a couple of assumptions here for this TF metric, which we don't have to go into details. You can just read them. Because, I mean, here it's not that important exactly for our exercises. And then anyway, in the exercise that we do today, we will solve something else than what this TF was made for. Yeah? And this TF was made for partial differential equation solvers, or let's say iterative stencil-based solvers. But we'll see that this whole idea of thinking, we can apply that to other things. All right, then, well, okay, let me still tell you something more about that. Yeah, let me tell you that, because it's in the end important. So an important assumption here is that the problem size is much larger than the cache sizes. That is what we anyway work with here. We work with a very large arrays. Then the usage of time blocking is not feasible or advantageous. There are some very fancy algorithms, but which are pretty much impossible probably for many real world applications to implement them. And so we assume we cannot reuse data in the on-chip memory over time, only in space, yeah, only in the space dimension, but not in the time dimension. Okay, so then we go further to task 6. Performance evaluation. So we computed the TF for different solvers, which we benchmarked in task 1, 3, and 5. And now, without redoing any benchmarks here, we just computed the speed ups achieved in task 3 and 5 based on TF instead of based on the runtime. And we see that the speed ups that we compute using TF instead of the runtime are exactly the identical numbers. Well, why? It's no accident. It's obvious because TF is something proportional to the runtime all the time. So this really shows that TF is something that really exactly grows with the runtime when you improve, say, your implementation. Well, it changes with the runtime, I want to say, and so it is a perfect evaluation metric in this sense. Yeah, it really goes with the runtime. Now, okay, then TF, yeah, let's look at this. So here was the question: well, did the speed ups you recomputed differ from the previous ones? And the answer was, therefore, it is a mistake. If you did a mistake, if you got some different values. So due to the way the TF is defined, it is always proportional to observed runtime and reflects therefore any runtime speed up by 100%, while the problem size and the number data type are kept fixed. Now, if you change the problem size or the number data type, then TF will reflect the additionally performed work. So this is, and it will therefore take that into account when you do more work. Yeah? While, however, if you just look at the runtime of a small problem and one of a big problem, then you cannot compare anymore in that sense. You cannot compare the performance of these two just looking at the runtime, because they solve a different amount. Then they solve a different, they do a different amount of work. And so it enables the comparison of the performance achieved in function of the problem size, or, well, data number type, and it even allows to compare the performance of different solvers or implementations to a certain point. But now, most importantly, comparing a measured TF with T-peak gives us some idea about the room for performance improvement. Now, with more complex solvers, etc., you will get less close to T-peak, but still you will have at least an idea what would be maximally potentially possible to get as an improvement. And so if you, for example, like here, you are at 91%, you will not spend 5 months to try to improve that, right? You will already say that's enough for me, many cases, and do something else. Maybe do improve the mathematical algorithm instead. Yeah? Okay, so this completes the first part of this data transfer optimization with Julia. Note that there are high-level packages, as for example, parallel stencil.jl, which can facilitate the development of HPC stencil codes for CPU and GPU. So then I go to the second solution. Oh, no, wait, sorry. Do you have any questions now about these first solutions? Okay, if not, then I go further to the second. All right, so we have here now the second exercise from yesterday. The idea was to learn how to use shared memory, which is some on-chip memory. It is actually, I would call it a repurposed L1 cache. So depending on the architecture, you can say I want to use everything as L1, or I want to use a part as L1 and a part as shared memory, such that you understand what shared memory is. Yeah. And when you use it as shared memory, then it is just a part of this very, very, very fast memory that you can now explicitly control. And all right, so again, we created a little performance laboratory. And then we looked at the same diffusion code as in the last exercise in the previous notebook. And then we create some arrays for benchmarking, again, large arrays. And then we did some performance evaluation here. Okay, so the idea was here to now compute this effective memory throughput that I presented briefly in the last notebook, and do that in function of the number of threads. So like in the very first notebook, the introductory notebook, we have here a little experiment where we fix here the number of threads, so 32 in the first dimension, and go here in the second dimension is an increasing number of threads. And then we see what is the resulting effective memory throughput of this above code. And so you see here that this is something very high already. If you compare that to T-peak, which is 561, we found, we are very close already. And just to remember here in this TF, we really only count what is absolutely minimally needed to move between main memory and processor. Then we just stored here the best found thread block configuration for the further exercises. And then we got here then we say here we want to relate the update temperature kernel back to the triad memory copy kernel that we looked at the very beginning. We can observe that if we remove the derivatives from the update temperature kernel, then we end up exactly with the simple triad memory copy kernel from the first notebook. Except for one little thing, we have some additional if statement here in order not to compute the values at the boundaries, because then when we want to make the derivatives accessing neighbors, we would run access things out of bounds. But so it is here really the same thing as this triad memory copy kernels, except for this if, which is irrelevant, this if statement. So you see before we had A equals B plus S times C, right? And now we have just different names for these arrays and the scalar. And so, no surprise, we get also the same performance. Now, in this case, when you do just a memory copy, T tot and TF are exactly the same. Because when you do a memory copy, you don't do any unnecessary memory transfers. Okay, now we get to shared memory transfers, shared memory basics, sorry. And so the idea was to modify this above kernel, which until now just does this triad memory copy. We want to modify it as follows. Read the values of the temperature array T into shared memory, then subsequently read the temperature values from there when updating T2. And so here is the solution. We allocate here some shared memory with the CU dynamic shared mem macro. How much do we allocate? We allocate the size of the block dimension X times block dimension Y, right? For simply for every thread, we want to have one cell in the shared memory to write our number into. And so here then when we read this data from the temperature array in the main memory and copy it into the shared memory, we do that just in a way that each thread just takes like his value from the temperature array in the main memory and copies it to his place in the shared memory local array. When I say local, it means local to this block here. And now this Tx and Ty, what is this? This is this just the thread idea. Each thread has an idea within the block. Yeah, I can quickly relate back to what we saw at the very beginning. It was this figure. Oops, where is that figure? Oh, I don't see that figure now here. Okay, so I will not go back. Yeah, we saw in this figure, I think you can see it in Slack, right? Yesterday I copied the figure into Slack. You can look at it there. You will see there somewhere it says thread ID idx.x, yeah? And thread ID idx.y. So this is just the ID of a thread within the block where it lives. All right, so every thread reaches value from the main memory array into the shared memory array. And then afterwards, when we write it to T2, we will now not anymore read from the main memory, but now read from this shared memory. Yeah, that's all. So we have this two steps instead of one. Now, when we do, when we evaluate the performance of this, then we get 561. Why? Well, because we didn't really do something more than memory copy as before, and we just copied things into the super fast memory, read it from there, and then we wrote it. So we don't do anything costly in addition. We do something that doesn't cost anything compared to before. And then we go to the next exercise. So we got the update temperature kernel from task 2. And we modify it as follows. We add now a little halo of size 1 to this shared memory on each side. It means on the left, on the right, on the bottom, on the top. To this purpose, we need to modify the allocation of TL and adapt the local threads TX and TY. You will see right after in the next exercise why we add this halo. Yeah? But let's now just do it. Then launch the new kernel, adjusting the required amount of shared memory, and compute TF. So, all right, what did we do? So we have here, we have here now a halo on both sides in X. So on the left side plus the right side means 2 sides, right? Plus 2. Then on the bottom, on the top, 2 sides, halo means plus 2. And then as we now want to have a halo, but we want to be in the center of this whole block with our threads, we do now here +1 in order to shift accordingly to this halo of 1. Yeah? And then we do the memory copy as before. We read just from this shared array and write into the main memory as before. So nothing else. We did just add this halo and we didn't do anything else. Did just a little bit of shared memory fun. And so, of course, the performance doesn't change. We just allocated more shared memory, but we didn't read anything more, right? Okay. So then you go to the next exercise. And now there, you see now why we did add this halo. It's because here we want to actually now add the values that belong into these halos. Now I'll tell you why do you want to add them? Because afterwards, when we will compute the derivatives, the thread at position 1 will want to read his left neighbor, and so he needs to find this in this halo. Yeah? And on the right side of the block, the last thread will want to read his right neighbor, and he needs to have a value, you know, to compute the derivatives. All right, so the idea here was to read just the required values in the newly added halo of TL, and then compute again the temperature, the TF, and you can see it's pretty amazing now. It reduces already the performance to a value that later won't reduce anymore. So we get 539 here, TF 539, because we did now actually some additional reads from main memory, or some can be from L2 cache or whatever. Yeah? But we do some additional reads. So as we do additional data movement, we have a decrease in performance. And then we get to the next exercise, where we actually add back now the derivatives to do finally the actual computations that we wanted to do. And so look at this, the performance. Well, okay. And in my test that I did at the beginning, the performance was exactly the same, 538. This is due to interactivity stuff, right? That is decreased still. But when I did each exercise like independently, I got 538 gigabytes here. After adding all this stuff, just the same thing as here. So the addition of these actual computations where we read many neighbors, etc., did not anymore change because we read everything from shared memory. So all these computations are that's why we said all these computations are for free, because we can do 58 floating point operations per number read from main memory. And you see here we read 3 numbers from main memory. So we could do here up to over 150 floating point operations. And here we do, I don't know what, 20 or yeah. Well, it depends then what you do. Addition, multiply, you count as 1 or etc. But this doesn't matter. But you see we have a few compared to this more than 150 that we could do. And so this does not decrease the performance. Yeah, so this was the major thing to see here. And then when we compute now TF divided over T peak, this ratio, we can see we are at nearly 95% of T peak. So the absolute maximum to improve this would be by 5% potential. Yeah, but I mean, still, as I said before, T peak is an upper bound, a theoretical upper bound. We cannot really achieve it. So we went through solutions now. And so now we have exercise 3 and 4. And then I would say maybe at 5 o'clock, I could quickly go through solution of exercise 3 and 4. Okay, hello again. So I hope you had some good exercises, and I'm going to walk through the solutions of today's exercises now. And with that, we will conclude today's session. And tomorrow, Tim Besard will then take over. So I will quickly change to the Jupyter. So here I already opened the notebooks with the solutions of today's exercises. And I have run them already before, so we don't have to wait for results. Okay, so it was, again, exercises about these data transfer optimizations. And the idea was to learn how to control registers for storing intermediate results on chip. When we say control, we cannot fully control everything, right? We can steer it. Tim will talk tomorrow or after tomorrow, certainly, about that. Then we want to learn how to use shared memory to kind of like communicate between threads. It's not very different from what we have done already. But it's, let's say, a different application. Yeah, so again, we created a little performance laboratory. Then now in the last notebook, you learned how to control one part of the on-chip memory usage, the so-called shared memory, which is repurposed L1 cache. And we will learn now how to control a second kind of fast memory on chip registers. Now, to this purpose, we will implement the CumSum function on GPU. For the sake of simplicity, we'll only write it for 3D arrays. And so here is the documentation of CumSum. CumSum is the cumulative sum of A along the dimension given as argument, called dims here, and it stores the result in the array B. So here a very small example how that works. You certainly have seen that now during the day. So for example, well, here we see the output actually only of the last one. So dims3, when you do the CumSum over dims3, so it means over the third dimension, you will see we have the sum here. Here is all ones, here all two, here all three, as a result of this summation over the third dimension. Then we again allocated large arrays in order to do this kind of benchmarking. And we pre-allocate also one array to store reference results obtained by CUDA CumSum for verification. And then if we only consider main memory access, then CumSum will ideally need to be read-only, will ideally need to read one array, A, and write one array, B, and no other main memory access should be required. So, as in consequence, we can create a little ad hoc effective memory throughput metric, like the one that I presented you earlier. And we will call that now TF_CS, CS for CumSum. And so we say what we have to do definitely is, as I said here, read one array, and write one array. So we have two full array operations to do. So we have here factor 2. And then the usual stuff, 1 over a gigabyte, and then the x times and y times and z, the size of the array, size of the number, divided by the time it takes. And so we say this will be the absolute minimum we have to do a CumSum. We have to read it, the array, do whatever you need to do to get the result, write it. Right? There won't be any possibility that anybody could do this chromosome without that. You have to read your array and you have to write it. That's just the bare minimum that one has to do. So this will define the performance that we can kind of achieve. Now, so the upper bound of CSCS, of this effective memory throughput metric that we just created, is given by the maximum throughput that we get by copying one array to another one. And so with the triad, we got a little bit better performance in the introduction notebook than when we just copied one array to another. And so there we had 550 for this specific case. And so we will use that saying that this is our T peak now for this case. Then we will now adapt the corresponding 2D memory copy kernel to work with 3D arrays. And so we get this here. So in addition to EIX and IY before, we have now also IZ, just for the third dimension. And here we have IZ and here. Then we run again with 32 by 8 threads, which is often good. And the third dimension is 1. And we get 540 gigabytes per second, which is very close to this 550 we measured the last notebook. And so we say, okay, that's now good enough to continue. Now we need to implement chromosome over all these 3 dimensions. And so let's start with the easiest one, the third dimension. And so we do that. We read A and write B in a way that, well, sorry, in order to do that, we will just first try to figure out how to read the stuff and write the stuff without doing any operations yet. So the first exercise here was then to modify the above memcopy kernel to read in A and B in a serial manner with respect to the third dimension, parallel in dimension X and Y, but serial in dimension Z. And so you can imagine, like the image that you saw in the intro, we still map the threads to a 2D plane, but we will not stop there by just reading the cells from a 2D array mapped with this plane, but we will now make a loop over the third dimension using this 2D mapping. And so here we have it. So all we need to do is a loop over IZ. And the rest is just like the earlier memcopy function here. And so, okay, we do that. We can afterwards check quickly that the memcopy is correct. Can set B to 0, all the values of B, run it, and then check that B is approximately the same as A. It will check every value, and it says it's true. So we know that it does really what it should do. Then the performance we got here now 520, and this, well, is a bit below what we got before, but we will say, okay, we continue anyway now, even if we could still maybe improve that, right? But we'll continue for this exercise with that. And then, by the way, you see here that this is a so-called grid stride loop. Grid stride means that you have the grid over a certain, like, for example, the plane, and then you move with the thread over the whole grid. So in the values that are addressed from memory are, for example, with the first thread is the very first number 1, cell number 1, and then the nx times ny times mz is the second value that the first thread will address, and so on. So we will do really such a sorry, not nx times ny times z, but nx times ny, yeah, the 2D plane. We go 2D plane at a time. Just that you know, this is some access pattern that is used in many cases. We have here a link to something, a blog from NVIDIA, where they explain why they think that is great. So you can go learn more about that. Now, you'll probably observe that this thought is a bit below that what we got before, but yeah, as you said, we'll consider that sufficient to continue. And so we will continue and add the actual chromosome. So here you got the solution. So we define here chromosome EZ a local value here, which is something which will then go into a register, and which belongs to this just current thread, the thread to one thread. Yeah, each thread will have his own chromosome IZ variable in the register. So we set that to 0, then we make the loop, and we add up on this register, and then store what is in the register back into and then we'll write what's in the register. We'll write this to the main memory, the B array, which is the result, and that will give us the chromosome for the whole array. So here we got the verification. So we can compute chromosome with CUDA chromosome, and then this we can compare it and see true. We did it right. It works. Then we can look at the performance, and we got 520 gigabytes per second. This TF with this metric, right? So we know we can at most speed it up to 550, we said, yeah. So we are very close with this rather simple code, but it is because it uses the registers in a quite optimal way. Now we can compare with the CUDA chromosome function, and in this case it gets a much worse performance, probably because chromosome, like any generic functions from Julia, they must work, or in any language, right? They must work for every possible case, well, also for very small arrays. And we here only care about large arrays, as we care about high performance computing, supercomputing. We want to scale things up. We want to solve big problems. Now we want to do the same in the second dimension, and this is not very different. So we can here create the memcopy kernel. Now doing the loop over IY instead of IZ, and check that it's true, right? And we get a performance similar to before. We saw, okay, the memcopy is good. We can now add the actual cum-sum operations, just like before. And so it will be really the same like over the third dimension here. We have now cum-sum EY, a local variable that goes into a register. Then we have the loop over IY. We sum it up, and we write the result to B. Then we check that it's correct, the performance, and we get something very similar then to the cum-sum dim over the third dimension. Now the result of CUDA, the performance of CUDA cum-sum here is a bit better than before. Then we go to the next part. So now cum-sum over the first dimension, that is a bit more tricky. So we start again with the memcopy. We do it now over the third dimension. The exactly same thing as we did for the second and the third dimension. And now doing this memcopy, we see we get only 36 gigabytes per second performance. That is crazy. We did exactly the same thing and we got such a way worse performance. But well, this is not really crazy. This is because of the way that we access things in memory. While before we always accessed contiguous memory, now in this case, not anymore. Let me be more precise. In this kernel, we access memory discontiguously with a large stride, in this case of nx numbers. So we read one number, then nx numbers further, we need the next number, nx numbers further, we need yet read the next number. And so we really have we pick some numbers out of everywhere out of the memory, and that's why it is so slow. So there is obviously no reason to create now the cum-sum function out of this. It can't be faster than it is now if we add more operation. If we add now the operations to it to compute the actual thing, right? It won't get faster, it can only get slower. So we first speed up now the memory copy function. And so, as I told you yesterday, when we have the way that things work on the GPU is with so-called warps. So a warp are 32 threads which work together as a team. They are inseparable or they work very badly, like you just saw. And so these 32 threads, we now want them to together go and fetch 32 numbers at a time. And not be like before, fetch only every now and then a number, right? And so we launched the kernel with 32 threads. Then, yeah. And here, sorry. And we adjust the loop now to do, not to go from 0 to the end doing one increment of 1, but we have now an increment of 32. And here is programmed more generically. We use block team X, so we could also launch it, for example, with 16 threads, and it would still work. Okay, and so then with this new loop, we compute now the offset of our coordinate ix, of our index ix. So we have 32 threads, and then we have which will be read, and then the next 32, and the next 32, and the next. All right. Then we can check that it's correct. So the mem copy did do everything correct, and the performance is actually even better than what we had before. Why? Because we have now parallelization over y dimension, z dimension, and in addition over x dimension partly. While before we had the parallelization only over 2 of the 3 dimensions. Now we have it over like 2.5. And in general, the more parallelization you have, very generally, if you run really a lot of threads, a lot of blocks, whatever is ideal, but a lot will give you good performance. Now, so to actually compute then the chromosome, we need to do yet something more. We need to now kind of communicate between these threads, because the registers are local to each thread, so they cannot kind of share what they got. So in order to communicate, we use again shared memory like before. And so here you see what we do. We again, like before, we allocate some shared memory. Now with the size of 32 in this case, the block team mix is 32, right? When we choose 32 threads in X dimension. But here it's programmed more generically, so we can also have a block team of 16, as I said before. Then we do, as before, a variable in a register. Then what is new is now here this. We read now from the main memory A, not like before into the register directly. Where was that? Here, you see, here we read directly A into a register and we could sum it up. But now we cannot do that anymore because we need to somehow find the result within these 32 threads of these 32 numbers that we read all together. Huh? So we read these 32 numbers into the shared memory, and then we say, okay, that's a very simple way to do it. We say the first thread of the 32 will now do the chromosome using what we read in the shared memory. And the other threads will not do anything at this moment. And then once the first thread has done that, then all threads together again will write the result back to, will write the result into main memory. And note here that when you do things with shared memory, you need to often sync threads precisely before you want to access things from other threads. So we need to be sure here that every thread has read in the values from the array before the first thread can start his work, right? He needs to be sure that the others have read in the data. And so that's why we have to put here a sync thread to be sure that data is there, only then I can start to do a CUMSUM. And the same in the end, we need to be sure that the first thread has finished before everybody can now read whatever is in the shared memory, write whatever is in the shared memory. So, all right, we do that. We see, okay, result is good. We did everything correct. Performance is now 340, which is still very good compared to the more generic solution of CUDA CUMSUM. And now this one could certainly improve further using warp level functions. As we have here already just 32 threads, if you launch it with 32 threads, right? We are kind of in a perfect situation to apply then warp level functions. Warp level means that these 32 threads have some special functions to communicate with each other. This is the deepest level you can go into the programming. Maybe Tim will talk about that. I'm not sure. All right. So I will go to the next. So here I finished exercise 4. I'll go to the last one, the introduction to distributed parallelization. So the goal of this exercise is to understand the basic idea of distributed parallelization and to learn about the API.jl on the way. And note that this course material was made by a large part by Ludovic Gress, in particular the codes, the actual codes. I just took them as they were and I put them in this Jupyter notebooks and changed a bit the text, etc. But there is a lot of text already that he also did, and yeah, a lot of things done by him. Now, in this part, so in this notebook, we will use MPI.jl, which is like the typical way to do distributed programming, like I showed in the introduction at midday or after midday. Now, as a first step, we look here at a 1D diffusion code which solves the linear diffusion using a fake parallelization approach. So it is basically the whole concept of creating an API application, but in the end, we solve it still on one CPU here. It's just about getting the concept. Yeah? So we split the calculation on two distinct left and right domains. Just like I showed you earlier today, this graph where I had split it into 4 domains. Here we split it into 2 domains. So we call the left array HL and the right HR, and then we compute for both domains the results, and afterwards we do a boundary update, so called, or in literature it's called halo update very often. So we do that in order to make sure that each process can afterwards compute the next iteration with the right values at the boundaries. Okay. So then here was the exercise just to do this boundary update. And so the solution was then here. So all we have to do is to say on the left array, at the halo, end is the halo, right? It's the last cell. The last cell of the left array, we need to get the second cell from the right array where in order to create a kind of an overlap of these 2 arrays. Yeah. So yeah, as we have finite differences, we cannot compute the boundary cells because we need the neighbor. And as we need the neighbor, we need to get it from the neighboring process in this case. And that's what's happening here. We just get kind of the boundary conditions from the neighbor, from the neighboring process. And now here, yeah, it is a fake process, but it's exactly the same idea as when you program MPI afterwards. Okay, so then, yeah, so this was the solution. Then the next step will be to generalize the fake parallelization from 2 fake processes to work with n fake processes. And so we created here an array which has a second index, which is the IPs, like the process, the fake process index, and the rest is analog to what we had before. And so what was to do here was to create the update boundaries correctly for now not 2 fake processes, but n fake processes. That's why I have here a loop over these n fake processes. And so we had to do here this boundary update. So like before, we need to put into the last cell the second cell from the neighbor, and into the first cell we need to put the second last cell from the left neighbor. And so that way we have like in the end like a contiguous array H, in a sense, a global array, which we can actually then create here. You see, global picture. To get the global picture, you can put all these together, and you will always use just the inner points. Well, it depends on how you do exactly, but you put them just all together in order to have in the end a global picture. And if you run this, you see what happens. Oh yeah, there was one more thing in the actual exercise. The idea was to first run it without boundary update to see what happens to the boundary. You see you get wrong results to the boundaries, and then with boundary updates to see that now you get correct results. This in all these exercises, this was the idea. You run it first without boundary update and then with, and then you really understand what it does. You know? Now, next task here was just to create a centered Gaussian anomaly here in the initial conditions. And in the essence, it's this here what we care about. So we create some x coordinates based on the process idea, and based on the length of the global array, of the global problem, we even set the 0 point origin of the coordinate system. So we move it here into the center. And then we compute the Gaussian with this formula. All right. Then after that, we are ready to create a truly MPI code, truly distributed parallelization. We had so far already all the concepts there, but now we do actually use MPI to really use two processes or n processes and not one process to do that fake. And so the idea is now to solve this physics. So compute here flux and update h based on the old value of h and this flux. And so to enable distributed parallelization, we do the following steps. We initialize MPI and set up Cartesian communicator. MPI uses something so-called communicator, which is basically just an idea to say a certain amount of processes, they are grouped together and it's in the same time defined how they communicate. So in the Cartesian communicator that we create here, we say all the processes that we have will be part of it. In another case, it could be just a subset. Yeah? But here we have all the processes together that we communicate together. And it's called a Cartesian communicator because they are arranged in a Cartesian way. Very similar to what we saw with GPU computing, where we have the blocks and the threads arranged in a Cartesian way. Then we implement a boundary exchange routine, create a global initial condition, and finalize MPI. So now to initialize MPI and prepare the Cartesian communicator, we do all that stuff here. Init is to initialize. Then dims create. This is to create together with card, create here the actual Cartesian communicator. And then you can get the rank, that is the process ID. This is the analog to IP before. Now we call it me, like me, who am I? Which process am I? Chords is to get the coordinates of the processing the Cartesian system, and neighbors is to know who is next to me. Then after that, we need to create the boundary update routine. And so you can see that this has basically the structure that I say, okay, do I have a neighbor on the left? Neighbor one is on the left. If yes, then I do send data to him and receive data to him. Then I check, do I have a neighbor on the right? If yes, then I send data to him and receive data to him. And so what we will have in here will correspond exactly to what we did here. Okay. Then after that, so we initialize H with a global initial Gaussian anomaly that spans correctly over all the local domains. And this can be done, for example, like this. The important thing is that we use the coordinates, like I showed in this fake parallelization example there. We also use the coordinates which we computed there. And then with this, and with these coordinates, we create here an offset of where is the start of my local domain in the global coordinate system. And then we also have this shift of the center of the origin of the coordinate system into the middle. And then we, like before, we create the Gaussian with this. All right, finally, we do then MPI finalize, and that's essentially it. So then the exercise was to run this code, diffusion 1D MPI.jl, which still misses the boundary updates, but works 3 times or yeah, with 1, 2, and 4 processes, and to see what happens. And you should have seen that it creates exactly the same problem as before, that the boundaries, you don't get the right values. It's in the boundaries, you have things computed wrongly. And well, in addition, when it computes things wrongly at the boundaries, this error propagates to the center of each local domain. Then, so the idea was to add this boundary update, and with this function here, you could visualize it to see how the boundary update would then make things correct. And the whole diffusion solver here only takes about 70 lines. Now, the next task was to do the same thing with 2D. This was just to see how things work now at the boundary. Suddenly you don't have just one value, but you have a whole line, a whole vector that you have to exchange between the neighboring processes. And else the idea was exactly the same of this exercise, the same idea like in the 1D parallelization. So run it, see what happens without boundary updates, run it again, fix the boundary updates, run again, and see that it works. Yeah. Then I will not go through the actual codes. I think, except if somebody tells me that I should. It is like standard MPI stuff that you can find in many introductions as well. Then the last exercise was a multi-GPU. And so here I will quickly go into the code. So the idea was to translate the whole code here into multi-GPU, do the code itself and the MPI part. So I'll quickly go into this. So this is here. Well, so what did we have to do? Well, add using CUDA, and then update this. I will come back to this at the end. First, I go to the main function. So here's the main function. So this whole MPI part here, we didn't have to change. All this stuff, the same. Then, so what we had to do is essentially change things where we use a whole arrays. So here, instead of allocate just zeros, we allocate now CUDA with zeros to have an array allocated on the GPU and not on the CPU. And then here, well, we can still, when it's initial conditions, and you can even just do them on the CPU when it's easier, and then just in the end create the GPU array on it, out of it. Because this will be executed only once, while afterwards time loop will be executed many, many times, can be millions of times, right? In this kind of iterative solvers. So it doesn't matter how fast this part is. So this means we have created the flux arrays and the H array with on the GPU that way. And so automatically these calculations here, which before were done on the CPU because it was using CPU arrays, now they're done on the GPU because the arrays are allocated on the GPU, and you don't have to change anything at all. Obviously now we're using GPU array programming and not GPU kernel programming, right, in this code. And so this code is not something close to optimal at all, but it was to show how that works. If you want to make it very good, then you need to apply all the things that we have seen in the other notebooks. And then, well, what remains here is only this update halo. And so let's go look into that. Now, so one has two options when one does GPU, multi-GPU computing with MPI. You can either copy the things explicitly from the GPU to the CPU and then use MPI as before, or you can use so-called CUDA-aware MPI, where you can access directly things from the GPU. You can directly give to MPI functions pointers to your GPU memory. And here we did now the first way, where we explicitly copy things to the CPU. Yeah, one more thing. CUDA-aware MPI has a good advantage that it allows to do what's called a remote direct memory access, which is something, yeah, very much used in high performance computing. Okay, but so now here, we do explicitly copy the things, the data from the GPU to the CPU, and then we send stuff. And when we get stuff, we get it on the CPU, and then we copy it to the GPU. So what do we have to do here? Sorry, these two lines are not needed. So we have we allocate here a send buffer array on the CPU, and then we copy what we need from the GPU in there. And so this will go through the PCI Express bus here on at bit synced. This is something that is, let's say, in the order of magnitude of the network in speed, in terms of speed. I see a question. Hello, yeah. Do you need to unmute?
Yes, hi. Yeah, I have a question. Do you have to map GPU, which GPU to which MPI rank? Or is this assigned automatically?
How to map one GPU to a process?
Yes.
Okay.
Well, on Pitstain, you have each node, you have one GPU, right? Now.
Yes. Okay. So here on Pitstain, we have only one GPU per node, and so automatically it will take this one GPU, device 1. But if you have a node with multiple GPUs, then yes, you have to first select the right GPU. And in MPI, you can do that using the node local MPI rank. So you can get an additional local rank, like here we have me, which is the global rank. You can get a node local rank, and that way you can assign to each process that you want to have on a node. You can assign a GPU.
Okay. Yeah. Thanks.
Okay. All right, so where was I? Okay, so we said we copy the data, the boundary data, right, to the send buffer. Then we also allocate the receive buffer. Then we call MPI send and receive with using these buffers. And in the end, once when we have gotten the result, we copy what we have in the receive buffer into the array where it has to go to. Now note that here, for simplicity, I think for most people it's more logical to have send before receive. Tended to understand. But actually, when you further optimize things, you will exchange these two calls. It is a bit weird, but it is better to put the receive before the send, because you want to have the receiver process already be ready when the send is happening, because else the send will have to write things in a buffer. Yeah, this is something for real further optimizations. Also, for further optimizations, we will use so-called non-blocking MPI. This is in the notebook as well. I can quickly go there. No, not okay. It's maybe not there. We use non-blocking MPI. This means that you can start to send with many. You say send, 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 send. And then at the end, you wait, call something called MPI wait all. Yeah? You wait only at the end. While here, after everything that you do, it will wait. Yeah? Well, after every thing that goes together. All right. But for every send, you need to have a receive, obviously. Then we see here, just after that, the rest is just the analog over the other dimension. Well, here, sorry, this was for the left neighbor, right? Then we do in the X dimension the same for the right neighbor. Then in Y dimension the same for the left neighbor and for the right neighbor. I mean, not the same, but the analog, yeah? Okay, so with this, I conclude that. Okay. Yeah, so this concludes this this part. Yeah, here was the part with MPI wait and wait all, etc. You can see that in this text. This is called MPI I send, MPI I receive are the functions for non-blocking MPI, and MPI wait or wait all, for example, to actually then wait for completion of the communication. Also, note that in these functions here, for simplicity, we allocated the buffers inside, so they're allocated every time. But of course, you should rather pre-allocate them and use pre-allocated buffers instead. With the buffers, I mean the send buffer and the receive buffer. Welcome to the third day of GPU programming with Julia. I'm super excited to have today to introduce Tim Besar from Julia Computing Inc. He is the lead developer of CUDA.jl, and he will show us some a lot of different things, new features, etc. Even a few unreleased features, maybe. Yeah, it will be really exciting. And
okay, can you see my screen?
Yes, we can.
Okay, great. So as Samuel mentioned, once you have set up the Jupyter Hub instance on the supercomputer, you can check out the notebooks I'll be using from this course, which I have on GitHub. So I'll share a link. So maybe you've done that in one of the past courses already, but to check that out, you can just launch a terminal and then do a git clone of the link you have there. Yeah, Harman just posted it in the general channel already. I have it checked out in this CSCS GPU course folder already. Once you've done that, you can switch directories and open the notebooks to follow along. So in the latest commit on that repository, I've removed the output as well as the solutions. So in any case, if you're stuck or if you want to see the solutions that I've added, you can just go back one commit in history, and then all of the content, all of the solutions are still there. It also renders on GitHub, albeit a little slowly. But to follow along, it might be convenient not to have all of the answers filled out already, to maybe spend some time in thinking along and trying to figure out some of the answers to some of the problems in the notebooks. However, I think that the style I'll be teaching with is going to be a little different from the past couple of days, in that I have fewer exercises that Samuel had. Nonetheless, tomorrow I'll have some more exercises to follow along. Today I'm going to be focusing on some of the lower level aspects of working with CUDA.jl, some of the libraries, how you can use them, the different programming models, a little more in depth, some specifics on memory management as well as concurrent computing. And then for tomorrow, I'll be focusing on optimization of GPU applications and then a in-depth optimization of a specific kernel. So those will be much more exercise driven, using the profiler to figure out where some of the slowdowns are and how to accelerate a GPU application. And I'll try to follow along Slack in case there's some questions. Anyways, as I mentioned, I'll be using my own local Jupyter instance. There shouldn't be a difference between the one locally and the one running on the supercomputer. We've verified that all of the notebooks also work on the supercomputer, but I prefer to do so locally because I have a more recent Julia installation which I need for some of the cells I'll be rendering, as well to more easily integrate with the profiler tomorrow. So for simplicity, I'll be using my own local Jupyter instance, but that shouldn't make any difference. And if there's some issue with the one running on the supercomputer, feel free to mention that in chat and we'll have a look what's going on. So let me start by clearing all of the output. Since I'm using a couple of more recent packages than are available on the cluster, you'll need to start every notebook by activating the project file that's part of the repository and then instantiating that project. So if you have a look at the repository, you can see there's a project and a manifest in there. And in that manifest, there's some specific versions, some specifics, revisions even from an unreleased CUDA version that I will be using for this course. Those aren't any hot new unreleased features, but mostly bug fixes for issues I ran into while preparing the content for this course. So nothing as exciting as Samuel mentioned. Anyway, so by doing this snippet at the start of every notebook, you'll be activating the project in the directory of your Git clone, or at least directory where this file resides in. And then when you instantiate the environment, it will be downloading all of the packages and making sure they are active in the current session. And the first time you do this, this may take a couple of minutes because it needs to download all of the packages as well as pre-compile them such that when you want to import them, that goes rapidly. Of course, in my case, all of that has happened already. So the second time you issue this command, it's going to be instantaneous. So now I've activated my environment, as you can see in the output, and now I can just import CUDA package. And for this first notebook, I'll be talking about the different libraries that you can use through CUDA.jl, because CUDA.jl in effect is more than just a GPU compiler. You can do more with the package than just write kernel code and execute that kernel code on the GPU. It's also the main package to interface with several CUDA and NVIDIA libraries. Actually, I should probably up my font a little. Is this readable for everybody?
For me, it looks fine.
Okay, great. So CUDA.jl can be used to interface with a couple of libraries. The main library we work with, or you as a user work with indirectly, is the driver library. As you can see on this picture, the driver is the bottom-most, lowest level interface for working with an NVIDIA GPU. And this is the main library that CUDA.jl uses to make all of its functionality possible. And that library is actually similar to the CUDA runtime library, and the CUDA runtime library is the library you would have been using in CUDA-C when you allocate memory or when you switch devices and so on and so forth. CUDA.jl itself doesn't use the CUDA runtime, but it provides a similar abstraction as the CUDA runtime does in CUDA-C, built on top of the CUDA driver library. And then on top of that, we also have several application libraries like cuBLAS, cuDNN, cuTensor, and so on. And CUDA.jl also makes it possible to interface with those libraries, either explicitly or automatically by just using some high-level interface. So the package provides wrappers to interface with all those libraries, and the specific ones apart from the driver I mentioned is cuBLAS for doing linear algebra, cuRand for doing random number generation, cuFFT for fast Fourier transforms, there's cuSparse for sparse arrays, and then cuSolver for matrix decompositions and linear systems. And those libraries are all part of the CUDA toolkit. But CUDA.jl also supports a couple of libraries that aren't part of the CUDA toolkit itself, such as cuDNN for doing machine learning with deep neural networks, and cuTensor for linear algebra with tensor contractions, and so on. There's a couple of other libraries like NVML, CUPT, and VPTX, but those are much, much lower level libraries that you as a user probably won't ever use. But all of those other libraries are ready for you to use. And in order to make that as easy as possible, CUDA.jl by default is going to automate the entire installation procedure and version management, because typically it's not as easy to install the CUDA toolkit as it's with ordinary libraries. For example, the CUDA toolkit you select has to be compatible with the driver that's installed in your system. Some of those drivers support what NVIDIA calls forwards enhanced compatibility, which is a typical forwards compatible upgrade path. But with some drivers, it's also possible to upgrade the driver library itself. And of course, external libraries like cuDNN and cuTensor, when you download them, you have to select which CUDA toolkit you are using, which then in turn is again dependent on the driver you're using. So basically, there's a whole complexity of compatibility that typically you as a user do not want to deal with. And that's why CUDA.jl generally manages all that for you. So we have repackaged the CUDA toolkit, as well as all of these libraries using binary wrappers. So in Julia, in the Yggdrasil repository. And as soon as you use CUDA.jl for the first time, it's going to look at which driver you have. It's going to look at whether it can upgrade the driver library. And then it's going to automatically download and provide the most up-to-date libraries that are available for your system and that CUDA.jl supports. You can see here in this output, this is what's meant by artifact installation. It's CUDA.jl has automatically installed all of these libraries from what we in the Julia world called artifacts. And then the specific versions are listed here. However, generally, especially on supercomputers, administrators aren't always as happy that all users download their own libraries and they want to manage everything themselves. And sometimes that's valuable because you have an unreleased version of CUDA or because you have some very specific hardware. But in general, I wouldn't recommend users wanting to manage CUDA installation themselves. However, you can do so, and you can do so by defining the Julia CUDA use binary builder environment variable before importing CUDA.jl. If you define that variable and you set it to false, then CUDA.jl will not try to resolve any of the versions and any of the libraries it needs, but it will just look at the local system, what is available. And then you can see the output where it mentions local installation. And if you run this command on, and maybe I'll try, so if you do this on the cluster, so let me replicate this, so instantiate environment, import the package, and then execute the version info call. Of course, it always takes a second. As you know, Julia has a significant time to first plot, as we call it, because of the compilation of code that we do. And now the version info call. And you can see here on the cluster that it has returned local installation. And that's because the cluster administrators have set this very environment variable. So you can do Julia CUDA use. And you can see that it's been set to false, convincing CUDA.jl that it doesn't need to do its own library resolution. Another neat thing you can see here is that it managed to upgrade the CUDA driver from one that's compatible with CUDA 11.2 to one that's compatible with CUDA 11.4, which is significant because that gives us some additional features like the stream ordered memory allocator, which I'll be talking about today or tomorrow, depending on how much time we have. Anyway, let's switch back to my Jupyter installation. If you were to run into any issues, either with the automatic installation or the installation using CUDA, Julia CUDA use binary builder equals false, then you can also set the Julia debug environment flag to CUDA. And this is also this is actually a generic feature of Julia, where if this is set, all debug messages will become visible. And CUDA.jl has a bunch of these debug messages all over its binary dependency management code. So if you were to run into any issue, then you can always set this environment variable to CUDA, and then you will see a lot of details on which binaries, which libraries are detected, what the version of them are. So if you have any issue with all this, then you can always file an issue with the output of Julia debug set to CUDA, and we'll probably be able to help you along there. So once everything has been set up, meaning you have imported CUDA.jl and it has a functioning installation, then you can query all of the libraries that it has detected by these entry point functions. For example, if you do CUDA.lib_kublas, it will return the path of a kublas library that's ready to use. And as you can see here, that's part of an artifact because Julia has downloaded this kublas for us. However, generally, it's never necessary for you as a user to use this low-level library, because for all of these libraries, in this case kublas, we provide wrappers at different levels of abstraction. So at the lowest level of abstraction, we give you basically the C functions that are available in this library. For example, in the case of kublas, a function like kublas_gemx, which is the C function to do a matrix multiplication, is readily available in the kublas module. So you can just do kublas.kublas_gemx, and then you can execute as if you were executing C code. This is very convenient if you're porting code from CUDA C or C to Julia, because you can most of the time just keep on using all of these low-level C functions. I'll demonstrate that later in this notebook, but I just want to highlight the different level of abstractions we have. Then typically above those C APIs, we have a slightly higher level function. For example, we have the gemx function, which automatically configures some properties, some values that need to be passed to the low-level C function. It makes it that you don't have to pass pointers, but you can pass arrays. So it basically raises the level of abstraction from C to Julia. And then if possible, we also try to integrate with high-level interfaces. For example, in the case of a matrix multiplication as implemented by the gemx function, we also provide an implementation of the linear algebra mulbank function, which is the Julia standard API function for doing matrix multiplication. And as a result of that, you can use kublas by never ever touching these kublas function, because you can just use the multiplication function from the linear algebra package. But again, as I mentioned, more on those library wrappers later. I'll first start with a brief overview of the functionality from the CUDA driver library. But as I mentioned, we don't necessarily force you to work with the CUDA driver library at the lowest level. We provide high-level wrappers that make it convenient to work with these APIs. For example, if you want to iterate devices, we just have a very convenient devices iterator. And this is also the reason I'm using my local system, because here I have 2 GPUs, so I can demonstrate multi-GPU functionality, whereas on the cluster, there's only a single GPU per node. So this output matches the output in NVIDIA SMI, and using the indices from the device iterator, you can instantiate a device object. So here I've instantiated an object for my Quadro RTX 5000. If I were to make it device 1, you get the Titan. That's pretty straightforward. So that device object can then be used to query all kinds of information from the device that may be useful for using functionality in CUDA. For example, you might want to check the compute capability. And that's because some functionality, if you were to look at the documentation of, say, cuBLAS, might note that it's only available starting at a certain compute capability. So with these functions, with these convenience function, you can fetch a couple of these commonly used attributes. Another one is, for example, the total amount of memory that's available. Generally, though, there's much more attributes to query, and you can always look at the CUDA driver API, which of these are available, and that's a huge enumeration with all kinds of device attributes. And you can pass those to the attribute function. For example, in this case, I'm querying the maximum amount of threads per block. And remember that number because it will be relevant in one of the future notebooks. Maybe a small detail. So we dropped the CU prefix from the enumeration because we already have it prefixed by the CUDA module. So you can just do CUDA dot and then device attribute max threads per block, as is mentioned in the comment below. Another common object that's actually used all over the place, but typically hidden for most users, is the context. So a CUDA context is much like a CPU process. It encapsulates all allocations, all state that you're doing in your current CPU process. So you can instantiate a context for a device, and then we can just display this context. And by using this doBlock constructor, the context will be destroyed after the end of this block. However, as I mentioned, generally, you don't need to deal with context yourself because CUDA.jl, the package, is going to manage a context for every device in your system for you automatically. And you can query that context by calling the context function. And this is actually the big difference between, in C, the CUDA driver library and the CUDA runtime library. The CUDA runtime library is also going to manage context for you, whereas with the CUDA C driver library, you have to do everything yourself. And we similarly in CUDA.jl automatically manage context for you, such that the programming experience by using CUDA.jl is very similar as to using CUDA C, where you typically also call into the CUDA runtime API. So because we have a automatically managed context, we of course also have a device that's associated with this. And in order to switch devices and as a result switch context, you can use the device bang function. So if you call device bang, and then we can see the context within that block is different from the context we had allocated before, because we have one context per device. It's also still possible to tear down the global context. For example, when you're dealing with an application that consumes a lot of memory or that has memory leaks, you might want to tear down the context afterwards. But that's a very dangerous function because every outstanding array or any object for that matter that you had allocated before resetting the context is invalid afterwards, even though it may still be reachable in your Julia session. So if you were to allocate an array, reset the context, and then try to launch your kernel using that array, for example, you will be running into illegal memory accesses. Nonetheless, even though it's a dangerous call, it might be useful for some applications, again, where you're dealing, for example, with memory leaks or with a very long-running application where you want to reset, start from a clean slate. And to illustrate that we have a different context, the context is unequal to the context we had allocated before resetting the device. So, but as I mentioned, generally, you don't need to deal with contexts. CUDA manages them automatically for you. And the only thing you might want to do is configure the context. For example, one of the common things you might want to influence is the cache configuration. This is also documented in the CUDA driver APIs. So you can, for example, you can influence whether the L1 cache is going to be used for either shared memory, a preference for shared memory, or a preference for caching. And this is something that's being set on a context global scope, and you can do so using the cache config bang function. I'm going to have a look at the Slack first to see whether there's any questions.
There's one question regarding, are any of these libraries also useful when using MPI? So is this single node or is this also multiple node libraries?
All of these packages are single node. So you can use them in combination with MPI, but as far as I know, they know nothing about a multi-node setup. If that answers the question.
Yes, it does. Thanks.
Yeah, so if you on the cluster we're using, if you try to access device 1, it's going to fail in the same way that device 3 is going to fail here. You'll get to see invalid device ordinal because in effect I only have 2 devices. Now, interestingly, the way how the cluster has been configured is in so-called compute exclusive mode, which means that once you can only instantiate 1 context per device. And that's a cluster-wide setting, which I couldn't change. But it means that, for example, if you have 1 notebook running and it has a context activated because you've allocated some array, or if you have done some kernel or whatever, and you won't be able to launch a second notebook and use the GPU in there before you have shut down the first notebook, which has allocated a context. And again, that's because the cluster's hardware has been configured in compute exclusive mode. And for interactive views, it's generally interesting to not have it configured like that, but it's an administrative level setting, which I couldn't change. Anyway, so contexts aren't typically that interesting for you as a user, but streams can be. So for anybody who's worked in CUDA-C using realistic applications, you have probably dealt with streams to automatically order computations, either for correctness, because within a stream, kernels and other operations are executed in order, or for performance, because you want multiple independent operations to overlap. But again, CUDA.jl, and this is a difference to CUDA-C, where all of CUDA-C, even with the runtime API, is going to use the so-called default stream. And this is actually the same as passing a null pointer as a stream object. So we have a single stream for the entire application, unless if you use explicit streams. Now you can use explicit streams in CUDA.jl as well by instantiating a stream object and then passing that stream object to every GPU operation that takes a stream argument. So in the case of kernels, it's a keyword argument you can set to stream. But in case of libraries, it can be vastly different. Typically, you have to configure the handle of the library to be using that stream for every operation on that handle. But as it should be obvious, that's not easy because, for example, if you're calling the mulbang function from linear algebra, you don't necessarily control how cuBLAS is being involved. So as a result, it's tricky to pass down that stream object to every API call that's being made. And because of that difficulty, we've also decided that CUDA.jl should manage the stream for you. So instead of using the default stream, we'll be using a task local stream. So we have this stream function, which gives a specific stream object that will be used for every GPU operation. However, as I mentioned, it's the task local property, which means that if we start a new task and we query the stream object in there as well, you can see we get a different stream. And this is really powerful because it greatly simplifies multiprocessing with multiple streams, because you can just spawn a new task and encapsulate GPU operations in there in order to use a different stream. But I have a full notebook on this way of concurrent programming, which I hopefully will get into before the end of the day. Synchronization is something you probably have done in the previous notebook already, when you have to wait for the stream to be ready. And similarly, because we have a task local stream, if you do a synchronization in CUDA.jl, it's also just going to be synchronizing the local stream, which again makes it possible for other streams, for other tasks to be computing, whereas in other languages, or if you typically synchronize in CUDA-C, then this would be a blocking API call. So you can see here, if we query the stream before the synchronization call, it wasn't done. If we query it afterwards, it is done. Another convenient feature you can be using with streams is so-called priorities. So if you have multiple streams, you can configure one stream to be more important than another by setting a priority. You can query the priorities that you can use using the priority range function, and you can query the default priority of a stream, which by default is 0, and we can create a new stream with a different priority by passing the priority keyword argument to the stream constructor. And then in order to use this stream, you can, instead of having to again pass it down to every function which takes or doesn't take a stream argument, you can call the stream bang function to call the current task local stream. So for example, in this snippet, I'm spawning a new task. I'm overriding the stream for this task by this new stream I've created, and then I'm querying the priority of the current stream and the current task. You can see that it's -5, which is the highest priority. And this can be useful when you're working with multiple streams or multiple tasks, and you want to make clear that the operations that are being queued on one task are more important than on another one. And the GPU can then use that to order operations adequately. Another common object that you might be using if you're programming in a CUDA application are events. So CUDA events can be used for different things. You can use them to time operations. For example, in this snippet, I'm creating 2 events. And then by calling the record function, we're going to queue an operation that marks when an event is reached on a stream. Then we call an expensive operation. I'm doing a matrix multiplication of 2 10K by 10K matrices, and then I'm recording my second event. So let's do this. And then afterwards, we can synchronize our event, which means we're going to wait on the execution, on the completion of our secondary event, and then we can query the elapsed time between those 2 events. And this is a convenient way if you want to know in your application how long it actually took between 2 things to be happening on the GPU. So if you were to measure this from the CPU side, then this measurement might be inaccurate because GPU operations are executed asynchronously from the CPU side. And by using events, you're using the CUDA API and you're having the GPU note when a certain event is processed on the GPU. So you get an accurate execution time on the GPU. So if you try this again, you can see it's fairly stable. Yeah, pretty stable. So, and because this is a fairly common feature, we have a more high-level way of doing this, and that's the add elapsed function. So similarly to how the Julia standard library has an add elapsed macro, making it possible to measure time from the CPU side, with the CUDA add elapsed macro, it's possible to measure it on the GPU side by using events behind the scenes. And this is, of course, a great way to do profiling of kernels. However, we have several other options for profiling, and I'll be explaining those all in depth tomorrow when we'll be talking about how to profile, analyze, and optimize a GPU application. So something else that events are useful for is when you want to insert dependencies between individual streams, because generally when you have two streams, they are fully independent. So as I previously explained, typically if you have dependent kernels, you all insert them on the same stream. However, the disadvantage of that is that the GPU can never overlap independent operations, even though there might be only a very small dependency between both streams. So instead, what you can do manually is you can use events to express what the specific dependency is between streams. And we can do so. Let me have a look at my example. Yeah, so we can do so by, I'm going to illustrate by using the launch function. So the launch function is a function that's going to queue a CPU function to be executed when the current stream, so when the current queue of operations on the GPU has finished. For example, currently the GPU is idle. I can check so by using the isDone function. So the current stream is fully idle, which means that if I currently launch this function on the CPU by means of the launch function, which is going to insert it on the GPU stream, it's immediately going to execute because, as I mentioned, the GPU was idle. However, using events, we can make a stream block on something. So first, I'm creating an event that's going to be representing my dependency. And I'm going to make the current stream wait on it. So again, the fact that this is going to make the current stream wait is because we implicitly use the stream argument in all of our API functions. So even though you can pass a stream argument to the wait function, by default, it's going to be using the current task local stream. And if we then, again, ask the GPU to execute the CPU function, we aren't going to be seeing anything. Oh, wait, we are. What's happening? Okay, this is strange. Well, we shouldn't be seeing this. All right, this doesn't work, even though it did yesterday. Yeah. I'll continue my explanation, but I'll have to have a look at why this isn't working anymore. So what ordinarily should have happened is that by queuing a wait on this event, the current stream wouldn't get to execute this launch function because the current stream was blocking on the dependency. However, then we could record in a different stream our dependency, which notes that the event is done, allowing the stream on another task to continue. And this is a mechanism of expressing dependencies between otherwise unrelated streams. So on the one stream, you can create an event, have the stream wait on it, and then you can record that event from a different stream, making it so that the other stream can continue. And this is a very fine-grained way of maximizing utilization of the GPU because you have multiple streams that can still execute code in parallel. I'll have a look whether there's other questions. So yeah, this is all. I'm I'm used to starting from the bottom up. So this is the low-level parts of the stack, just to show that people who are coming from C and C++ still are able to use all of the low-level familiar tools they have been building CUDA applications with in Julia CUDA without losing performance or without losing flexibility. However, for most users, these functionalities are generally not necessary, or at least not from the get-go. So in the next notebooks, I will be building up and showing the high-level functionality that we also have available in these packages, making it convenient to program GPUs without having to know anything of the CUDA driver library. But first, I want to get this out of the way, because this often provides some of the basics that I need to explain some of the more advanced features that we have implemented in CUDA.jl. So another recent CUDA feature that might be interesting when you're developing an applications are computational graphs. So typically when you, for example, allocate an array and then you perform a couple of operations, each of those operations are going to be queuing a new GPU operation, which makes it fairly expensive to perform multiple GPU operations in succession. And it's generally very interesting to fuse operations together into a single kernel. And this is what we'll be doing tomorrow when we're optimizing a GPU application consisting of multiple individual GPU operations. Trying to fuse them together into fewer operations is always going to be great for performance. However, nowadays, the CUDA toolkit also has a way to do that automatically for you. And that's by building a computational graph. For example, if the sequence of 3 kernels, if we want to execute these multiple times, for example, as a time step in a for loop, and what we can do is we can capture the operations in a graph. And this doesn't mutate the data, but so the data is still 9 as it was before. However, it records all of the GPU operations that would have executed if we were to execute this code. And then afterwards, we can instantiate the graph and we can launch it multiple times. However, when we want to update the data on which we want to call it, for example, if now instead of the matrix A, we want to execute that graph on the matrix B, then we do need to recapture. However, instead of instantiating the graph again, we'll just be updating our existing instantiating. And this is much cheaper than instantiating the graph from scratch again. And this is why it can be interesting to have such a sequence of graph captures, updates, and launches in a for loop, because presumably it's cheaper than doing the operations by themselves. And you can get the performance boost out of it because the operations will then be fused into a single kernel. So if you do this, then you can see we get the expected result in B, which went from 1 to 9, which is similar what we did with the A matrix. And because this is such a common sequence of operations, because we also have to deal with, for example, when we do something incompatible. So here I'm changing the shape of the matrix. I was using a vector of size 1. Here I'm changing it to a matrix of size 1 by 1. And if we then try to update our graph, CUDA is going to complain that this isn't compatible because the update is too different from the original instantiation that we had captured. And then we need to re-instantiate. And again, this is a fairly common pattern where you have to see if you can update a graph given the new inputs, or if not, whether you have to re-instantiate. And to make it more convenient, CUDA.jl provides an add captured macro, where you can just, so you have the functionality that just works like that, and by adding it to add captured, it's going to automatically perform the graph captured, the instantiation, and then in the second iteration, it's going to do a recapture, try to update, and if that fails, try to instantiate again. And this is a very convenient pattern that may be helpful when implementing an GPU application that needs to perform kernels in a loop. And tomorrow we'll be profiling exactly how this performs. And the spoiler there is that it doesn't necessarily always improve performance. So it's definitely no silver bullet to apply to all of your for loops with small GPU operations. It's generally still interesting to fuse operations together. And there's some other APIs that I won't be discussing in detail in this notebook, but I will into one of the future ones. For example, how to manage kernels, because that will that actually mostly happens automatically by using the @CUDA macro, which you've used before. We also have the occupancy API, which is a way to query how many threads and blocks you should be launching for a kernel. And of course, all of the memory management pieces I left out because I have a dedicated notebook for that. And then the last detail I want to highlight on the CUDA driver API is that all of these high-level or relatively high-level objects like CUDA-device, CUDA-context, events, and streams, you can use those in combination with existing C functions. So even though the C functions generally expect a pointer, if you were to have a look at the documentation for example, this CUDA-device can access peer function, it takes a device ordinal, not a device object. However, we've set up automatic conversions between all of our high-level objects and all of these C functions so that you can automatically use all of the C functions without conversions. So here I have two devices, as I mentioned, and I want to check whether I can do peer-to-peer access, which is a function we don't have a high-level wrapper for yet. However, we can just call the C function, which takes an output pointer to store the result in. Nonetheless, we can just pass CUDA-devices to that C function without having to do any conversion to ordinals ourselves. And the same applies to the application libraries. So as I mentioned, for example, with cuBLAS, we can do matrix multiplication or generally linear algebra. And the wrappers for those libraries are again split up in the very low-level C-style functions you might have been using in your C application. So more higher-level Julia functions, where we have all of the C-isms removed and then integration with high-level packages. And I demonstrated the GEMX function, or I mentioned the gem function before, but this is a good demonstration on how these APIs work. So let's illustrate that using the sgem function, which is going to perform a matrix multiplication of single precision floating point values. So for that, we start by allocating two matrices of 1024 by 1024 single precision floating point numbers. When you want to use the cuBLAS sgem API, so we can have a look at the documentation here, you can see that all of these APIs take a handle. And if you want some of the low-level functions in the cuBLAS API or in any other API, you will need to pass a library handle. And CUDA API and CUDA.jl generates such a handle for you. Every submodule has a handle function. So we can do cuBLAS.handle, we can do cuFFT.handle, cuDNN.handle, and so on and so forth. And again, these handles are task local. So if you were working on a different task, then you can see you've got a different handle. This may seem irrelevant at this point, but it will become important when we talk about concurrent computing, which I will again in the latest notebook for the day. So then with this handle, we can invoke the lowest level function that the cuBLAS library has available, which is the sgem function. Do note the v2 suffix, which is missing from the documentation, but it is there and you need to use it because of how the library actually versions their symbols. Once they have a breaking change, the CUDA APIs introduce a versioned subfunction, and then the older function can still be used in a binary compatible way, but newer source code will automatically be using the newer function. So if we were to compare, if we were to have a look at the documentation, we can see we need to pass the handle, the operation, transpose, conjugate, and so on, dimensions, scaling factor, pointer to the array, leading dimension, pointer to another array, also leading dimension, another scaling factor. So let's do that in Julia, where we first allocate a output container that has the appropriate size for a matrix multiplication. These matrices are not transposed, so we pass a n, and then we pass all of the relevant sizes, scaling factor of 1, bias factor of 0, and all of the strides. And like that, we get a fully working matrix multiplication because we're comparing with what the result would have been if we were to compute this matrix multiplication on the CPU. And this is just to illustrate the lowest levels way of interfacing with CUDA libraries. And this is generally how you would be using these libraries in C or C++. Of course, in Julia, we want to make it easier. So on top of that, we've written functions that, for example, remove all of the stride and size arguments, because you can automatically derive that from the array. Also, it changes the S name in the function, because we can derive which precision version of this function to call again from the input arrays. So we have this gem function which does all that for you. So the only things we still have to call pass is whether it's a transpose or not, scaling factor, bias factor, and the free arrays. All of the rest is automatically derived from the inputs. And in that sense, this is a very Julian function that removes all of the C-specific stuff. But of course, for most users, this is still fairly low level, and that's why CUDA.jl integrates with all relevant high-level interfaces. And in this case, that's the mul interface from linear algebra, where you can just do a multiplication of A times B and write the result in C, or you can actually just use the multiplication symbol, which will automatically dispatch to this mul bang function. And the implementation of that is built on gem, is built on this sgem function. And the reason I explain this is because it still may happen that, especially if you're porting code, or when you're looking into a very, say, specific solver or a specific decomposition, that you want to call some functionality that we haven't fully wrapped in CUDA.jl. We might not have had integrated with the relevant standard library, or we might not even have provided a high-level wrapper. And that's why I explained this, that it's actually not that difficult to just go in and read CUDA documentation, figure out which API function you want to call, and do so. And if you have time for that, contribute that change as a PR to CUDA.jl. But nonetheless, the fact that it's still possible to, from within Julia, use all of the C functionality, and doing so fairly user-friendly by, for example, being able to pass arrays and not having to cast everything to pointers, makes it a fairly productive programming environment, even if you're coming from another language and having to port code. So I'm almost done with this part. The only briefly one I want to still show off is the NVIDIA management library, just because it gives some cool statistics. So with the NVML library, you can instantiate a device, but it needs to be an NVML device. And NVML devices are not indexed by the ordinal that we've used in the previous example. So if you did devices, you can see that my Quadro is device 0 and my Titan is device 1. In order to instantiate an NVML device, we need to pass a UUID, but we can derive a UUID from my CUDA device. Nonetheless, that doesn't matter much. We still get a NVML device that represents my Quadro, and as you can see, the ordinal of the NVML device is actually 1, whereas the ordinal of the CUDA device was 0. Doesn't matter. The fun thing is that with this NVML device, we can query some more interesting metrics, like, for example, the power usage of my GPU, or the current utilization rates, how much compute is being used and how much memory is being used as a percentage. And we can also inspect which processes are currently using the GPU. And this is interesting when, for example, you write an application and you want to have some statistics in the front end to show how effectively or not the GPU is being used, how much power it consumes, and so on. All right, this has been the first hour, and I propose to take maybe a 5 or 10 minute break to give everybody the chance to go through the notebook, maybe experiment a little with some of these APIs and ask some questions if anything was not clear. And then in a couple of minutes, I'll resume by explaining the different programming models that CUDA.jl has to offer. So instead of using libraries, how you can actually write code for the GPU. All right, welcome back. I'll start now with the second notebook in the repository, which is focusing on the different programming models. So the first notebook was on all the libraries that CUDA.jl makes available to you. The second notebook is going to be on how you write kernel code, or just how you write code that executes on the GPU. Now, presumably, you've been doing a lot of that in the past 2 days already. So I'll be focusing on some more problematic areas or some more advanced areas. But maybe first for some overview. So let me start by activating my environment. Note that I'm using Julia 1.7 for this notebook, and that's just because some of the code reflection that you'll see later down this notebook is of slightly higher quality in Julia 1.7. It all still works on Julia 1.6, so CUDA.jl does still support Julia 1.6, but some features work notably better in Julia 1.7. So I'd recommend you, if Julia 1.7 comes out in a couple of weeks, hopefully, to use that version as soon as it's available on your cluster. So in terms of writing code for the GPU, there's 2 ways to go about.
By the way, Tim, I'm not seeing your screen at the moment.
Ah, yeah, sorry.
No worries.
Yeah.
And also maybe before we continue, there was one question on Slack, which was already answered, but maybe for posterity, because Slack is not recorded in this session, maybe we could still go over that one. So somebody is asking, in the previous notebook, you were using the mul function, which was imported from the linear algebra module. How come it can still do a multiplication on the GPU, even though linear algebra doesn't know about the GPU? I think this is the kind of question that comes up when you're used to Python and you start using Julia.
Yes, that's a very good question. So in Julia, if it's basically function overloading. So some function are both an API and an implementation, where the function, the mul bank function from linear algebra, is going to be implemented in a way that is compatible with most CPU arrays. Whereas CUDA.jl, when you import the package, it's going to be loading additional definitions of this linear algebra.mul bank function, providing specialized versions that will only be used when you invoke that function with GPU arrays. But in effect, when you do so, they will be using kublas or will otherwise be using a version of the function that's optimized for the GPU. It's basically a function overloading, but more fine-grained, because we have control over, we can accurately dispatch to one implementation or another based on every argument that's passed to the function. Anything you want to add to that, Harman?
No, I think it's a perfect explanation. Thanks.
All right, so I didn't show my screen, so let's start again. Just by instantiating my environment, and as I wanted to show in the upper right-hand corner, it shows that I'm using Julia 1.7, but that doesn't matter too much. So essentially 2 ways of programming GPUs. Either you write your own kernel function or you use the higher level abstractions that we've built on top of that. And typically those are the array programming abstractions, where you use an array object in combination with vectorized operation, meaning operations that apply to multiple elements of that array at once. And that operation has then been implemented in a GPU-friendly manner. And with CUDA.jl, that's the cuArray type. So if we import the CUDA package and we allocate some data, we can simply do so by invoking the cuArray constructor, passing a CPU array along. This will automatically allocate some data on the GPU and copy our CPU memory to the GPU. So in effect, the cuArray type serves multiple functions here. On the one hand, it's a managed container for GPU memory, meaning it ties some GPU memory to the CPU object, having assigned some values to it. And it's also a way to dispatch to CPU specialized functionality. So to illustrate with the mul function, if we were to call a multiplication function on this A object, Julia knows that we're looking for a specific method that applies to cuArrays, and CUDA.jl provides such methods. If it didn't, then we just fall back to the default implementation, the fallback implementation, we also often call it, in the Julia standard library. And oftentimes, those default implementations are fairly GPU compatible, unless they do something incompatible, as I'll demonstrate in a couple of minutes. Much functionality from the base standard library or from whatever package you're using might already just work on the GPU, just by virtue of changing the input type to a cuArray type. Many array operations are will automatically work. The goal of the cuArray type is to make it as user-friendly possible for you to use the GPU. For example, if you have this cuArray type allocated, which is a 2x2 matrix, just by doing a multiplication, you'll automatically get the multiplied version of those matrices. But we'll also be using cuBLAS automatically behind the scenes. So all of those lower level methods I showed in the previous notebook, you don't ever need to use them, because as much as possible, we've integrated all of that functionality with high level integrations. However, at the same time, if some lower level library doesn't implement this operation, for example, if you want to be doing a element-wise multiplication, then we'll be using a native kernel that we've written in Julia, because it's possible to compile Julia to CUDA. And now we get, well, the different answer, the answer we expect. But the way this works is completely different, yet hidden from the user, because again, we try to make everything as user-friendly as possible using this array abstraction. However, I could go on demonstrating how impressive this array abstraction can be. But assuming that you've seen a lot of that in the previous days already, instead I'll be focusing on what the issues may be. Because sometimes occasionally you may be calling a function, a fallback function from the base standard library, or some functionality from a package that doesn't turn out to be GPU compatible. So it needs a specialized operation, for example, in CUDA.jl, but it hasn't gotten one. And this can manifest as different ways, different errors, really. So in case of, for example, if your function is calling a C library, like the BLAST function for CPU, or some function in MKL, and it's trying to pass a GPU array to such a function, that wouldn't be able to work, because generally GPU memory isn't addressable from the CPU. And that would crash your application. And in order to prevent that, we actually use a different pointer type for CPU allocations. And if some code you're calling tries to interface with the C library, then it would fail and you would see this error. cannot take the CPU address of a CUDA array. So if you ever run into this error, again, it doesn't happen much, but it's one of the errors that might happen if you want to use a CUDA array and throw whatever functionality you've written or applications or packages at it, then this is one of the errors you might be running into. This indicates that we are calling some functionality that wants to do a C call, a low-level C API function that requires CPU memory and isn't compatible with GPU memory. Another common issue that you might be running into is that some operations use what we call scalar iteration. So Julia is known for its JIT compiler, making it possible to write code that contains for loops, whereas in languages like Python or R, which are interpreted, for loops are fairly expensive, and it's better to call vectorized operations, which then use a operation that has been implemented in C. But in Julia, it's possible to write your own for loops and expect code to work fast. However, it's a double-edged sword because those for loops are very incompatible with GPU code. And the reason behind that is that if we have a CUDA array, which represents some memory on the GPU, that is an object on the CPU. And as a result, every operation that we perform with that CUDA array is going to get lowered to a single invocation of a GPU kernel or a function in cuBLAS, for example. So in this case, if, for example, we want to compute the sum of our array, and we do so by iterating every element in our array, fetching it and adding it to an accumulator, this will be launching a GPU operation for every iteration. It will be fetching a single element for every operation. And in fact, it will be performing the addition not on the GPU, but on the CPU, because it has fetched a scalar. And we don't have anything like a GPU scalar. Anyway, long story short, for loops or other algorithms that fetch one element at a time, if you use those with a GPU array, those are going to be excessively slow. And in fact, we're actually not using the GPU at this point. We're just fetching memory and doing something with that memory on the CPU. And it can happen to run into these kinds of functions when you use packages or when you use certain functionality from the Julia standard library, which we haven't optimized for GPUs yet. And because it's so slow, if we execute this code, didn't do that, if we execute this code, the first time you'll do so, you'll get a nasty warning where it explains somewhat more briefly what I've just explained, that these kind of scalar operations are very slow. And you might wonder then, why should we ever enable it? Well, that's because on the one hand, it's very convenient when you're porting applications that have been written with array in mind. If you want to port them to the GPU piece by piece, whereas you still want to be able to maintain that the result is correct. If then the CUDA.jl package would throw an error straight away, you wouldn't be able to verify the result until you've ported your entire application, and that's of course not productive. However, of course, if at the end of your porting effort, you think you've removed all of the scalar iteration, then it's interesting to toggle the flag, and you can do so by calling the allow scalar function. And as such, I recommend to do so whenever you've got a production-worthy application. And if then an application tries to do any scalar iteration, as for example, I tried to do here, then you'll get an error and your application will not proceed. But again, I don't recommend doing this in an interactive session because on the one hand, as I mentioned, when you port code, you want to be able to verify everything. But also when you've wrapped code in a complicated manner, some of the display functions may trigger scalar iteration. For example, if I take a transpose of a function, the show function still works. But if I take a view of my transpose, then all of a sudden we're triggering scalar iteration. And this is a result of how Julia's type system work, where these array wrappers, because both a view and a transpose are implemented by wrapping the original object, Well, by doing so, we end up dispatching to a non-GPU specific show function. So again, for interactive purposes, it's recommended not to disable scalar iteration, or at least not until you're absolutely sure that you won't be triggering this kind of functionality. Another interesting consequence of what I've explained before is namely that a QArray object, even though it represents GPU memory, it's still an object that lives on the CPU, is that we don't actually use QArrays on the GPU. So when you invoke a kernel, for example, here I'm calling a dummy kernel, a kernel that does nothing, but I'm passing a QArray. And what you can see in the output is that we've actually used a CUDA.device array on the device. And that's an interesting consequence of how our array package works, namely that the object that lives on the CPU isn't necessarily GPU compatible, because, for example, the object on the CPU is meant to be dispatching to cuBLAS, to cuSolver, to cuFFT, and to a bunch of other CPU libraries which ultimately use the GPU. But that means it isn't GPU compatible, and we need a different object, a different type, to be able to implement those methods in a GPU compatible manner on the GPU. And this is a bit of an implementation detail, but the only reason I mention it is that if you create a struct with a QArray in that, and then you try to pass that struct to a kernel, then the GPU compiler will complain, because then all of a sudden we're trying to pass a QArray, not a CUDA.device array, to a GPU kernel. And that's, as I mentioned, incompatible. And I explain this because in Julia, it's a fairly common thing to do so, to be putting arrays and structs and expect those to be able to work on the GPU. Luckily, there's a way around this, and it's not necessarily a way around. It's just teaching CUDA.jl how it needs to convert this contained QArray to a CUDA.device array. And we do so using the adapt package. So adapt is a package that just contains a bunch of rules that explain packages like CUDA.jl how to reconstruct, how to adapt structures. So what we want to do then is, instead of myStruct, which contained a hard-coded QArray, we make our myStruct parametric, where the inner field is now of type T, and T is just any type of array. So it can be both a QArray and a CUDA.device array. And then by registering this adapt rule, which explains how to reconstruct this parametric struct after having adapted the inner field, now we can just pass our structure, which contains a QArray, to our kernel. And what we can see is that the CUDA compiler now automatically knows how to create a derived parametric struct that contains a CUDA.device vector. It's a bit of a detail, but it's interesting when you want to be able to write your own structures or create your own structures containing GPU memory. Next up, kernel programming. So you have been doing a lot like that in the past couple of days. And generally, even though array programming is really powerful and you can do a lot with it, at some point, either you want to implement a more complicated operator operation that isn't easily supported by array operations. You want to optimize something, or there's some functionality you're triggering that's GPU incompatible. All of that are valid reasons to start implementing your own kernel. And I'll briefly discuss some of the GPU-specific functionality that you can only use within a kernel, because it, in some way, maps on, for example, hardware-specific functionality. So, one of the earlier sessions, kernel function is a kernel that gets executed massively parallel. So you indicate how many threads should be launched, and every thread is going to be executing your kernel function. Threads are then grouped in blocks, and that matters because communication between threads is easier than communication between threads in different blocks. And that's why you can fetch your current thread and block number using these thread index and block index functions. Those are in fact intrinsics mapping on hardware indices that the hardware exposes. Within a block, threads are actually also grouped within warps of 32 threads, within which, again, communication is even cheaper. And you can fetch your current index in the warp by calling the lane ID function. You can query the size of the warp, which should always be 32, by calling the warp size function. So generally, if you write a kernel that's so-called embarrassingly parallel, well, where every execution of the function doesn't really which block it is in, then you can just throw all of these indices together and compute a single global index that you can use to address your array. For example, here I'm launching this kernel with 2 threads and 2 blocks, but let me try that again. Yeah, there we go. But again, as I mentioned, you don't really care about which block you're in, so you just compute a global index going from 1 to 4. Sometimes, however, you might have to synchronize between your threads because, for example, in this contrived example, I allocate an array of zeros, and then when I launch a single block, the first thread in that block is going to be responsible for initializing one element of my array, and then the other arrays are going to copy that one element to the rest of the array. And that's very contrived because in the end we just get an array with all 42s, but it does show where we need to synchronize. Because in this case, we're executing a single block of 512 threads, but that doesn't mean that all these threads are literally executing at the same time. In fact, the GPU is going to be executing warps, so groups of 32 threads, one at a time. As a result, if we want this assignment of the value 42 to be visible to all threads, we need to first synchronize, which tells the GPU that it needs to wait until all threads has reached this point in time before they can continue to perform the remainder of the kernel function. And this is called synchronization. And it's important to note here that synchronization is only possible within a block. So generally speaking, it's not possible to synchronize within different blocks. And that's important because if you've written an algorithm, as we'll do later today, that requires to communicate data between threads in a block, then you need to be configuring your kernel such that you won't be requiring synchronization between different blocks. Again, that'll become clear when we actually implement something like that. If you're doing, you can also do even more fine-grained synchronization. For example, as I mentioned, threads are executing in groups of warps. And within a warp, you can be doing very cheap communication through registers. However, sometimes you might also need to synchronize functions within a warp, and for that you can use the sync warp function. But that's a bit out of scope for this course. So there's an NVIDIA blog I linked to where warp level programming is explained. And most of the functions that are explained in here, like the sync warp function or the active mask function, if you just remove the underscores, much of them are just readily available in CUDA.jl to implement some of these more advanced communication patterns. Another interesting feature you might want to be using on the GPU are atomics. So, for example, as I mentioned, you cannot be synchronizing between different blocks. So if different blocks want to be using the same global memory, you can do so in an atomic fashion in order to make sure that the results are valid. You can also do so within a thread in order to simplify your communication. Generally, though, atomics are very expensive, and I'll demonstrate that tomorrow when we will be profiling a kernel that uses atomic operations. So you should only try to use them sparingly if possible. So here I have a accumulator again. I have 512 values being reduced by 512 threads, and they're just very naively adding into my accumulator. And in order for that result to make sense, that needs to be done in an atomic fashion. Otherwise, threads would trample over one another and the result would be invalid. And generally, you can just do something atomically by putting in. Be sure to use CUDA.atomic because Julia 1.7 now also has its own atomic macro, and both aren't currently compatible. We hope to make them compatible at some point in the future, but currently you need to prefix the use of the atomic macro by the CUDA module. Another very useful set of functions you can use on the GPU, especially when debugging or when initially implementing the kernel, are some output functions. So we have @printf, which makes it possible to print some things. And as you notice, sometimes I have to execute this kernel twice, and that's because printing happens lazily a bit after the kernel has computed. So Jupyter doesn't realize that, and as a result, the output is a bit lagging behind. So this is a traditional printf function where you have to specify a C-compatible output format. To make that a little easier, we also have a coprintln function, which is going to automatically figure out the formatting string it has to use. And now you can see I'm still on one. Yeah, it's valid. And to make it even easier, we also have this @show macro, which is very similar to the show macro in the base standard library, which you can just put around any expression and it'll preserve the expression, but it will show the result. So again, this is the output that was lagging behind. And here we have the evaluation of the expression which we have wrapped with @show. And this is very convenient when you're initially implementing something and you're not sure everything is correct, and you can use all of these macros to dump some information from the GPU to the CPU without having to actually delve into using the CUDA debugger, which is extremely low level. Again, I think even though I could focus on all the things that are possible, I think it's also valuable to show you some instances of things that may go wrong and what you need to do about them. Because especially if you're initially writing kernel code, you might assume that all of Julia is available in a GPU kernel, but that isn't the case. Crucially, we don't have access to the Julia runtime library, which is a runtime library, a small one, but still a significant runtime library implemented in C, where the garbage collector is implemented in, as well as the dynamic function invocation mechanics. So as a result, for example, by not having access to the runtime library from the GPU, you cannot be doing allocations, and you can also not be doing dynamic invocations, both of which are a common result of doing type unstable operations. So it's fairly easy when, for example, you do a typo or you call a function with the wrong arguments to get type unstable code. Especially so because Julia is a dynamic language which expects to be able to report errors at runtime rather than at compile time, whereas the GPU compiler is a static compiler. And this tension sometimes surfaces when you do something wrong and you run into potentially nasty compilation errors. So to demonstrate a couple of the common errors you might be running into, a typical one is when you're accidentally returning a value from a kernel. For example, here I have a kernel which wants to return 42, but the kernel function cannot return. So we get a nice, well, not that nice, but we get an error that the kernel function returns a value of type int64, which is invalid. The problem is that sometimes these returns aren't always as obvious. For example, here I'm throwing an exception, but then I'm returning nothing. However, nonetheless, Julia reports, or the GPU compiler reports, that we are returning a so-called object of type union, and that's the empty union. That's the bottom time, and it represents an error occurred. So if the Julia compiler notices that you're throwing an error unconditionally, it will make it so that your kernel function also returns this error value, which is currently not supported by the GPU compiler. Sometimes, however, it can be more subtle. For example, in this seemingly valid function, we also get a return type of the error value. And in order to spot what's wrong here, because this kernel seemingly looks okay, we can always have a look at the code that's being generated by the different levels of the GPU compiler. So you might know the add_code_warrant_type function, which exists in Julia, to have a look at the lowered code, annotated with nice colors and such to make it easier to debug. Well, with CUDA.jl, we have device_versions of all of these common macros. So you can do add device code warrant type to have a look at the type annotated IR generated by the Julia compiler. And this is why I'm using Julia 1.7, because this output is slightly better in Julia 1.7 than it is in Julia 1.6. And what we can see here is that, for example, the first expression of our function was still inferred properly. So the Julia compiler figured out that thread index is a named tuple with fields X, Y, and Z. However, then we have this get property, which fetches one of the properties of our named tuple, and then everything derails. Then all of a sudden, everything that's returned from the function are error constants, and this isn't inferred properly. So this teaches us that we need to have a closer look at this expression to see what's going wrong. And what we can see here is that we're using a capital X instead of a smaller case X, which is the type of error that the Julia compiler has realize you're making, and as a result it figures out that your kernel cannot ever not throw an exception. And then again, we're back in the case where your kernel function was just doing a throw unconditionally. So that's not ideal. We're working on improving this, but again,
this is also something that your editor could tell you, that it's a capital X, it should be a lowercase x.
Yes, exactly. So if you're using Visual Studio Code with a linter plugin, which I think is nowadays the default if you use the Julia language extension, then your editor is going to highlight many of these common errors. Nonetheless, it's always useful to know how to use these lower level macros to help you with figuring out what may be going wrong. And it might be rare that you're running into these issues, but nonetheless, I want to explain all of the tools that can help you debugging those kind of issues to make it less of a painful of an experience when you do happen to run into some GPU incompatible code. Sometimes it might not be that clear because, for example, if the error is in a child function and then we just look at the outer code, then we just see an invocation of the child function without any details. And normally we use the Cthulhu package for that, which makes it possible to interactively look at all of the generated code. However, nowadays there's an incompatibility between CUDA.jl and Cthulhu. So in the meantime, I'm going to explain the workaround, and that's just manually expanding the generated code of the child function. So if you have a look at the generated code of the parent function, we can see we're invoking the child function here. We're passing A, and we know the type of A. And this is just to note, you can see the conversion from CUDA-array to CUDA-array again here. So we just note this type, and then we can do a manual code one type of the child function with that type. And if we do so, then we can see the same error we've spotted before, namely that we have a thread index being successfully inferred, but then we fetch the wrong property of that named tuple. I'm going to have a quick look for questions first. It's not related to the error stuff here, so I'll just continue that first. Other errors might arise when we're invoking LLVM. For example, in this case, I have a kernel which generates invalid IR. And again, this is because the Julia compiler wants to emit dynamic IR that reports an error at runtime. However, the GPU compiler wants fully statically analyzable IR, which doesn't contain any errors. And as a result, it's failed the compilation process. However, oftentimes we do our best, the GPU compiler does its best to try and reconstruct what the dynamic error would have been. For example, in this case, it successfully detects that we're using an unsupported, an undefined name, and that makes it much easier to spot the typo. So instead of thread IDX, we've done thread ID, which results in a dynamic invocation of an unknown function. And of course, we can also still spot this issue in the device code warrant type, because if we have a look at the warrant type, we can see that the result of this call to thread ID is highlighted in red. It's of so-called type any, which means that the compiler couldn't figure out what this call would have returned, and that's because, of course, it's a non-existing function. And that kind of uncertainty in the IR is generally GPU incompatible. Another type of error you might run into is, in this case, illustrated with a array operation, so it's not necessarily restricted to using your own custom kernels, is when passing invalid data to a GPU kernel. For example, here I'm doing a broadcast over a GPU function, but I'm accidentally passing an array, and a CPU array is obviously non-GPU compatible. And then the GPU compiler prints this blob, and it tries to expand all of the fields that the fourth argument consisted of. And if you just follow the tree, all of a sudden you see .x is one of the contained values there, is of type vector in64, which is a CPU vector, and as such is GPU incompatible. So if you ever run into some of these issues, just always have a close look at which argument is GPU incompatible. Look at the last line, and oftentimes it should be clear which type of invalid object you're trying to pass to a GPU kernel. And lastly, just to show that we're doing our best to also support some of Julia's semantics in terms of runtime exceptions, so dynamic errors which aren't thrown at compile time. For example, in this case, I'm passing an array of integers to my kernel, and then I'm trying to add a floating point number which cannot be safely converted to an integer because it has this trailing .1, which would result in an inexact error on the CPU. This code compiles successfully. However, it does print a message at runtime explaining you that an exception was thrown during kernel execution. We don't provide a better stack trace on that error. Why? Because typically embedding these stack traces in GPU code hurts performance. However, it is possible to see better stack traces by restarting Julia with the -G2 flag, which is going to enable additional debug information. If we then run our kernel again, we get a very helpful stack trace, which shows us exactly which line in our kernel caused the error, and then we can quickly follow the stack trace and see that we have an invalid conversion to a N64. All right, with all of that out of the way, so I've explained how to use arrays, what the typical issues may be with arrays, how you write kernels, which intrinsics you use for that, and what the issues might be if you write your own kernel. I propose to maybe do a little exercise. It's a running example, which I'll be using in the rest of this session as well as tomorrow, to compute the root mean square deviation or root mean square error of two matrices. So let's start by allocating two matrices, a matrix A, which contains, in this case, 10 by 10 values, a matrix B, again, containing 10 by 10 values. And I propose to have a try at trying to implement both a sequence of array operations that computes the root mean square deviation of both matrices, as well as a kernel that performs the same operations. And everything that I've explained in this notebook should be sufficient for you to figure out how to implement both those, so both array operations and a kernel to perform that operation. And I propose that in 10 minutes or 15 minutes or so, we'll walk through the solution. And again, this will be a running exercise that I'll be using tomorrow to profile that code to see where the performance culprits are, how to further optimize that, and similarly with the kernel implementation to try to make it as fast as possible. Okay, I propose to have a look at my implementation at least. So to compute the root mean square deviation of two matrices with array operations, it's very easy. You just can subtract two matrices, then you do an element-wise square by 2. You compute the sum of that divided by the length of the array, and then we take the square root of the resulting scalar. So you can do so with, actually I meant to do so with CPU code first, and then we can quote unquote port this to the GPU by just uploading these arrays to GPU memory by calling the QArray constructor. And as a result, we get the exact same computation on the GPU. And to convince you that there's actually code running in the background, we can prefix this by the add device code PTX macro, which is similar to the code warrant type and the macro I showed before, but now shows the PTX code that's being generated for our GPU invocation. So, and to put this in a GPU kernel, what I've done here is I've written a RMSE kernel, which takes A and B as inputs and C as the output. Let me just mute somebody here if I can. No, I can't. Yes, let me continue. So I've written this kernel here, which takes a output container to write the result in and two input matrices between which the root medium square deviation needs to be computed. Firstly, I'm initializing the memory, which is undefined because I allocate it with the similar function. I initialize this memory on the first thread by setting it to 0 when the thread index equals 1, which is the first thread. Then I need to synchronize, as I mentioned before, because otherwise the other threads could be executing before this initialization has taken place. And now every thread is going to use this thread index to compute the difference between two values. So it takes the scalar A, the scalar B, subtracts them, squares them, and writes that atomically to the C output container. And then again, we synchronize threads to wait for all threads to have processed every element of our matrices. And we finally, on the first thread again, finalize the computation by dividing the value by the length and taking the square root. And if we then execute this kernel, we can see that we get the same result as expected. However, here I'm just using the thread index to compute which element we need to process, which means that this kernel is going to be limited to a number of threads. And now you recall the 1024 limit I looked up in the previous notebook, where this GPU apparently can only launch 1024 threads per block. And since I'm just using the length of the array here as the number of threads to use in this block, if we now start using 1024 by 1024 inputs, and again, we launch this, we get an error by CUDA, error invalid value, and CUDA doesn't help to be more specific about the error. However, we know that it's caused by the length exceeding one of the device limits. Of course, in order to fix this, what we could do is we could launch multiple blocks. So we could change our kernel that instead of using thread index, it does this typical computation of thread index plus the block index times the block dimension, which is going to be multiplying the size of the block by which block we're currently in. And as a result, we get a global index, as I mentioned before, that spans across blocks. So as I mentioned, this kernel only works in a single block. And we could extend this kernel to work across blocks by launching multiple blocks and then computing a global index. However, I don't want to do this because, as we'll notice tomorrow, this atomic addition is ridiculously expensive because, in effect, it forces every thread to wait until there is a unique time where it can, in an uncontended manner, access this global memory. And this just kills performance. The alternative is that we do it in a more fine-grained manner, where we'll have to do some communication between threads. However, as I mentioned before, it's generally tricky to do communication between threads across multiple blocks. So we want to keep this computation within a single block here. We only want to cap the number of threads to whatever value is valid for the device we're doing the computation on. And the solution that I think you've seen in a previous notebook is to introduce a so-called grid stride loop. With the grid stride loop, what we're going to do is we have our thread index, but we're not directly going to use this thread index to index our arrays. Instead, we're going to start with the thread index, but then we're going to add the block dimension to it. This is our stride. And we keep on doing this in a for loop until we hit the length of the array. And as a result, we can now just launch to 56 threads or whatever number of threads is compatible with the device we're operating on. And the loop will take care of extending the execution of this kernel until we have covered the entire array. And this, as a result, keeps the computation running within a single block, which will then make it easier to do the kind of optimizations and the kind of transformations that I want to illustrate later today and tomorrow. So now we've implemented a kernel that does the same operation, and maybe just as a sneak peek for tomorrow. So let me take the array expression and let me introduce the use benchmark tools package. Benchmark tools is a very convenient package for benchmarking. I'll explain all of these tomorrow, but let us do a small benchmark of the implementations we did with arrays. And we'll also add a benchmark of our kernel. There we go. So this performance is fairly okay. This performance is horrible. So it's not necessarily because you've fused all of your operations into a single kernel that it's necessarily going to be fast. The way you program a GPU needs to be happening very carefully. You can't just use the threads in a GPU as if they were independent threads which can do whatever. And in this case, it's the atomic whatever that's extremely expensive and really nullifies the advantages that a GPU has to offer. And we'll have to do our best actually to implement a kernel that's carefully optimized to outperform this array expressions. And we'll do that tomorrow after I've explained the profiler and how to do proper benchmarking. For now, I'm just going to focus on the implementation. And in terms of implementing these kind of kernels, as you've noticed, figuring this out is easy enough if you know how to program a GPU, but in general, this is a lot of new API surface that probably many of you aren't familiar with. And arrays are one way to make it all much easier, but there's also a couple of packages that try to make the kernel programming aspect easier. And one of those is the Tulio.jl package. And with Tulio, it's possible to write so-called index notation or Einstein notation, which is a convenient way of expressing an arbitrary index operation, which slices arrays, which performs operations on a certain dimension of the arrays, and compiles them all together into a single kernel. So I'm just going to run through it because apparently my material is taking longer than I anticipated. And the key concepts of Tulio is that if you write an expression with the @Tulio macro, if it contains a semicolon equals, it's going to create an output array. On the right-hand side, you have a bunch of input arrays that you have defined, and it's going to preserve any variable across the dimension you use on the right-hand side and you still use on the left-hand side. For example, here A is two-dimensional, so I can index A with I and j, and because I preserve I and j on the left-hand side as well, this is just going to be copying the values from the right-hand side to the left-hand side. However, if I drop one of those, for example, if I drop the second dimension's index, then we will be performing a reduction across that dimension. So in this case, we're going to reduce the second dimension, and by default, we're using the addition there. And if we drop them all together, we're going to be reducing this into a single scalar. And then, for example, we can combine this with the pipe operator to perform another function outside of the reduction. For example, in this case, I'm going to sum both directions, which should be 100, and then I'm going to apply the log 10 function, the 10th logarithmic, and then, of course, we get the expected value of 2. So these are, in essence, the necessary bits you'd need to know to implement the root mean square error of two matrices using Tulio. So we start by allocating some data again, and recall that this is the expression that we want to implement. And we can do simply by this indexing expression. So what does it do? Again, it takes every element by indexing A and B. It subtracts them and it computes the square. And then outside of the expression, outside of the reduction, we're going to be dividing the value, which is implicit by using the underscore function. We're going to be dividing it by the length of the input and then taking the square root. And this is a very, very compact representation to essentially get the same answer. And impressively so, it even runs on the GPU. We just need to be importing some necessary dependent packages. In this case, that's kernel abstractions and CUDA kernels. And then we can just use this Tulio expression with random matrices allocated on the GPU. Do note here that the result type is of type float 64, whereas on the CPU it was float 32, whereas on the CPU it was float 64. And that's because the rand function on the CPU by default generates double precision floating point values. However, because on most GPUs, double precision floating point is extremely slow, the rand function in the CUDA submodule defaults to float 32 values. However, it's always possible to specify the element type, and then we'll get the precision we expect. And then lastly, another package that's noteworthy is the kernel abstraction package, which is a package which Tulio is actually built on. With kernel abstractions, you can write your own kernels, very similar to the one I've implemented in this notebook. However, it abstracts the device-specific properties like CUDA strat index and blob index, and just makes it possible to get you an index using the @index macro. And then you can specify whether it has to be a global or a local index, whether it has to be linear or Cartesian. And you can use this value similarly as I did in one of my previous examples, then synchronization happens with the @synchronized macro. So I didn't implement the root mean square error example because the kernel abstractions currently does not support atomics. However, that doesn't necessarily matter for your use case. And the advantage of using kernel abstractions is that it's not GPU specific. So in this case, it works on the CPU. It works on the CPU, it works on the GPU, and it even also supports AMD GPUs, and Intel GPUs are going to be supported in the future as well. However, of course, the disadvantage is that kernel abstraction sticks to the common denominator of functionality that all of these platforms have to offer. And as a result, for example, atomics aren't supported currently. Another noteworthy disadvantage is that kernel abstractions is built on cassette, which is a very flexible tool, but it also heavily taxes the Julia compiler. So as a result, it might significantly slow down your application. Now, I had another exercise lined up here, but I think I'm just going to explain it right away out of time considerations. Namely, to extend the matrix root mean square error computation to a batched version. So batching is something you generally want to do often on the GPU because launching kernels and launching GPU operations is generally a fairly expensive business. So as a result, you want to group operations as much as possible. And batching is a good way to do so, because then we'll be processing a number of batches using a single kernel. Our initial CPU implementation might just look as follows, where we're not actually batching, but we're just calling our function in sequence. So we have a for loop that iterates over all of the batches 1 to 16, and then we're slicing our input arrays, computing the root mean square error, and assigning that to an output vector. Again, this is a pretty bad implementation. It's slow because it doesn't actually batch. It still launches a number of operations, but tomorrow we'll be looking into how this is a great example to show and how to optimize realistic applications, which always consists of many operations which often cannot be easily fused together. Interestingly, with Twilio, we can very easily extend our previous indexing expression to one that supports batching. And that's by just preserving our batch index in the output. So we still have our I and j iterators, but because the inputs are now three-dimensional, they include an additional dimension with the batches. We add our k index here, and that k index is then preserved in the output. So do note that I can't just use the length of A here anymore. I have to use the size of A in the first dimension times the size of A in the second dimension. Nonetheless, this still gives us a very simple extension of our previous implementation to a batched implementation. Ludovic mentions on the chat whether it wouldn't be more efficient in the simple implementation to compute the root mean square error for every thread and only make the reduction global. Yes, that would be more efficient, and that's one of the optimizations we'll be looking into tomorrow. I'm just keeping it simple for the initial implementation's sake. And now finally for this notebook, I want to extend the kernel implementation to also include batching. But that's not as straightforward because of how we were indexing our arrays. So if we recall our initial implementation, let me scroll back because I didn't copy it there. As you can see here, A and B are two-dimensional inputs. However, we're indexing A and B with a linear index, which is just the current thread index. And that's not a big problem because it's possible in Julia to index a n-dimensional container with a single linear index. However, if we want to add the batch to the mix, then we cannot just do I, k, because now we'd be indexing a 3-dimensional container with a 2-dimensional index, and this doesn't make sense anymore. So in order to extend our kernel to work across the batch dimension, first of all, we want to be launching a number of blocks, and each block will be processing one batch of arrays. And this is why I wanted to keep this implementation local within a single block, because I knew I wanted to be able to just scale the implementation across multiple blocks, where every block is going to be processing one batch. Of course, then within that block, we still need a way to fix our indexing. And a simple way to do so, it's fairly hacky, but it's a good start, is to reshape our 2-dimensional inputs, A and B, and as it were, flatten the first 2 dimensions. So it's 1024 by 1024 by n. We're going to flatten that into 1024 multiplied by 1024, and then the second dimension is going to be the batch number. Let's do so. And this just lets us easily adapt our initial implementation, where we can now pass the n, the number of batches, as the number of blocks. Within the kernel, we then look up the batch number, and now we can do I, batch across our kernel, which is otherwise completely unmodified. However, as you may realize, this is not very nice, and it's also not very generic, because this relies on the fact that we can flatten our input arrays, which may obviously not be the case if we're dealing with a more complicated operation we want to implement. And that's why I want to demonstrate a much more general way of doing this, relying on one of Julia's more impressively designed features, namely Cartesian indices. So a Cartesian index is an index that represents how to index a container across all of its dimensions. For example, we have 111, 211, and all of these are Cartesian indices that can be used to index a container. So in the case of our input arrays, we can actually look up each indices of A, and then we indices of axis A. Then we can get, see, these are all the indices that we should be using if we want to be indexing our 3-dimensional input array. So it goes from 111 to 1024 by 1024 by 16, which is the amount of batches we want to be processing. Now, what's neat about this, and this is all explained in this blog post, so if you're interested in this, I would generally recommend you to have a look at this. It's possible to split the indexing domain into separate Cartesian indices. For example, here, we know that our main array only spans the first 2 dimensions, and it goes from 11 to 1024 by 1024. And then our batches go over across the 3rd dimension from 1 to 16. And using these expressions, it's just simply, well, I'm not going to explain them out of brevity, but we simply are splitting the entire range of the Cartesian indices into a subset that goes from 111 until 1024, 1024, 1. So it keeps the batch index at 1. And then we have a second group of Cartesian indices that goes from 111 to 1116. So essentially, it's only dealing with the batch index. And why is this useful? Well, this is useful because we can pass these to a kernel, and then we can index these groups of Cartesian indices with our hardware index. For example, if we take this group of indices going from 111 to 1116, this is called our badge, and we pass this to the kernel as our badge. Then we can index our badge with the badge number, giving us an iterator that goes from 111 to 1116, depending on which block we're currently in. And we can do the same for our main iteration domain. So we're passing our main, which again goes from 11 to 1024, 1024, and we can index using our grid stripe index. And then we fuse together both these indices using the max operator, yielding an index that we can effectively use with our containers. And this should take a while to understand how this works, but in effect, it makes it possible to write fully generic kernels that can be passed arbitrary arbitrary containers. In this case, treating the last dimension as the badge index. For example, I can illustrate here by invoking this function with a 10, 10, 10, 10, n badges. So it's now a 4-dimensional main iteration space and 1 badge dimension still, and our kernel still works properly. And this is a very, very powerful way of indexing arbitrary containers in a way that's fully general and agnostic to the exact dimensionality we use. Nonetheless, still making it possible to specialize the treatment of some dimensions based on, for example, how the GPU works or where we can efficiently communicate. And this is also a pattern that we use to implement, for example, the map reduction kernels, which also needs to treat some dimensions specially because it needs to reduce across some dimensions and it needs to preserve other dimensions. So as such, this is a very interesting and very powerful programming pattern that is strictly very easily usable with GPUs as well. So I recommend if you're often dealing with higher dimensional data and you need a general way to write code that works, in some cases even across the GPU and the CPU with higher dimensionality containers, I recommend you give the blog post I linked in the notebook a read so that you can use this technique as well in your kernels without having to hard code for the dimensions you're currently working with. So this was a fairly advanced example. Don't expect to be using this on a daily basis, but nonetheless, it's a very powerful pattern that might be very handy. This is the end of this course. I propose we have a short break now, and then I'll continue with 2 more shorter detailed sections, one on memory management, and then finally one on concurrent computing, where I illustrate how to use tasks and such for more efficiently using the GPU. All right, let's continue. The third notebook I have prepared is on memory management, which again is a little bit lower level, but I prepared this because people might be coming over from C or C++, where they might expect to have these lower level management tools when porting code to Julia. So again, starting out by activating the environment, and now because I've explained it in the previous session, I'm always going to disable scalar indexing, not to trip up some performance, some hidden performance problems because of that. So CUDA.jl has some expected functions to query the total amount of memory there's available, the available memory. And then there's, again, a whole lower level interface for you to allocate memory with. But for most people, they shouldn't be required to use this because the array constructor you've seen me demonstrate in the previous session does all this allocation for you. So when you allocate a QArray, when you instantiate a QArray, it's going to decide how much memory to use and how to allocate that memory. Nonetheless, I want to explain some of the lower level bits because they may be valuable depending on how your application works. Because the GPU has multiple types of memory you can allocate. You can, and the basic memory that CUDA allocates is so-called device memory, which is memory that's allocated on a single GPU and it's only usable by a single GPU by default. But there's also something called unified memory, and unified memory is memory that's accessible from any processor in the system. It be the CPU, the GPU, or another GPU. However, depending on how those are interconnected, those accesses might then be slow or fast. There's also host memory, which is memory that's always located on the CPU, but can be made accessible to the GPU. And that's useful when you want the GPU to occasionally let the CPU know about something. And then finally, there's also array memory, which is opaque and essentially only used for textures. So to allocate all of these individual forms of memory, you need to use the lower level interface that CUDA.jl offers. And that's hidden in the mem sub-module. And there's a convenient function in there. There's the alloc function, so you can do mem.alloc, and that gives you pass the type of buffer you want, for example, a mem.device buffer, the size, the amount of bytes you want, and then you get a buffer. You can do the same with unified memory and with host memory. But these aren't arrays. These are just strictly buffers with no functionality whatsoever tied to them. And in order to use them on the GPU or the CPU, we need to convert them to a pointer. For example, our device buffer, we can convert to a CU pointer, which is the GPU-specific pointer I talked about. However, conversion of a device buffer to a pointer is illegal because we cannot read the device buffer from the CPU. In contrast, a unified buffer can be converted to both a CU pointer and a regular pointer. And you can see it actually has the same value, but this depends on your system characteristics. And finally, a host buffer can be converted to a CPU pointer. And if you've allocated it by passing the host alloc device map flag, which is going to tell CUDA that this CPU buffer also has to be mapped to the device. If you did that, then it's also possible to convert it to a CU pointer. And then once you have these pointers, you can continue and use those pointers to wrap an array around them so that you can do something usable with these buffers, because at this point, there's still buffers and pointers, but there's no functionality tied to them. Wrapping an array around the pointer is done using the unsafe wrap function. So you call unsafe wrap, you pass the type of array you want the pointer you're wrapping around. It's going to derive the element type from the element type of the pointer, and then the number of elements. And then all of a sudden we get a unified array as represented by a CPU vector. And let's take the same pointer. So this is a unified pointer pointing to a unified buffer, which is accessible from both the CPU and the GPU, which means we can take the CU pointer we derived from the unified buffer and wrap a CU array around it. And now watch what happens if I modify it on the CPU side. It's also modified on the GPU side. So this illustrates how unified memory works. And this can be convenient if you're working in a system where interoperability between the CPU and the GPU is a necessity, or when you want to be using multiple GPUs in a single node. Because again, if you're just allocating a plain CU array, that will be device memory, and you cannot access device memory from the CPU, and you generally also cannot access device memory from one GPU on another GPU. However, by doing these allocations ourselves, we've opted out of CU array managing its memory, which means that we need to free it manually when we're done using it. And this, of course, is one of the advantages that using the CU array type gives you, is that it will automatically manage all that memory for you. People who have been, there's a question from Ludovic, are operations on unified memory significantly slower? Nowadays, that has been carefully optimized, and especially if you have recent modern hardware, its memory management units actually support page faults when you access unavailable CPU memory from the GPU or vice versa. So unified memory was introduced back in the day when there wasn't such hardware support, which resulted in it being significantly slower. Nowadays, performance is much better. And in some cases, it can even outperform pure device memory, because with device memory, you're copying memory to the device, and then you're running the kernel. Whereas with unified memory, you're just keeping the memory on the CPU, and then you're launching the kernel, and it will copy memory to the GPU whenever it's needed. And in that way, you can get a staggered execution, which might even be, in some cases, faster. So people who have been using CUDA.jl for a while know that we used to have something called memory pools implemented in CUDA.jl itself. And this was to cope with the fact that memory operations were synchronizing, meaning that if you had a bunch of GPU kernels executing, but then you needed to do a free or an allocation, you actually needed to wait until the GPU finished execution, which was horribly ineffective. Nowadays, CUDA has something called a stream-ordered allocator, which makes it possible to order these memory operations according to a stream, which is very useful to garbage collected languages like Julia, which may result in freeing memory at quote-unquote random places, because the GC can kick in at every time. And when it used to do that, it caused your application to synchronize and lose a lot of performance potentially. So the stream-ordered allocator is very, very useful. And as such, I can recommend using it. And it's done so automatically as soon as you use CUDA 11.2. And I've seen that that's the case on the cluster. But on older systems, this is where CUDA.jl's automatic binary dependency management is very useful, because it may automatically upgrade the driver from an older version that doesn't support stream-ordered allocations to a newer version. Nonetheless, your device also has to support it, and older devices may not. So in this case, my device does support memory pools, which is great. It's still always possible to use the old allocator. And it does so when you pass the async equals false flag to memallocc. And if you want the entire CUDA.jl managed allocations to not be using the memory pool, you do so by setting the Julia CUDA memory pool environment variable to none before importing CUDA.jl. Again, this variable used to exist in the past, and you could set it to bin, split, and a couple of other values. All that is doesn't exist anymore. So, and if you're using the memory pool, you can also use it to inspect some of its properties. For example, there's a function used memory, which will tell you how much memory is actively being used from the pool. There's cached memory, which shows you how much the pool is holding on to. Both of these can be neatly shown by calling the memory status function. So which shows you the effective GPU memory usage, which means the card in your system, how much memory is in use. And then the memory pool that you're using, how much of that are effectively live allocations and how much have just been reserved. Typically, as soon as an allocation is freed, CUDA will also get rid of the reserved memory as soon as you synchronize. In some cases, some applications might very often release all of their memory, but expect it to be able to release it. And for those, it might be interesting to set a so-called release threshold. If you set this to a number of bytes, then CUDA will always hold on to that number of bytes, which again might speed up your application if you often release all of your memory and then allocate it again, because in that case, it will just be able to use the reserve instead of having to allocate it from scratch again. But again, all that isn't as relevant to most of you, because you can just use the array abstraction straight away. So by just doing using the QA constructor, for example, here I'm instantiating a Q array of integers. It's undefined and it should be one element large, and it will automatically contain a device buffer. So that's why I mentioned Q arrays by default will be using device memory. And we can see we can actually extract the pointer of that Q array by using the pointer function, and very similarly we get the pointer that the contained buffer points to. And nowadays, it's also actually possible to allocate unified memory using QArray by just specifying the type of buffer you want as the type parameter. So here, as you can see, this QArray has 3 type parameters. It's the element type, it's the number of dimensions, and then there's the type of the buffer. So if we call the constructor where the buffer type has been specified, again, with an undefined, it should be undefined and it should be 1 element large. Now we get a unified buffer. And this is a much more convenient way of allocating unified memory because it still does all of the automatic management for you. So as soon as this QArray goes out of scope, that unified buffer will be freed and you won't have to manage that memory manually. Page locked memory is what I mentioned before. If you have host memory that's accessible to the GPU, you can do that by calling the pin function. And the pin function, well, it's actually not going to map into, but it's going to pin the memory, more on that later, which makes it page locked and will make a couple of memory operations much faster. And you can do so by calling the pin function on a CPU array. Now, any of you who have written a realistic Julia GPU application might have run into the fact that because of Julia using a garbage collector, it's possible that you run into out-of-memory situations because memory isn't freed as eagerly as it would have been if you manually managed memory in, say, CUDA.c. You have to wait until the garbage collector comes along, scans the entire heap, and releases all of the memory that it knows is unused. And this may be problematic because GPUs typically have not as much memory as your system has. It's in the orders of tens of gigabytes if you're dealing with very high-end GPUs, whereas your system may have hundreds of gigabytes. So in the awaiting compiler improvements, which we're working on, so the Julia compiler will in the future be able to early free memory itself without having to wait on the garbage collector. So awaiting that, you can actually early free memory. For example, if we have a temporary allocation, which we need to use in our function as workspace or work area memory or buffer or I don't know what. And you know that this memory is now, can be released again. You can early free it by calling the unsafe free function. Now this is an unsafe function because whereas if the allocation would only be collected by the garbage collector when it went out of scope, in this case, the object is still in scope, which means that after freeing that object, you could still use it. And this would result into errors, maybe fatal errors in your application, making it crash. So that's why it's an unsafe call. And you can work around this, or at least you can keep everything safe by just making sure that this object is also unreachable after you call the unsafe free function. So again, this is a typical pattern where you may want to do this, defining a library function where you have some work area that's similar to the input array. You perform your expensive operation that requires some work area, and then you unsafe free the work area before returning the result. So I mentioned unified memory already briefly, so let's demonstrate it a little better because this is a useful type of memory. I mentioned that you can allocate it by setting the buffer type as a type parameter. There's another experimental interface, namely the CU function, which you may have heard of. Me myself don't like it very much, but people seem fond of the function. It's a function that automatically converts all kinds of CPU objects to GPU objects. It does so recursively, and it also does so in an opinionated manner. For example, if it encounters an array of float 64s, it will automatically downcast it to an array of float 32s because those typically work faster on the GPU. That's also the reason why I don't particularly like this function. But especially in the machine learning community, people are always using this CU function. And that's why it also gained a unified equals true keyword argument, which you can then use to convert any CPU buffer to a unified memory on the GPU. And this is, again, as I mentioned, very useful when doing multi-GPU computation. For example, here, if my current tasks is on device 0, I allocate some memory, then I switch devices, but after switching devices, I cannot use the stamp allocation because this allocation is bound to the first, to device 0. Whereas CUDA.jl is not going to detect this right now. So we're working towards arrays to know where they were allocated on, kind of provenance. But nowadays, it's not the case. So if you were to execute this code and use stamp on device 1, you would get illegal memory accesses. Unified memory solves that. So if you just use some unified memory, then we can use it on device 0, where, for example, I'm setting adding 21 to every element of the array, and then on the second device, I'm multiplying by 2. Note that, of course, I do need to synchronize after each of these computations. And finally, I can expect the value of 42 in my unified array. And because it's unified, it's even possible to access that memory on the GPU. So we can do so by taking the pointer of our unified array, reinterpreting it as a CPU pointer, wrapping an array around it, and then we can directly read the value of 42 out of this array. And this is much faster than copying it first to the CPU, because here we're just going to read our memory whenever we need it from the GPU directly, without having to allocate memory, without having to copy beforehand the entire array. This may be an interesting pattern to optimize some kernels or some operations where you need to transpose limited amounts of data from the GPU to the CPU. Another thing I mentioned earlier on was pinned memory. Pinned memory is CUDA's term for page-locked memory. So when you allocate memory on the CPU, that memory is managed by the operating system, and the operating system is free to page out that memory to disk, for example, when there's lots of memory pressure on your system, or when you're haven't used that memory in quite a while. That's a problem for asynchronous operations. So asynchronous operations, as most GPU operations are, is an operation that when you queue it from the CPU returns immediately, and it just keeps on running in the background on the GPU. And that's very convenient because you can then queue a lot of operations one after another on the CPU and expect the GPU to just be tugging along in the background. But with non-page locked memory, that's impossible because the memory may be paged out at any point. So the CPU has to essentially perform a blocking copy of that memory from the CPU to the GPU. As you can see here, this is a screenshot of the profiler, and we'll be working much more with the profiler tomorrow. You can see that this is the trace on the CPU, and this block is very large, which means that a lot of time is being spent blocking on the CPU, whereas it's maybe 80% or 70% of the time that the GPU is spending the copy asynchronously in the background. Which means that potentially there's lots of time being lost here if you wanted to do something more efficient on the CPU, sorry. There's a way to fix this, and that's to pin memory by calling the mem.pin function on a CPU array. The CUDA driver is going to make sure that that memory cannot be unpaged anymore, and as such, it's possible to perform this memory copy asynchronously then. We can see here in the profiler trace that now the memory copy, the red block, it's a second red block here, is instantaneous. And that doesn't mean that the operation completes instantaneous, but it does mean that the CPU is free to do whatever after it has enqueued all of these operations. And this will be very important when doing concurrent GPU computing, as I'll explain in the next notebook. It also makes possible to do the copies slightly faster, because previously we first needed to copy to a staging buffer on the CPU before we could copy from that staging buffer to the GPU. Whereas by avoiding that copy, we can copy directly to the GPU. So your copies may even be significantly faster. However, as I mentioned here, there's no free lunch. Pinning is expensive. So that's the reason CUDA.jl doesn't do it for you. You cannot just be pinning all of the arrays before every memory copy. Your application needs to manage the memory buffers it wants to pin intelligently beforehand, which typically is doable with HPC applications, but it's not as easy when you have a very ad hoc application where you just took some existing code and threw a array at it. With HPC applications, it's interesting to consider pinning some buffers you'll be using to copy back data to the CPU. So the last memory type I want to discuss is the array memory type, which is actually a bit of a misnomer because it's essentially only used for texture memory. So texture memory is fairly limited, but it can be used for, it has two advantages essentially. One advantage is that the GPUs, because they were originally graphics processing units, have a hardware accelerated filtering functional units, which makes it possible to do hardware accelerated interpolation between values. If your application requires that, it might be interesting to use texture memory. For example, one neat demonstration I'll do is where if you had an array, for example, our 1024 by 1024 array, you can index that array using floating point indices, and it will automatically, in a hardware accelerated manner, interpolate between, for example, the nearest neighbor or the nearest couple of neighbors across both dimensions. Another advantage of texture memory is that the array type is an opaque allocation, an opaque buffer type, where the rows of the data will be padded in a way that the reads can be done in a conflict-free manner. This is fairly specific, but it means that threads can, with less contention, read from the data that's stored in a texture. And to illustrate that, let's actually use some realistic textures. So I'm importing the images package here to get some image instruction and the test images to get this nice typical picture of a lighthouse. CUDA.jl only supports plain plain element types for each channel, so it doesn't support the RGBA of a fixed point integer as is used by the images package by default. So let's interpret our image to a simple 4-channel 8-bit integer. Next, in order to use this on the GPU, we need to create a texture object, and that texture object can either be backed by a texture array, which is the opaque array type I mentioned that has each of the rows padded to avoid bank conflicts when reading memory. So that's what we're going to do though. We're going to create a texture array from our image, and then we're going to create a texture that's bound to that texture array. I'm also passing the flag normalized coordinates equals true here, which means that we want to, or we will want to index our texture from 0 to 1. That's just to demonstrate that functionality, and because it's convenient, because I'm multiplying by the sign here to create a warping effect. So now I've written a kernel. It's a fairly simple kernel. It just looks up a global index. And again, looks up the Cartesian indices of our destination array. And based on that, it's going to take both components of this two-dimensional Cartesian index, so the row and the column. It's going to divide it by the size in order to get an index between 0 and 1. And then it's going to multiply that index by a sign to get a warping effect. Let's execute that. No, that's just a kernel definition. This is how to execute it. And there we see the warping effect. So what's interesting here is that the amount of warping is completely defined by the size of the destination. If we change this to 200 by 300, we get a completely different warping, because by the way we use our destination indices and we scale it from the range 200, 300 to 0, 1, and then we can use those normalized 0, 1 coordinates with our input without having to think about the size of the input. All of the interpolation happens automatically, and this is a nice use case of normalized coordinates where we can just discard all of the input sizes by using the normalized 0 to 1 range. So by default, let me first scale up this again to the original side so you can see the differences I'm going to illustrate now. When you create a texture object, you can also determine the addressing mode. And the addressing mode is what happens when we go out of bounds. So here, because we're warping, at some point we go out of bounds. And by default, it's going to clamp the latest pixels it could have read, but we can also use the so-called border mode when we'll just be using a white value of 1 for the output. Now we can clearly see where we went out of bounds. And there's some other interpolations mode. There's mirror, there's clamp, there's there's a couple of other ones. Oh yeah, there's a link here. Wrap to wrap around, clamp to the edge, which is the default, mirror to go back in the other direction, and then border, which is the one I demonstrated here. CUDA also only supports a limited number of interpolations, nearest neighbor and linear, I think. And we've extended that in CUDA.jl by a couple of additional interpolations modes. And the most interesting one is bicubic interpolation. So let's use that by just setting this keyword argument to the texture object. Bicubic interpolation, doesn't support normalized coordinates, so I'm not setting the normalized coordinates flag now anymore. And as you can see, instead, we need to be multiplying by the size of the input texture here to scale up from the 0, 1 range to the 1, 2 size of the input array. Otherwise, there's no difference between normalized and non-normalized coordinates. So let's launch this kernel again. And as you can see, it's much it's fuzzier. So if you see the borders here are very aliased and harsh, the borders here are blurred because of using this cubic interpolation. And this cubic interpolation mode, even though it's not supported by the hardware, it builds itself on top of the hardware accelerated linear interpolation mode. So in that sense, it's still fairly fast and hardware accelerated, even though it has to perform more reads that by themselves aren't hardware accelerated. The last piece I want to highlight is some more advanced memory copying. So by default, if you just call array on a QArray or QArray or on an array, there's several functions involved. So first we call the copy_to function, which is going to perform some bounce checks. And then it's going to call unsafe copy_to, copying the array data and metadata, because we also support union arrays, which are arrays that may contain element types of different type. So it has to copy both the data and the metadata, which is then going to call the unsafe copy_to function that works on raw pointers, where the actual memory copy happens. So as I mentioned, array buffers are already padded, where you have some padding in order to make sure that the image rows don't result in bank conflicts. And there's actually in CUDA C also a way to use these with regular allocations. However, this is currently not supported by CUDA.jl because the speedups we've seen aren't that significant. Nonetheless, you can use the two-dimensional and three-dimensional copy function that underpins this strided array to perform some more advanced copies. Notably, for example, if you have, in this case, an array of zeros and you want to set a range within that matrix, you can actually use a strided two-dimensional memory copy where you can specify the start of the destination position as well as the stride of every row. And this is, in this case, convenient to blitz this matrix of ones that's smaller than the input to the middle of the matrix without having to require a bunch of individual memory copies. So if we wanted to do this in a naive way, we shouldn't need to do a bunch of copies again, which would probably be slow if we're dealing with real-life data. So as an alternative, and I think this is also used by some of the software that's actually being developed and run on the CSCS supercomputer, this can be used to have seriously optimize those kinds of two-dimensional memory copies. And a similar function also exists for three-dimensional memory copies. That's it for memory management, I think. I'm going to take a 5-minute break to let my voice rest a little. If there's any questions about this material, don't hesitate to ask them on the Slack channel, either today, tomorrow, or anytime in between. And then we'll finish off in 5 minutes with a part on concurrent GPU computing. Okay, let's continue with the last notebook for today. This notebook I have prepared is on concurrent GPU computing, which is a fairly recent addition to the CUDA.jl programming stack, but nonetheless, I think is going to be very important in the future when GPUs are becoming more capable and it's becoming more difficult to max out the capabilities of modern GPUs. So before that, a short introduction to concurrent computing. So concurrent computing is when on a single thread of execution, you still have multiple tasks concurrently execute. And this works because some applications, some operations are blocking. In this example, I have a print statement, then a sleep function, and then another print statement. And of course, when we're actually waiting on the sleep function to complete, why couldn't we be executing something else? And this is exactly what concurrent computing does. In Julia, that's done using tasks. So by putting functionality, operations, expressions in tasks, you express that these are in a way independent and the scheduler can move from one task to another when one hits a blocking point or so-called yield point. So here we have two tasks. Again, one does some printing and sleeping, the other does some printing, and then we wrap all that in an at-sync expression, which makes us wait on both tasks to finish. As you can see in the output, we start with task 1, then we switch to task 2, and ultimately we switch back to task 1, and then the at-sync block finishes. And this works because, as I mentioned, we had a yield point. The way sleep is implemented is, in effect, we take the current time, and then while we haven't waited long enough, we call the yield function. This is basically what the sleep function does, leaving some complications out of scope now. And of course, all this applies very well to GPU computing because oftentimes the CPU has to wait for the GPU to finish. And currently, Many GPU operations are actually asynchronous already to make it possible, as I mentioned before, to queue up multiple operations at a time and not having to wait on the GPU to finish. For example, if I call a kernel function in a loop that in this case goes to 1 from 10, and that's the way it is, if kernel launches are asynchronous, then the time spent on the CPU launching the function, which is the block here, is shorter than the time it takes to complete on the GPU, which means that we can queue up all our function in very close subsection before then having to wait on the GPU to finish. And the result of that is that the GPU is also a very, the GPU's timeline is also very dense, meaning there's no gaps between the individual kernel invocations. Whereas if GPU's operations were synchronous, meaning the CPU would have to wait until the GPU finishes, then subsequently the next kernel couldn't start immediately after, but would have to wait first until the CPU would have queued up some additional work. And as you can see here, that causes some blanks in the profiler trace. We call that a sparse trace. And as a result, the total iteration also takes a significantly longer than the operation where all of the launches were asynchronous. Nonetheless, even though many of these operations are already asynchronous, some operations are still synchronizing. And the most obvious one is, of course, when you call the synchronize function. When you call the synchronize function, the CPU will have to block and wait on the GPU to finish. And typically, the synchronize function in CUDA-C, or just in the CUDA library for that matter, is a blocking call. When you call that function, it's going to block in libCUDA, which isn't great because if it's actually blocking, then we cannot use that time to switch to another task in Julia land. So we've re-implemented the synchronize function recently to make it so that it blocks similarly like the sleep function does. It checks whether the GPU is done, and if it isn't, it yields. And the result of that is that if you're computing something expensive, here, for example, a large matrix multiplication, when we're waiting for results, it didn't switch actually now. Now it is. If we're waiting for results, it can switch to another task to perform some other operations. And that's useful, and that's concurrent computing applied to GPU operations. However, there's some pitfalls. Namely, that the way so the first pitfall is that some operations are still blocking. And the most important one is what I mentioned in my previous notebook, copying memory from or to the CPU involves spinning and blocking on the CPU side if that memory wasn't page locked or pinned. And this is the same screenshot I showed before. So the CPU blocks the most of the time of the copy. And during that time, it's not possible to switch to other tasks. And that's, of course, a very good motivation to pin memory again, because then we have much more time on the CPU available to call into other tasks. So now what do we do with all that new free time on the CPU? Well, one opportunity would be to overlap CPU operations with GPU operations. For example, we could have some CPU task that does some sorting, and on the same time, we have some GPU task performing this matrix multiplication from before. However, if I were to execute this, this doesn't actually, and is never going to multitask between the CPU and the GPU task. And that's because the GPU task, which just does some sorting, does not include a yield point. It doesn't do any blocking operation, it just does raw compute, which means that there's no opportunity for the CPU to start its work. And so you need to think about which CPU work you want to overlap or you want to multitask with GPU operations. If it's just pure compute, then it probably won't work unless you insert a manual yield point. This is something, it's a bit of a hack, but you could do it. And then you can see that we go from CPU task begin to GPU task begin. We actually interleave execution of the CPU and the GPU task, but that's a bit of a workaround. A better solution is to pick applications that are blocking in some way, and typical operations that are blocking on the CPU side are, for example, input-output operations, file system operations, printing, but also synchronization primitives like locks and conditions, channels, and so on. So just to show you how all of this works, and this ties into the very first notebook I started this day with, it's all of the task local state, because we have a different stream object between every task. So this is the main task, this is a newly created task. As you can see, the streams are different. Similarly, this different stream object is then also used by kublas. For example, here I am calling the kublas get stream function, which is going to inspect our kublas handle to show which stream this handle was configured for. And again, if we do this on the main tasks or on the asynchronously created task, we can see the kublas library is using a different handle. So in that sense, all of our operations with the GPUs and with libraries are decoupled between tasks because they are using different streams automatically. And all of this is stored in the so-called task local state. So you can inspect this by calling the, what am I doing wrong? Task local storage, sorry. So if we call the task local storage function, you can see there's a dictionary of values for kublas handles, which stream they were configured with. And there's also some task local CUDA state containing all of the contexts for the current device. This has some pitfalls though, and this is why this change was breaking. This was introduced with CUDA.jl 3.0, namely that the obvious result is that every GPU operation is now task local, which means that, for example, if you allocate some data and you perform a expensive operation, and then you call the synchronize function, but you call the synchronize function on the wrong task, then our stream isn't actually done on the main task, which means you need to take care where to synchronize. There is an obvious workaround, and that's the device synchronize function. The device synchronization function is as a function, as the name tells you, going to synchronize the entire device, but that's a very coarse workaround because it essentially blocks progress for all tasks until the device has fully finished. The real solution is that you synchronize in the correct task. So we shouldn't be synchronizing within this function. We should be synchronizing where we've produced the data and where we are using the same stream. Another example here is I'm allocating A and B on my main task, and then I'm doing a multiplication of those in a newly created tasks. And if I do this a couple of times, we should see corruption. Yeah, there we go. So corruption in that the results are wrong. And the easy way, again, is not to do device synchronization anywhere. The solution is also not to synchronize in this task, because here we would be synchronizing the stream of the newly created task. We need to be synchronizing where we produce the data. So in this case, we put a synchronization after where we've allocated the data. And this should always yield the correct results. So there's also note that there's not much of a difference between calling the CUDA.addSync macro and the synchronize function, but the advantage of CUDA.addSync is that it returns the result, whereas if you use a synchronize function, you first need to assign the temporary and return it afterwards. If you want more fine-grained ordering, you can use events, as I tried to show in my first notebook, but failed to do so. However, it should work here, where we create two events, one event that indicates when the input is ready, one event that indicates when the output is ready. And then on the main task, we can allocate data, signify that the input is ready. But again, this is asynchronous. This is just going to queue that operation on the stream. And then within the newly created task, we can have that newly created tasks stream wait on the input ready event, perform the multiplication, then signify that the output is ready. Again, this is asynchronous. The output isn't ready when this function is evaluated. It's only so when the multiplication is actually done. And then on the main task, we can have the CPU block on the output ready event by calling the synchronize function. And this is, in fact, better than calling the synchronize function, because with the synchronize function, we're unconditionally waiting for the stream to finish, while with this, we can express very fine-grained dependencies without having to wait for the entire stream to finish. So the most interesting use case for all this is, as I mentioned, to overlap GPU operations. Because modern GPUs are so powerful, it's realistic that any kernel you write is not going to be using 100% of the capabilities of the GPU. Similarly, your CPU side might also not be perfect in that you might have some time spent on the CPU, some overhead where you could have been doing work on the GPU. And to cope with those two inefficiencies, you can overlap independent GPU operations by launching them from different tasks. Because of doing so, those operations will be queued on separate streams and the GPU will be able to overlap them. You will be able to execute them concurrently, in parallel, when you're not using all of the GPU's resources. So for example, here, in this example, I'm doing a multiplication that uses CUDA. Then I'm using a broadcast, and finally I synchronize my task, and I'm calling this compute function on some dummy data on two tasks. And what you can see here is that in this green segment, this is where all of the operations are queued on the CPU. And even the matrix multiplication, which you expect to be a very well-optimized, heavyweight function, is executed in an overlapping fashion. Again, then it's overlapping with the broadcast from the first task and so on and so forth. So even with these very optimized cuBLAS kernels, it's possible to squeeze some more performance out of the GPU by having independent work execute on different tasks so that the GPU can overlap them. And especially with HPC applications, it might be possible to put separate tasks that need to be executing in separate tasks and separate Julia tasks and have everything work automatically out of the box. Again, this is assuming that you manage to avoid any blocking that might still be happening, for example, when doing memory copies to or from unpinned memory. So we can try to apply that to our batched root mean square operation. So recall that this was the original, of course, inefficient implementation, but nonetheless, to illustrate how we would perform these operations, each of which are in effect independent because every batch does not influence any other batch. We can simply launch this on separate tasks by adding the @async in front of the function call, and then at the end, fetching all of the results that the tasks produced. Am I doing so? So as you can see, the root mean square errors array is not going to be containing scalars anymore. It's going to be containing tasks object, which I can then fetch at the end, and we get the same result. The only thing different is the element type, but that's because I made a typo here. This should be L type. Actually, this could just, this should be L type A. There we go. And even though this doesn't really speed up our application because we're doing a very fine-grained operation, only a couple of kernel launches concurrently. Nonetheless, if we zoom in the profiler, which again I'll explain tomorrow in greater detail, we can see that some of these executions managed to overlap on my GPU. Another interesting application for this concurrent computing for using tasks is, again, because every task having its own task local settings, you can use different devices in each task. By just switching to a device at the beginning of a task, all of the operations in that task will be using that device. Even if in the meantime the Julia scheduler switches from one task to another, CUDA.jl will then automatically call the necessary CUDA API functions to actually switch devices. And when you switch tasks back, it will do the reverse. So if we execute this and we put it under the profiler, you could see that we're using our different devices at the same time. So this is a very convenient way to do multi-processing, especially combined with the unified memory that we've recently added. This makes it possible to do single node multi-GPU computations fairly easily. There's one pitfall, though, namely that you should always explicitly set the device at the beginning of a task, because otherwise it's undefined which device that task will be using. And the technical reason for that is that Julia currently doesn't have a feature to inherit values from the parent task. Once we get that, we will have a more straightforward behavior. So just to be safe in the meantime, just pick the device you want to work with at the beginning of any task. You only need to do so if you ever switch devices, but if you do so, please be explicit at the start of every task. And finally, we can also extend this to multi-threading. So with Julia 1.3, we've gained the threads.addSpawn macro, which mostly can be used in place of the addAsync macro. But as a result, we'll get multiple threads performing the work on these tasks. And here we can see in the profiler that, again, we're still using our GPUs in parallel, but that's being done so by separate threads. We have our master thread over here that doesn't perform any API calls. Then we have two threads which are performing API calls to work with the device. Thread safety is a work in progress. I'm going to be honest here. If you run this on a realistic application, you might run into crashes, but please report them. In the meantime, this may still be useful when you have to be calling blocking operations, because, for example, if you can't pin your memory and if you're always doing blocking memory copies, that's not of an issue if you're using multiple threads, because in that case, we just block a single thread and the other thread would still be able to do meaningful work. So dependent on your application, multi-threading might be useful or not. That's it for my material for today. Before I close off, I had some notes for tomorrow. Namely that tomorrow we'll be using the profiler. However, the profiler currently isn't packaged by any Julia package, so you need to download the profiler in order to use its user interface on your local system. And you can do so by browsing to this web page on the NVIDIA website. However, you need to be logged in to be able to download these files. If I open this in private session, you'll see I will be able to browse to this site, but then I won't be able to download any file. You need to register for an account. Of course, registering a developer account is just free. It's easily done. So please do so so that you have a working installation of the Insight Systems profiler for use tomorrow. On the server side, you will be able, so I already have Insight Systems unpacked in a Scratch folder of mine, which, if I understand correctly, you all should be able to use. So please verify if this works. If it doesn't, let me know on Slack. Then we'll figure out a way for you to have Insight systems on the cluster by tomorrow. That's it for me today. I'll be staying around online on Slack for a little while. So if there's any questions concerning any of the material today, please let me know, and I'll do my best to answer them. Also, tomorrow I only have 2 bits of material, which I assume is not going to cover 4 hours. So if any of you are more interested in any of this or want to see a demo of something specific, let me know. That maybe we can use the final hour or so to discuss some user-related questions or interest during this course. Thank you all. I'll see you tomorrow. Samuel, if you want to say something, now's the time.
No, I don't think I have anything to say anymore. Just thank you very much for this awesome, incredibly vast material. I think there's a lot to digest now. So yeah, see you tomorrow. Thanks for being here tonight, today. All right, so let's get started. So welcome to the last day of the course GPU Programming with Julia. I have only 2 things to say, and then we'll pass over to Tim. I'm sure that also today he has some exciting materials yesterday. So the first thing, I uploaded yesterday the solutions from day 2 for those who didn't see it yet. And second, please use again the reservation Julia when you create the Jupyter server. I will not show that again. I copied instead a screenshot into the Slack channel, so you can see there how this is happening in case you had any problems. All right, so with this, I'm happy to give over to Tim. Please go ahead.
Thank you. So yesterday, I explained all about the features that CUDA.jl has to offer, both in terms of working with libraries, as well as how to write your own kernels and GPU applications in general. Today, I'll be focusing on how you optimize these applications. So once you have implemented something to run on the GPU, how you have a go about using NVIDIA's tools to profile everything and figure out what you need to optimize and how to optimize. So I've pushed my notebooks to the Git repository. There's been some changes compared to yesterday. So once you have your Jupyter Lab server running, you could do a Git pull in the directory where you have cloned the notebooks yesterday. I've also noticed that there was some confusion given the instructions that I mentioned yesterday on how to install NVIDIA's Insight Systems tool. I'll run through it once I get to that part in my notebook, so don't worry about that. I'll make sure there's plenty of time to get that set up and working properly for the remainder of the notebook. So there's 2 notebooks again. The first one is on how to analyze GPU applications, and the second notebook is going to be how to deep dive into the optimization and the analysis of individual kernels. So let's start with the analysis of GPU applications. I'm again going to run this in my local Jupyter instance because that's a little easier, but most of the things should just equally work as well on Jupyter Lab. So make sure you also reinstantiate the environment because I updated one of the packages, benchmark tools, to include a bleeding edge version that has a specific new feature that I'll demonstrate in this notebook. So first, I'll quickly see. There's a message from the yes. If there's any problems with how to check out the notebooks or anything, let us know in the chat, and then I'll give you some additional details on how to make sure that the notebooks have been checked out. and make sure you can follow along. So once you have the notebook running and you have the environment up to date and CUDA checked out, you can follow along. And I'm first going to demonstrate how to do some basic time measurements from within Julia without having to use any of the external tools. So in Julia itself, we're used to some of these macros, such as, for example, the @time macro to measure execution time. And we can equally as well try to use this for GPU code. So in this example, I allocate some data. I perform a matrix multiplication, first a warm-up iteration, and then a iteration of which I measure the execution time. Let me zoom in a little first. There we go. But as we can see, this execution time is very low, and actually it's much too low for what we expect for this kind of computation. Maybe I should clear the output first. Let me do that. There we go. So as you can see, still the execution time is very low. And that's because, as I explained yesterday, most of the operations you execute from the CPU to be executed on the GPU are asynchronous from the CPU's perspective, meaning that the invocation of this matrix multiplication returns immediately. And as a result, measuring CPU execution time like this doesn't make much sense. And as you can see, the result is that the execution time is much too short. And in order to accurately measure the execution time from the CPU's point of view, what we need to do is to add some synchronization. You always want to synchronize beforehand, because otherwise you could include other asynchronous operations in your time measurement. And of course, you want to synchronize after your asynchronous operation. And if we do this for this matrix multiplication, you can see we get much higher times, which are more realistic for this kind of operation. And because this is such a common operation, we have our own version of the @time macro in the CUDA module. So anytime you want to measure the time of a complex application that performs some GPU operations, it's better to use the CUDA version of the @time macro. So if you do that here, once for warm-up and then for the final time, you can see we get the expected execution time. And in addition, the CUDA version of the @time macro also reports on some allocation details, because the 46 allocations we see here is actually misleading, because these are CPU allocations. And in CUDA's version of the time macro, it clearly says so that these are CPU allocations. And because this is implemented in the CUDA module, it actually also knows about the GPU allocations that happened. And this is expected. For this kind of operation, this matrix multiplication, which is out of place, we need one destination array to store the results in. So we have to perform one GPU allocation, which took around 3% of the total execution time. Similarly to the @timed macro in base, which gives you programmatically access to all of these timings, the CUDA module also has a version of the @timed macro, which includes the things we expect, like the CPU bytes and the CPU GC stats, but also GPU memory statistics, GPU memory time, GPU bytes, and so on. So this is useful if you want your application to have access to these timings in order to, I don't know, present some statistics to the user or anything. And finally, we also have the elapsed version of the elapsed macro, which is the one I explained yesterday. There's a big difference between the @timed and @elapsed, because the @timed macro is going to measure execution side from the CPU side, while the @elapsed macro is going to be using CUDA events. So it measures the execution time from the GPU side, which most of the time is going to be similar, and it definitely is in this case, because we're using a very small operation. But however, if you have a type of application that also has lots of CPU overhead, and the @elapsed time might be smaller. And this is apparently the case here, because of course the allocation that needs to be performed on the CPU is not part of the time it takes on the GPU. So anyway, these are some fairly convenient, but still low-level tools, which, as you can see, if we execute some of these a couple of times, we get wildly different results. So that's why it's generally recommended to use the benchmark tools package. Benchmark.tools.jl is going to give you the somewhat more statistically sane results by evaluating the code you want to execute, measure multiple times, and making sure that the distribution of the timings is somewhat sane. And again, we can easily use this in combination with GPU code as long as we just make sure that we synchronize everything properly. And in order to make that a little more convenient, so instead of having to add the function calls to the synchronize function, you can also use the CUDA.sync macro, which I also demonstrated yesterday, which is somewhat more convenient because it preserves the output. So in this case, it doesn't matter really, but in other cases, you might also be interested in the result of A times B, and then the @sync macro is a little more convenient. And as you can see here, we get the lower bound execution times that in some cases were reported by the @elapsed usage. So the @timed version was still including some CPU overheads, which aren't relevant in the long run. Now, even still, this may look like a very noisy result from the histogram. But as you can see here in the output, this is the y-axis is logarithmic, and in the latest version of benchmark tools, you can actually set this to be non-logarithmic. And this is just to show that the actual noisiness of this measurement is much lower. So this is why I'm using a bleeding edge version of the benchmark tools package. Generally, you don't necessarily need to. There's nothing that makes it more GPU compatible, but this is just to highlight that the plot isn't as noisy as you might think if you see the first output of this plot. So there's one big pitfall with benchmark tools though. So as you may have seen, I never used interpolation to make sure that we have fast references to these variables. I purposely did so because if you do, then it's impossible for Julia to free these arrays, because by interpolating them with the benchmark tools package and this @benchmark expression, it's impossible. There will always be a reference to A and B because they are interpolated in a function definition. And the sad result of that is that, especially in the case of memory constrained devices like GPUs, you will be leaking memory, and after performing a bunch of benchmarks, you will be running into out-of-memory situations. So that's why generally I don't use interpolation, also because it often does not matter because the operations are so heavyweight. We're performing a multi-microsecond operation where the cost of just doing this global lookup is very small in relation to the actual cost of the operation. Nonetheless, if you do want to use interpolation, there's a couple of workarounds. So one workaround is the early free function, the early free function I mentioned yesterday, CUDA.unsavefree. By doing so, you can forcibly make CUDA.jl free this memory, even though there might still be a reference somewhere in some private function generated by benchmark tools, which you will never execute anymore. So this is a hacky way to get rid of that memory. An alternative, a better way, is to teach benchmark tools how it needs to set up the arguments and afterwards how it can tear down the arguments. So in this case, by adding the definition of the A and B arrays to the setup phase of the benchmark, we don't need to interpolate. And as a result, there won't be any references to this memory interpolated in some function definition, and Julia will be able to free this memory. So this is a good alternative way if you don't want to do the unsafe free hack to make sure that Julia can release this memory and you won't run into out-of-memory situations. And as you can see, the timings are virtually identical. So these are very convenient tools to be measuring the performance of GPU applications from the CPU side, and we will be using them throughout this and the next notebook. However, it's still a coarse number. When you're dealing with a complex application, you might want to know why some operation takes long, or where time is being lost, which kernel is slow, and that's where a profiler comes in. But again, the same issue that we had with measuring time breaks usage of Julia's profiler here. So here I'm using the add-b profile macro from benchmark tools, which is also a new feature, but this is just going to call add profile multiple times. And as you can see, if we look at the trace here, which I've truncated quite a bit by adding the noise floor argument, because otherwise we get much more lines, we don't see anything related to matrix multiplication in here. It's all just management of the execution, and then most of the time seems to be spent waiting for the GPU to finish. It's actually not even visible in this case, but if you expand a little more frames, you can see that most of the time is soaked up by this wait call, which comes from a call to a synchronization. So because the way we make it possible for Julia's scheduler to perform other work when the CPU is waiting for the GPU, this is where most of the time will be soaked up. So of course, this is not useful whatsoever, and we need a way to really show what the GPU is doing while it's performing these operations. And for that, we can use NVIDIA's tools. It's called the Insight suite of tools. There's actually a couple of tools depending on what specifically you want to do. And NVIDIA has this helpful image on their website explaining which of the Insight tools you should use. And it's pretty clear that you should always start with Insight Systems. And that's because Insight Systems gives you a high-level overview of the performance of your application. As you'll see, and you've seen the screenshots in my previous notebooks yesterday, it gives you a neat timeline of every operation when it was queued on the CPU, when it was executed on the GPU. And as such, it can teach you where you need to remove some CPU overhead, and you can learn from it which GPU kernels need to be optimized. So once you know that, and typically this is sufficient to optimize most of your GPU applications, but sometimes much of the time may be spent in a couple of kernels, and then you might need to take a closer look at the performance of that kernel. And for that, you can use Insight Compute, which gives you detailed kernel performance metrics and the ability to know how you should optimize your kernel. Generally, Insight Graphics is not relevant here because the only thing we're doing is compute on the GPU. So in this notebook, I'll be using Insight Systems to illustrate how you should analyze and profile a GPU application. So for that, we need to set up Insight Systems for use on Pitsdaint. And you also need a local installation, or at least a local version of Insight System to render these results, because as you'll see, NVIDIA Insight Systems has a user interface, and we obviously can't easily run the user interface on the supercomputer. So first of all, let's start with making, so it's explained in here in case you want to read this afterwards or have a closer look at the commands in order to copy paste them. But Insight System consists of two binaries. There's the NSys binary, which we'll be using on the supercomputer, and then we have the NSys UI binary, which we'll be using on your local system to visualize the result. And both of these binaries are part of Insight Systems if you download it from the NVIDIA homepage. So yesterday I mentioned the instructions for doing so. But if somebody wouldn't have been able to set it up, I'll run through them quickly now. So once you're on Jupyter Lab, you can open a terminal. And in order to use Insight on the supercomputer, you can just use it from my Scratch space. And in order to do that, you can use this statement, which adds a directory to your path. So you can just use the Insight binary. I discovered you can copy paste into this terminal by shift right clicking and then using paste, which is a huge quality of life improvement. So now we can just do ansys version, and everything works here, which is great. So now we'll be able to record and profile software from the supercomputer. Now, in order to download NVIDIA Insight systems on your local system, you can go to the website, which I shared yesterday. I'll share it another time in the Slack now, in case somebody wants to download from there. However, you need a user account in order to download these files. And because it might take some time setting up that user account, I have also mirrored the where's Jupyter Lab? I have also mirrored the installers in my Scratch space. So you can actually go to my Scratch space, and as you'll see, there's the Insight installers over there. There's one for Windows, there's one for Linux, and there's one for Mac. So if you copy either of those to your home folder, Insight Systems, let's just take the Windows one. If we copying to my home folder and we refresh the view, we can actually download the file from the supercomputer, which is an easier way to have all that set up. So maybe I'll give people a couple of minutes now to make sure that everything's set up. So you need to make sure that you can run ansys on your terminal instance in Jupyter Hub, and you also need to make sure that you can run ansys UI on your local system, and then you can get the user interface. Yeah. There it is. It'll just open like this, and then here you can then open and import files we'll be collecting from ansys on the cluster. So if anything doesn't work out there, let me know in the general channel, and I'll give people 5 minutes or so to try this out and make sure it's all set up. So seeing how there's no questions on the general channel, I suppose that everybody managed to set up Insight. So now I'll demonstrate how to use this tool on the cluster or on any system that has a GPU. And the real power from Insight systems is that we can use it interactively. So you can do ansys launch Julia, and now we get an interactive wrapper. So we can, as we're used to, import the package and perform some operations like do array of 1, and then I do a broadcast +1. This, of course, takes a while to do the initial compilation to GPU code. So nothing out of the ordinary is happening currently. The magic of the profiler only kicks in when we surround code by CUDA.add profile. So once we do so, this code will be evaluated and run on the GPU under the profiler, which has itself injected in current process. And as you can see, the Insight system tools detected the sign that the CUDA.add profile macro gave it, and now it's capturing some stuff, writing to disk, and we'll be able to download and import the resulting file. So here you can notice that it initially wrote a QD stream file to disk, which is a trace file that's fairly large. And then finally, it saves the report as this ansys report file, which is much smaller, and it's written in the current directory. However, I've noticed that on BitStained, some of these steps fail. So it only produces the QD stream file, and it never moves it, or it never imports it as a ansys rep file. However, I think this is because the home file system is so slow and it actually times out. So I've added some instructions in the notebook on how you would do it yourself. So if it would fail, you'd see import error, the importation timed out, skipping import of the QD stream file. And then instead of creating a report file, it just puts the report under a QD stream file in the current directory. But that's not a problem, because either we can then download the QD stream file instead of the report file and import that. However, those files are typically very large, hundreds of megabytes. So instead, we can do the import step manually by in a new terminal using the QD stream importer, which is also located somewhere in my Scratch directory. And launching that tool on the QD stream report you have in your current directory or wherever you're running this from. And then as a result, you'll do the processing step manually and you get a report file nonetheless. I've already filed this as a bug with NVIDIA, so let's hope they fix this real soon. Nonetheless, it's just one additional step to get you the report file. So once we've done that, you can see that there's now a report file in the current directory. And we can download that file to our desktop, our working station. And these are small files, orders of megabytes. And then we switch to the Insight Systems user interface, where we can open this file. And now we see a very sparse timeline, but we see a timeline nonetheless. So this is a timeline from 80 microseconds. And we can see right here, very small, that there's some kernel being executed. And we can zoom in, zoom in, zoom in, zoom in. And we get to see our the launch operation as well as the broadcast kernel being executed. So this is extremely valuable to be able to visualize what happens on the CPU, what happens on the GPU, where the sources of latency are, and how to optimize them. We can even see the memory copies. If we highlight any of these, we get some additional details on everything. For example, the throughput. If we highlight the kernel, we can see some details on the occupancy, on the register usage, and so on and so forth. So even though this is the high-level tool that gives you a application overview, it can often give you quite some details already. So now let's switch back to the notebook. So for most of the things I'll be mentioning in this notebook, you can either copy paste them into the terminal in order to run them under Insight Systems and try out the tool yourself. Or alternatively, at the point where we'll be optimizing code, you can just use benchmark tools to only have a look at the final execution time that your kernel or application took. However, the workflow in general is extremely valuable for you to optimize any application that you've implemented in Julia using the GPU. So another more cute approach to running Julia under Insight is actually adding a kernel definition to Jupyter, making it possible to run Julia under Insight Systems in a notebook, as you can see here. So this is what I'm doing. And that's the reason I'm using a local Jupyter installation, because we cannot modify the kernel definitions of the Jupyter lab at Bitstained. So what I can do here is, because my entire Jupyter session here is running under Insight Systems, I can just import the packages, run some more realistic code this time. And as a result, we see the same output. And I can open the resulting file. CSCS, there's a report, and as you can see, this has been modified at this point. So this is a very convenient way to work with both notebooks and the profiler tools. So zoom into selection, there we can go. There we go. Can everybody read the application here, or is this too small?
For me, it's readable.
Okay.
On the screen, at least.
Great. So one thing you may notice here is that my multiplication, so in the previous profile, this one, all of our operations were just there in a sea of other operations, or in this case, a sea of sparseness where nothing was being done on the GPU. And this can make it hard to pick whatever your operations you're interested in. Whereas in this new report, I've used the NVTX, the NVIDIA Tools Extensions API to enrich the profiler trace with arbitrary additional information. And I've used that to highlight where the multiplication is happening. You can do so very easily in source code by using the add_range macro from the NVTX submodule. So this is a module that's part of CUDA.jl. So as soon as you import CUDA.jl, you can use NVTX.range to annotate code occurring, and that then will be visualized in the output of the profiler. It is recommended to always make sure that there's a synchronous block being executed under NVTX, because otherwise the NVTX range might cut off before the operation is actually finished. Because of course, NVTX is a CPU level API, and it's not stream ordered, which means that if you record an asynchronous operation, you'll only highlight the queuing of the operation and not the finishing of the entire operation. So there's a question about how to use ANSYS in the terminal on the Jupyter Notebook, and this requires you to set the path. So in a normal terminal, you won't have any access to the ANSYS binary, but you can export, add a directory to your system path where my version of the ANSYS binary is located. I'm not using any Insight Systems installation that's part of the modular system, because the one that's available is outdated and has some known bugs in combination with Julia and the interactive profiling that we're doing with Julia. So that's why for now, it was the quickest solution to just deploy my own version in my Scratch space. But over time, I'm sure that the version on the cluster will be updated to be the most recent version that's compatible with Julia. So going back to the notebook now, so I explained how you can use NVTX.range. It's also recommended to always run code twice when you're profiling. For example, here I'm profiling a matrix multiplication, and the initial time it took to profile was 8 milliseconds, but let's do 2 runs in a single profile, and you can see the spoiler here already. The second matrix multiplication is much shorter, and I'll just confirm that by opening the report, which has been generated here, and you can see the difference is smaller. Oh, the difference is inverse. Something went wrong here. Let's try that again. So the reason these are a little noisy is because I'm using my GPU that's driving my display for these benchmarks, which is generally not recommended. Okay, so here we can see what I expected. The initial profiling run, actually the initial non-trivial API call took a significant time, whereas the second evaluation was significantly shorter. As you can see, this time is entirely spent in CUDA itself, so I don't think we can do much about this except for recommending people to do a warm-up call or profile certain parts of their application twice to make sure that they have the best possible measurements. And maybe to briefly explain the rest of the user interface. So the bottom lines of this trace are all happening on the CPU. These 9 threads are all CPU threads, and we can see how the CUDA APIs are being used from the CPU, how the MVTX APIs are being used from the CPU, and it also, the tool and site system also knows to a certain extent how to decode operating system syscalls and other interactions, so they can see what's happening when, for example, your application is stalling. Now, the top lines are generally what you're most interested in, because those highlight the execution happening on the GPU. And this blue bar really is the time being spent computing something on the GPU. And the height of that bar indicates how fully the GPU was being used. So that might not be clear, but if we zoom in a lot, let's, for example, zoom in this minor selection, it's actually still not visible, but with a realistic application, you'd be able to see that this scales from a pixel high to its full height, representing 0 to 100% of GPU usage. And when you expand the kernel view over here, when you expand the GPU view, it will show you exactly with which kernels are being executed. And helpfully so, it also shows you the GPU side of the MVTX macro. So we invoked MVTX from the CPU, and Nsight visualizes which API calls that corresponded with. So even if you queued your MVTX range asynchronously, so forgetting the CUDA at sync on the GPU side, it might still give you a more accurate representation of the time it took to actually execute these operations on the GPU. There's a question on using any card that drives your display for profiling. The results will be significant, but you might have to do a couple of runs to make sure that everything is statistically sound. So let's continue. Another possibility which you can do with MVTX and that can be helpful is insert markers. So if you don't necessarily want to group anything in a range, but you just want to highlight a certain point in computation, you can use the mark function. And this will add a very tiny line to your trace, indicating when this point was reached in time. This is what I just explained, the fact that you can expand the view of the kernels over here. And once you do so, if you highlight the specific kernel invocation, you get a lot of interesting information about the memory usage, the register usage, the occupancy, and especially the occupancy is always a very interesting metric, as I'll explain in my next notebook. So with all that explained, I propose that we have another look at the root mean square error implementation we made yesterday. So recall that this was the batched implementation we ended up with, where we have a function that computes the root mean square error of two matrices. And then in our driver function called doIt over here, we call this function a couple of times for each batch that is part of the input. So let's benchmark this function to get a baseline performance, which we'll want to optimize. And then similarly, let's run this on the profiler as well. So you can see the screenshot I made from the profiler while preparing this notebook already. The baseline performance is 2.8 milliseconds, which we'll want to optimize. And let's open the report, which should be done by now in the profiler trace. There we go. So you see again, I have executed it 2 times. One time took 8 milliseconds. The second time took 3 milliseconds, which still is a little bit larger than the output by benchmarking tools. But that's because there's some obvious overhead of using the profiler rather than just directly executing code. So the way we go about optimizing this is mainly having a look at what the GPU is doing. The GPU should be really processing, doing processing as much of the time as possible. And even though the GPU is in effect doing something from the beginning until the end of our MVTX range indicating the do it function, nonetheless, there's a lot of sparseness, gaps in the profiler trace. And this generally indicates that we're doing something on the GPU that's either too slow or blocking because it prevents submitting sufficient work for the GPU to continue on computing. So typical reasons for this is that either the GPU is doing too much work. For example, you're doing some type unstable computation in between launching subsequent kernels, which means that the Julia runtime is going to be spending some time on the CPU, whereas you should have just been submitting new work. Or other possibilities are that you're, for example, running in some of these blocking APIs I mentioned yesterday, for example, copying to and from the CPU memory from non-pinned memory. And as a result, the CPU has to wait until the GPU is finished before it can resume preparing its computations to then be launched on the GPU. And those stalls really often result in gaps in the GPU trace. And there's a couple of ways we can try to improve this. So generally, we want to avoid launching too many kernels, because of course, even if we can optimize all of this white space, all of these gaps between individual kernels, if we're still launching too many kernels, then there's a couple of disadvantages. For one, we'll have to allocate temporaries. If an operation is split into 2 separate operations, the result of the first operation is going to be written in global memory, and the next kernel is going to have to read from that global memory. The disadvantage of that is, on the one hand, we need to allocate memory to store the temporary in, and secondly, reading from global memory is slow. And it also prevents the compiler from optimizing these 2 operations as a whole. So that's why it's generally interesting to try and fuse operations together, which then also avoids the additional overhead to launch 2 operations or more, reducing it to only the overhead we require to launch a single operation. And then, of course, in order to avoid the gaps in the trace, we want to avoid any synchronization or blocking operations on the CPU, sorry, making sure that we are not wasting any time doing unnecessary computations in between preparing the next kernel to be launched. So maybe as an exercise to figure out how to work with these tools, you can try, well, the solutions below, but you can try first taking this initial implementation that we had here, where we're running the root mean square error function for every batch, trying to run that under Nsight profile, trying to spot the issues I've spotted in here, namely the white space in between and the fact that we're launching so many kernels, and try to optimize and have a look at that optimization effort in the profiler. Meanwhile, I'll try to make sure that everybody gets this up and working, and in maybe 10 or 15 minutes or so, I'll work my way through my optimization and how I went about taking this function and making it a couple of times faster. Let's continue. So I'm going to assume that everybody has figured out how to run Nsight systems on both BeatStains and on your local system to inspect reports. Harman has posted some helpful commands in the Q&A channel, which you can copy and paste into a terminal in order to quickly demonstrate how to get everything working in case you still have some problems. So now I'll continue taking this batched root mean square error example that we developed yesterday and try and optimize it. So the baseline performance was around 3 milliseconds for 16 batches of 1024 by 1024 float 32 inputs. So let's try and optimize that. As I already mentioned, if we look at the trace, we see lots of kernels and also quite some gaps between the individual kernels. And if we look at the API calls that correspond to those gaps, we can see that there's a bunch of memory allocations happening which take quite some time. And worse, there's some time being wasted in between the individual iterations. And that's because of a property of the Julia language, namely that if we, let me go back to the implementation, sorry for scrolling. If we slice arrays like that, we'll actually make a copy. So before launching the RMSE function for every batch, we'll actually be copying a 1K by 1K matrix every time. So we can easily avoid that by using views instead. And if we now, let's enter this definition, we can see that the results are also the same. If we profile this, sorry, if we benchmark this, baseline performance was 2.9 milliseconds. We're down to 1.9 milliseconds, just like that. And if we have a look at the profiler trace, we can see that the gaps between the individual iterations are gone, but nonetheless, there's still quite some white space happening, which in this case indicates, or at least if we have a proper look at the trace, then we can see that at every iteration, we're actually waiting for the GPU to complete. And the reason behind that is that we're calling in the RMSE function, we're performing a sum that reduces to a single scalar, and then we're saving the scalar in a vector on the CPU. And that's a bad pattern, because by having to reduce to a scalar, we actually need to wait for the GPU to finish, because otherwise we wouldn't have a way to know which number has been computed. There's no way to reduce to a lazy scalar that can be asynchronously collected later on. Of course, an easy workaround, or an easy solution, actually, it's not a workaround, is to reduce to a single element array. So let's do that here by specifying the dimensions of the reductions. Instead of just doing an ordinary sum, we'll actually be reducing to a single element array. Even though we're reducing across all of the dimensions, we're still reducing to a array and not a scalar anymore, which means that this sum operation is now allowed to complete asynchronously. And in order to benefit from that, we're also going to use a broadcast division by the length of the array, as well as a broadcast square root computation, all of which is going to be working with this one element array, and as such can be launched asynchronously. Finally, we save all of these one element arrays into a vector on the CPU. And when we return from our doIt function, we collect all of these arrays and concatenate the results on the CPU. So that's also the reason I don't have to synchronize after calling this function, because the contract of this function is that it returns a CPU array, meaning that it needs to wait for the GPU to finish before it can actually write some CPU values. And as such, I don't need to synchronize. We can see that the results are still sane. So let's have a look at the performance. Last performance was 1.9 milliseconds. And now we're down to 1.5. And let's actually have a look at a profiler trace. So let me copy this invocation. I see that I didn't make a screenshot here. This obviously always takes a while. In some strange occurrences, it's possible that Inside Systems hangs. So let me verify that's not what happened here. It looks like this is exactly what happened here. So let me kill my Inside instance and restart it real quickly. I haven't seen this happen on the cluster, if that's any consolation. It only happens on my local system. Okay, there we go. Let's restart the kernel. And we just need to import the package now again. That's at the top. Using the package. And defining the data. And this is the profile trace. Oh, sorry, first need to define the doit function. It's actually still compiling the function at this point. Again, because the initial compilation of the GPU kernel first requires to compile most of the GPU kernel itself before it can actually start compiling the kernel you want to execute. There we go. Now we have a trace. Let's zoom in on the second iteration. So we can see here that gaps are starting to disappear. There's a couple of large gaps left. Some of these take longer than other allocation because once in a while, CUDA has to compact its memory pool. And on the other hand, sometimes you might see a huge gap like this, and this is often caused by the Julia garbage collector having to perform a scan. And if you actually have a look at if you select something in the profiler, you can see the time it took to complete this. So this is actually only half microsecond, which is somewhat acceptable in terms of the GC's performance. But of course, when you look at this kind of very optimized GPU applications, half a millisecond is quite significant in the grand scheme of things. So if we run this a second time, probably we wouldn't have included a GC run, and we wouldn't have this large gap. And this, of course, is one of the reasons that if you have lots of temporaries, like we currently do in our implementation still, because we haven't fused kernels, then it's advisable to use the unsafe free function to return that memory really quickly to the CUDA allocator, so that we don't have to call the garbage collector when we run out of memory, which is probably what happened here. So nonetheless, there's still some allocations left, which we can get rid of. And of course, these allocations are because we were still creating a bunch of new arrays every time we run the root mean square error function. And we were then saving it in a CPU vector, but we can, of course, go one step further and allocate a GPU vector, because this call to similar is going to create a one-dimensional GPU vector with n elements, which we can then use to save the result of all our operations in. So we take a view of that function, and we'll also be reshaping it to a 1-by-1. And as a result, we can pass it to the sum bank function, which is an in-place sum computation that's going to look at the dimensions of the destination container, which is the first argument here, C. And it's going to reduce all of the singleton dimensions. So in this case, all of the dimensions are 1, they are singleton, and as a result, the sum bank function will reduce both the first and the second dimension and sum across them, which is exactly what we want, because we first want to compute the difference and square that, and afterwards we want to sum that to a single scalar value. However, it's still going to be saved in this C output matrix, meaning this is not a eager call that finishes right away. It's going to lazily compute the sum and lazily reduce all of the values in our input matrices to this 1-by-1 vector. So let's again measure the performance of this. Output looks correct. Let me also already copy the invocation of the profiler and put that in a new cell. 1.4 milliseconds, so that's actually not a great reduction, but nonetheless, it's one of the steps on the way. Profiling has finished. Let's open this up. Let's fit the second one. We can see we further reduced everything a little, but nonetheless, there's still allocations left. And those allocations come from the temporaries, because if we look at our implementation first, we still have to compute A minus B, which results in a temporary, and then we square that, which results in another temporary. So as a result, even though we've made the sum in place, all of these operations still result in a bunch of temporaries. And this is something that you generally want to avoid in this kind of hot loop. Luckily, we can do so because we can, instead of the sum bank function, can use the MapReduceDim function, which takes an anonymous function that it will first use to map all the values with, and then perform a in-place reduction to an output container. So here we pass an anonymous function that's going to perform the compute the difference of two elements, square them, reduce everything using the plus operator. And because of the size of C, again, having two singleton dimensions, it's going to reduce everything to a single element array. So if you try to execute this, sadly, we run into a error, and it should have been highlighted here. The reason we cannot invoke this version of MapReduceDim is because it doesn't support two arguments. But what it does support is a lazy, we can manually perform the broadcast lazily first. By calling the broadcast.broadcasted function, we get a lazy non-materialized function, which we can then just pass to the MapReduce function. As a result, fusing everything together to a single kernel. And this is a really powerful pattern. It's a bit verbose, but you can more easily use it with the lazy arrays package. If you use lazy arrays, you get a very convenient macro-based syntax to just perform a broadcast and get a lazy non-materialized broadcast as a result. But here, not to add another package dependency, I've just done it manually. So again, this is a lazy broadcast, which I then pass to MapReduce, and as a result, we only will get a single invocation of MapReduce in which all of the element-wise operations have been fused in. So let's make sure this is valid. So do note that MapReduceDim requires us to initialize the output. So instead of just having a call to similar, I also have a call to fill now. And let's benchmark this again. And finally, we also want to highlight this in the profiler. Now we're down to 600 microseconds, which is a nice improvement from the original 3 microseconds. And let's have a look at the trace. Fit to screen. And there we go. No allocations left whatsoever anymore. So the huge allocation you could still see in the previous run, slowing down GPU execution, now is completely gone. And as a result, we get a very packed trace on the GPU. And this is very much what we want. The reason that it's delayed is probably because of some profiler interaction. If we'd run this a second time, it would be much faster, because otherwise we wouldn't be down to 600 microseconds. Of course, all this is somewhat contrived, because we could have taken this to the next level and just have gotten rid of the outer loop, because everything takes a DIMS argument. So we could as well have removed the outer loop and just have MapReduce dim reduce across the batch dimension, actually preserve the batch dimension, but not have it launch one kernel for every batch. And this is, of course, what you need to do to make this kind of small operation very fast. But I didn't want to include it from the get-go, because typically with realistic applications, you do get many operations in sequences. So in that case, you do want to more carefully try to avoid operations, temporaries, try to fuse things together whenever possible, try to make sure you copy memory through to and from pins, CPU memory, in order to avoid stalls, and try to avoid other sources of synchronization. So in that sense, having the for loop with a bunch of kernels in a body was a good demonstration of these properties, because any inefficiency would have been multiplied by the amount of batches that we're doing. However, specifically for this operations, it's of course much better to fuse it all together, and then we get an execution time of 500 microseconds, which, mind you, isn't much better than the 600 something microseconds we got with the for loop still. So most of the gains came from fusing within the loop and avoiding temporaries within the loop, and not necessarily getting rid of the outer loop altogether. So, and if we profile this, I'm not going to do it now because the screenshot is just as interesting. We can see there's only a single blob where the GPU is computing with only a couple of kernels being launched. It's still a couple of kernels because the square root and the division are still individual broadcast operations, and the fill as well requires the kernel to initialize the memory. So, and before I end this notebook, I have two additional comments on this. One is that the advantage of avoiding array operations like this is that you can still use everything on the CPU. So all of these operations we've done in here, the MapReduce dim, the broadcasting, fill, similar, there's nothing GPU specific in here, meaning that we can still execute this on the GPU, on the CPU as we're used to. And it's always interesting to to compare the performance of a CPU and a GPU implementations. So the GPU implementation was 500 microseconds, but it did include memory transfers, whereas in this case, it's 17 milliseconds on the CPU. So we're an order of magnitude faster. And of course, Tulio, which we introduced yesterday, is also interesting to have a look at, because with Tulio, it's very convenient to express these kind of operations very succinctly. And in the case of the CPU implementation, I overwrote my input, so this is only going to evaluate on the CPU. So the CPU implementation actually performs really well. It goes down from 17 milliseconds to 2.6 milliseconds. But the GPU implementation is actually horribly slow. So I can't evaluate it anymore because I've overwritten my inputs, but it's around 100 milliseconds. However, that's presumably a bug in how code is being generated, because as you can see, Tulio does manage a nice speed up for the CPU implementation, and generally so for other applications I've looked at. Tulio also does a great job for GPU code. Well, however, in this case, in this root mean square deviation over batched inputs, the performance of the Tulio generated kernel is pretty bad. Something else that's interesting to demonstrate is the use of the CUDA Graph API, because the CUDA Graph API is basically made for this. When you have a for loop that launches a bunch of kernels, with the Graph API, it's possible to record those, and as a result, the launch overhead of the graph operation, which includes all of the individual operations, will be much lower than launching all of the individual operations individually. So let's try this. So this is back to the original implementation, and now we just add an add capture to it. And sadly, we immediately get an error, and the error is stream capture invalidated. And that means in a very inscrutable manner that we recorded some operation that's incompatible with the graph capture. And as a result, the graph capture got invalidated. And here, so this actually can vary between CUDA versions and CUDA.jl versions, because with every CUDA version, more and more operations are supported. And similarly so, with each CUDA.jl version, we try to detect when we're recording for a graph and then avoid doing some operations which we know are unsupported. So in the future, it's possible that this very example might just work out in the box, but currently it doesn't, and that's because we perform some synchronization when copying from and to the CPU, and that kind of synchronization is not supported when doing a graph record. So instead, let's use one of our in-place function that uses a QArray for all of the results and passes it to the RMSE function to use as an in-place container. And this we can actually successfully record. So as we see, we get to see the results, and it has executed under the add captured macro. There might be, if you try to reproduce this, there might be some errors. We have some known issues with how memory is being managed. So as a result, I won't be running it under benchmark tools, because then we would run into an out of memory situation. But nonetheless, we can still run this under the profiler. And what's interesting there, so the top profile here is when we run the individual operations in succession without using graph records. And all of these launches, for example, take around, what's latency, 3.8 microseconds. However, if we use a graph record, then all of the operations we record are much, much faster. For example, a launch of a kernel now only takes 1.4 microseconds. And then in the end, we have a single API call, the cugraph launch, which takes significantly more time. But the expectation is that the total time of all of these shorter operations and the one expensive launch is going to be significantly lower than doing all of the expensive operations by themselves. However, in the case of this very application, you can see that the total evaluation time actually regressed a little from 1.7 to 1.8 milliseconds. So that means that the Graph API isn't, or the way we use the Graph API currently isn't well suited for this very application. So as a result, you shouldn't treat the Graph API as a silver bullet that you can just throw at any application. On the one hand, there might be quite some incompatibilities because of operations you're doing or CUDA.jl is doing. And on the other hand, it might also not improve performance. So the Graph API can be very valuable. For example, when you don't necessarily have to re-record anytime, if you just want to replay a kernel a couple of times, a sequence of kernels a couple of times, then it will definitely be faster. But if you have to re-record every time, you have to take care and make sure that using the Graph API has some benefits from your applications. Right. So the next notebook is going to be on kernel optimization, whereas we now focused on the high-level timeline and optimizing the GPU application in terms of its operations. But before that, I propose we take a 10-minute break. Maybe a good time to try and reproduce some of these timings with Insight systems or on any of the benchmarking tools that I've demonstrated. And if there's any questions, don't hesitate to put them in the Slack channel. See you in 10 minutes. Okay, so for the last notebook I'll be presenting today, I'm going to have a look at how you analyze and optimize a individual kernel. So I'm back to using Julia itself. So I'm not running under inside systems anymore, which means you can just follow along in Jupyter. I'll be benchmarking these kernels with the benchmark tools package. Because now we know we're just going to measure the execution time of a single kernel. There's no overhead anymore from other kinds of operations. So it's easy enough to just use these raw time measurement tools to have a look at the performance of an individual kernel. Now, generally, it's not necessary, or it's only necessary if you have a very well optimized application in the first place before having to dive into optimizing a kernel. Nonetheless, there's some things you need to take into account and are good to just think about when you're writing kernels, just to make sure that you're not running into any or falling into any performance pitfalls. So for this notebook, for this session, I'll be explaining some of those pitfalls and some of those more Julia-specific optimization patterns, because there's plenty of resources out there already. So I'll be focusing on things that would mostly apply to working with GPUs in Julia. So generally, when you want to optimize a GPU kernel, if you want to consider first picking an appropriate algorithm. You don't want to perform a serial algorithm, of course, on the GPU. But beyond that, the most common optimizations are avoiding thread divergence, which means that every thread in a warp should be essentially executing the same instructions, which means that you cannot be branching even in one direction or another direction between threads of a warp, let alone doing completely different code. So threads on a GPU are not as you need to take into account that they're really running in lockstep in a warp of 32 threads. But that's not really Julia specific, so I won't be spending much time talking about thread divergence. It's also a very typical optimization when you Google for CUDA kernel optimization guidelines. Another common optimization is avoiding global memory accesses, because the global memory bandwidth, meaning from a thread to its global memory on the GPU, even though it's fast, it's not fast anymore if all of a sudden you have thousands and thousands of threads doing those memory accesses at the same time. So you generally want to avoid global memory accesses as much as possible. You can do so by either caching values in, for example, block local memory or shared memory, or you can be using other more fine-grained mechanisms to send data between threads. For example, if you have threads running within a warp, you can very easily communicate between them through registers, which will not incur any performance or will not result in memory bandwidth usage. Generally, so you just want to optimize your memory accesses as well, making sure you don't have bank conflicts, making sure accesses are coalescible, but those things I'll mention briefly during this notebook. So again, let's start with the batched root mean square error computation. We have written yesterday the kernel version that performs all of the operations within a single kernel. So here I have my kernel function, which we implemented yesterday. And then I have a small driver function, which calculates both of the Cartesian indices. If you remember, it's the set of indices that needs to be reduced. And then there's a set of indices that correspond with the different batches. And then within the kernel, we're adding those indices together and using that to index our main memory. And we get the results we expect. However, actually, I didn't clear the output once again, so let me do that again. So if we benchmark this, if you remember, we have some pretty bad performance characteristics. 20 milliseconds, and this is for the same operation that only took 600 microseconds on our optimized array implementation. So this is, needless to say, very bad. And in order to analyze this, we can, because if we analyze this with Nsight systems, you would just see a single blob of a single kernel taking up all of the time. There's nothing to learn from that with regards to what took any time. For that, we have to use the second tool called Nsight Compute. And using that tool is a little more complicated. So we can also still do it in an interactive fashion. So let's use the terminal. You're not able to do this on Piet currently because of some incompatibility between the hardware and the tool in question. So you will just have to follow along this time. Of course, most of the benchmarks in this notebook, you can just reproduce using @benchmark from benchmark tools, but you won't be able to see the detailed analysis I'm doing here. Of course, if you have an NVIDIA GPU in your local system, you can always try doing so locally. And Nsight Compute can be downloaded from the same NVIDIA web page, where you have to use your developer account to download any of the versions that correspond to your operating system. I'll share the link in case anybody wants to follow along on a local system. If not, you can follow along by me doing it. And where we previously used NSYS launch with NVIDIA Nsight Compute, we just can do NCU --mode equal launch. So it's slightly dissimilar. And then passing the path to Julia. In my case, I'm just using a wrapper. You can ignore this. This could just be Julia if Julia is on your global path. And then we again get a interactive session where we can just import CUDA, where we can do stuff like allocate a Q-array. However, the very first CUDA API call we perform will just sit there, it'll hang. And that's because it's waiting for the profiler to attach. So for that, we then need to open up Nsight Compute user interface. And from the quick launch, we can connect to our local setup. So normally it should also have been possible to SSH, to automatically SSH to your compute node and have Nsight Compute set up everything for you. However, that just doesn't work with how the cluster is currently set up, and that hopefully will work with the new supercomputer when it arrives, because the current hardware generation, the P100s, are on the verge of not being entirely supported by Nsight. It does work with Nsight systems, but apparently it doesn't work perfectly with Nsight Compute. So now I'm connecting to my local system here, and you can see that it detected the Julia process that's waiting for a profiler to attach. So now we can just click attach. And we get to see the API version, the API call where it's stuck at, but we're not interested in API call, so we can close this. And what's crucial here is that we enable auto profile mode. And auto profile mode is going to make sure that any kernel that's being launched under CUDA.add profile will be profiled within Nsight Compute. You also want to disable the break on API error, because we do some API calls that we know will fail, and Nsight Compute will otherwise hang at those, and we don't want that. And then we can continue, resume. Now you've seen in the background that my application has continued. So let's perform a dummy operation again, a broadcast addition by 1. This takes a while to compile. There it is. And as I mentioned, it first needs to be running under CUDA.add profile before Nsight Compute jumps to live. And you can see that we have some output here. And these are extremely detailed information about what this specific kernel does. We can have a look at all of the memory characteristics, all of the instruction characteristics. We can even have a look at the generated source code, where it tries to map it to Julia source code and so on and so forth. So this is very valuable, but ridiculously detailed, and you generally don't necessarily need this. That's why I recommend always using Nsight Systems as a first tool before considering Nsight Compute. Nonetheless, in this case, we do want to optimize our kernel, so let's paste this in my terminal. We need some data first, of course. There we go, and then we'll be invoking this on C, A, and B, and these are the expected results. So let's run this now under the profiler. And here we can select the kernel we want to analyze. So this was the initial broadcast kernel we did. Now we want to have a look at the root mean square error kernel. And if we go to the details page, you can see some of the issues that this kernel has. And some of the major issue with this kernel is that you can see it mentioned here. Every scheduler is capable of issuing one instruction per cycle, but for this kernel, each scheduler only issues an instruction every 21 cycles. So we don't have enough instructions that are being executed because the GPU is stalling. And you can see that here. In 95% of the time, there's no warps that are eligible to execute, again, because they are stalled. And then in order to figure out why things are stalling, we can have a look at the warp state statistics. And here we can see that there is a stall long scoreboard. And this is typically a type of stall that happens when you're dealing with loads from memory. All of that is explained in detail in the NVIDIA. There is a link. There is a kernel optimization guide. Yeah, I link it later down in the chat. But all of these stall reasons are thoroughly explained in the CUDA documentation. And there it's mentioned that the stall long scoreboard is caused by memory loads, typically so. Typically also when instructions that stall aren't necessarily bad, because the GPU is great at hiding latency that comes from these stalls. For example, if we're stalling, but at the same time, there's plenty of warps eligible to execute, then the GPU can just perform something like a context switch to a different warp, and the latency of the first warp stalling is completely hidden because the GPU just continued executing some other threads. And this is one of the big advantages of using GPUs. Even if you're loading global memory, as long as you have enough threads to execute, then the GPU can hide that latency. But that also means that we need to have enough threads eligible to execute. And one of the ways doing so is to optimize the kernel implementation, as we'll do so later now. But in this case, it's just impossible to hide all these stalls. And in order to figure out where the stalls come from, you can always have a look at the source code. And in this case, because we're still working on a good mapping between the generated code and the source code, as you see here, it's not fairly useful because it's just pointing to a low-level function in LLVM.jl. And that's because in Julia, we inline a lot of stuff, and we're working on improving the rendering of inline source code. So we'll just have a look at the PTX code. And here we can, I'll just use the screenshots instead of scrolling all the time. We can have a look at the screenshots to see where the sampling profiler was stuck all the time, or at least where most of the samples were taken. And you can select the categories that you want to show. And in this case, I've highlighted the sampling data, which typically is the most useful category to start your profiling effort, because this is just where the profiler noticed that the GPU was stuck at a certain point in time. And here we can see that we're performing a subtraction, but it stalled on there because some of those loads came from global memory. And this is where the long scoreboard load came from. And all of that, if you have a look at the surrounding code, clearly points to those global additions, which first need to load some memory, then perform an addition, and then store back to the memory. So the fact that we're doing global memory stores on every iteration on this kernel is bad. The fact that we're doing so atomically is doubly bad, because it in fact synchronizes the execution and prevents threads from executing when another one is waiting for a global memory operation to retire. And the way we have to resolve this is by just computing the sum in a different way. So the reason we had this at atomic addition, if I go back to the source code, it was to compute the sum of these values subtracted and save that in our C output matrix. But again, every thread doing a global memory operation and every iteration is just a bad way to compute a sum. It's a bad way to perform a reduction. Instead, we need to use multiple threads to perform this reduction cooperatively. And those kind of things are fairly tricky to implement on the GPU. NVIDIA has written tons of blog posts on this. For example, this is how to implement a faster parallel reduction on Kepler era hardware. And many of these implementations, many of these optimizations have already been implemented in CUDA.jl. And I'm going to, instead of spending time explaining the optimizations from this blog post, which is a generic GPU optimization pattern and not necessarily one that's specific to Julia, I'm just going to reuse that implementation, this unexported function from the CUDA.jl package in order to perform this reduction in a cooperative manner. So here what we're doing is, instead of writing to global memory atomically every time in every iteration, we're going to be reducing to a local value. And this is a cooperative reduction, meaning that at the end of this loop, every thread has the same value stored in val, while every thread in a block. Which means that finally we can just in one thread of the block use that value to write to C. And because we know that every batch is going to be processed by only a single block, we don't need to perform any addition here. We can just write to global memory straight away. So this is what I meant with doing a kind of algorithmic optimization in a sense, because instead of having every thread doing the reduction on its own in a almost serial manner, because the hardware can't execute this in parallel, we're going to use an algorithm that allows doing this cooperatively across the threads of a group. And as you can see, performance has dramatically improved from 20 milliseconds to around 4 milliseconds. And now if we run this in the profiler again, we can see that the amount of eligible warps has improved, because there used to be 95% of non-eligible warps, and this has lowered to 77% of non-eligible warps. And at the same time, the huge initial stall of the long scoreboard reason has almost completely disappeared. It went from something around 40 cycles to around 2, which is much more straightforward. Another problem here is that we're hard coding the amount of threads we're using. And this is okay because we're using a grid stripe loop, which means that the execution of this kernel is going to adapt to how many threads have been launched, even though we're maybe using a data size that's smaller than 256 or way larger than 256. That's the beauty of this grid stride loop. It will just adapt and keep on iterating until we cover all of the values we want to cover. However, that doesn't mean that this is sufficient, because that is optimal. Because as I mentioned, the GPU, in order to hide the latency of operations, needs to have enough threads executing within a block. And in this case, by artificially restricting the amount of threads to 256, we're restricting the ability of the GPU to switch to other threads to hide the latency, because there just aren't enough threads. And we can inspect how many threads we ideally should launch for a given kernel using CUDA.jl. By passing the launch equals false keyword to @CUDA, we are not going to launch the kernel, what's in the name, but we get a kernel object that we can then use for reflection. For example, one of the things we can do with that kernel object is use it as an argument to the launch configuration function, which is going to query CUDA's occupancy API to figure out how many threads we should ideally launch to get as much occupancy as possible from this kernel on the GPU we're working with. And this is at the same time also an upper bound, because as I mentioned yesterday, every GPU has an upper bound of how many threads you can launch, which on my GPU was 1024. However, depending on how much registers and how much local memory every kernel is using, that number can be further lowered. So instead of 1024, it's only 512. And that's presumably because this kernel uses a lot of local memory or a lot of registers.
Can I ask what the criteria are, or how is this determined?
The amount of registers or the ideal thread configuration?
The ideal thread configuration. So what's happening if you run launch configuration? Is it something in CUDA.jl, or is it?
It's an API. It's an API in libcuda. So it actually calls there is a heuristic implemented in the CUDA libraries that inspects how many registers your kernel uses, how many register space your GPU has, and it tries to map out an efficient way to it proposes a launch configuration. So this is not a heuristic that's implemented in CUDA.jl, it's a heuristic that's implemented in CUDA itself.
Okay, thanks.
So the thread count is both an upper bound, but it's also a recommended lower bound, because otherwise you're underutilizing the GPU. The block count obviously is just an advisory lower bound. You can always launch fewer blocks if your algorithm doesn't require as many. But that will not use the GPU as optimally. In this case, it's going to determine a optimal block count based on the amount of streaming shared multiprocessors that your GPU has. So even though the GPU's programming model doesn't really make it clear, every GPU contains a couple of processors, and in order to fully utilize them, it needs enough blocks to launch on each of those. And in this case, I think I have 24 multiprocessors, but each of those can execute 2 warps at a time. So as a result, we need 48 blocks for an optimal usage of the GPU. However, because of us using the block dimension as for the batches, it's not as easy to just run more blocks, because in this case, we actually only have 16 batches, which means that we're underutilizing the GPU's multiprocessors. So one way to cope with that is to adapt our kernel and adapt our grid stride loop so that it's possible to launch more blocks as well. So in this case, I'm going to adapt my kernel so that the X dimension of the grid determines how many blocks we additionally want to launch to cover the occupancy. And then the Y dimension is still going to be the batch number. And the changes we then need to do in our kernel is that we now look up the batch number from the Y block index. And then our grid stride loop now also takes into account the grid dimension, or at least the X component of the grid dimension. And because of that, we've adapted our grid stride loop to cope with multiple blocks. And if we execute this, you'll see that the performance has significantly improved. And we can already see this in the screenshot from NVIDIA Inside Compute below, where the amount of uneligible warps has further lowered from 77 to 59, and performance has dramatically improved. So we went from, I think, was it 4 milliseconds to 800 microseconds. And the improvement is twofold. So one part of the improvement is from using a, actually, no, I'm wrong. The entire improvement here is from using additional blocks. We're still using, no, we already upped the number of threads from 256 to 512. So the improvement is twofold. So from the one hand, it comes from launching more threads, which means that every block, every multiprocessor itself will be able to hide latencies better. And then on the other hand, the second part of the improvement comes from launching more blocks, which makes that more of the streaming multiprocessors will be used in our GPU. So it's a twofold improvement, and we could split it up to see the individual improvements, but nonetheless, as you can see, the improvement is significant, going down from 4 milliseconds to 800 microseconds. And in order to make this code a little more resilient, because currently here we're hard coding the 512 and 48 blocks we got from the launch occupancy, what we typically do is that we query the information from the launch configuration at runtime. This code has been carefully optimized so that it's actually feasible to do so for every invocation of a kernel. And let's benchmark this. So it was 860 microseconds, and by actually doing all of the launch configuration checking at runtime, we shouldn't regress too much. Yeah, 864. So it takes a couple of microseconds to query all of that at runtime and give you a fully generic adaptable kernel. So this is getting close to the 600 microseconds. If we want to go beyond this, we'll need to have a look at the generated code. So yesterday, I already hinted at some of these device code macros. Yesterday, I only used at device code warrant type, but we have some more lower level utilities. For example, we have at device code LLVM. That makes it possible to have a look at the LLVM code that's generated for this kernel. And do note that I added debug info none here. If we wouldn't have done this, then the output would have been much more verbose. You can see all of the debug information corresponding to each of the inline frames. And maybe just to touch back to what I mentioned earlier, this is why the Inside Compute experience isn't great. And that's because Inside Compute always only reports the bottommost frame of the stack of code, whereas in Julia, because we have so many frames of inline code, that's not always useful. So for now, let's add back the debug info equals none. And we can see that the generated code is fairly, as we call, straight line code already. So much of the expensive computation just happens as a bunch of instructions in succession. What we want to do ultimately is reduce the amount of registers that this kernel uses. And that's because the amount of registers that the kernel uses, which you can also inspect from the compiled kernel object by using the CUDA.registers function. This is one of the inputs that the launch occupancy API uses to determine how many threads to launch, because this results in an upper bound of the amount of threads that we can use, because the amount of registers that's available to a kernel is limited. So if we use many, we won't be able to launch as much threads on a given streaming multiprocessor of a GPU. So as you can see here, this 512 is the same number that was reported by the occupancy API. But if we look at this code, one of the things we can see here is, for example, lots of bounce errors being thrown. And those are the kind of things that inflate register usage, because across these calls, state has to be kept alive and state has to be allocated to report an appropriate bounce error. So generally, to avoid those branches in the first place, but also to lower register pressure, it's a good thing to try and eliminate all of those unnecessary branches. And in the case of bounce errors, we can easily do so by adding @inbounds statements to our code. Of course, you should only do so when you're absolutely certain that this code is actually functioning properly, but in this case, because it's in a for loop that's upper bounded by the length of our iterator, that's okay. Nonetheless, if you put this stuff in an application, then it's generally recommended to run your test suite with bounce checking enabled. This is done by default, so it doesn't need any action on your side, but it also applies to GPU code, which is a good way to catch any out of bounds accesses that might have slipped into your code. So let's benchmark this. So we were at 864. And it has improved significantly. And let's have a look at why that might be the case. And you can see here that our register usage dropped from 98 to 90, which now makes it possible to launch 640 threads instead of 512. And again, as I mentioned, because of launching more threads, every processor in the GPU has more abilities to hide latency because it has more potentially eligible threads to switch to when it hits a stall during execution. Another source of register pressure is the fact that we in Julia use 64-bit integers for almost all scalar integers, whereas on the GPU, lots of stuff is 32 bits by default. For example, all of these hardware indices, thread index, block dimension, all of those are actually 32-bit integers. So it might make sense if you're micro-optimizing a kernel, again, don't do this by default, it might make sense to make sure that all your arithmetic is being performed as 32-bit integers as well. And I do this here by casting my 1 to a 32-bit integer. Sadly, we don't have any automatic detection of which precision to use like Rust has, so we have to do it manually, at least for now. So again, let's compile the kernel, and we saved on 2 registers again. And that's the way we typically continue. So we keep looking at some of the code. Let's look, is there some other exceptions in here? If you go at the bottom, if I'm not mistaken, there's another bounce error which we should be able to get rid of. Maybe I didn't evaluate this function. That's strange. This is the one I wanted to highlight. So there's another exception left, but this case it's not a bounce error. It's actually an inexact conversion within the implementation of division in Julia itself. And that's to guard against dividing by either 0 or dividing by a unsigned, unrepresentable number. And it's much trickier to get rid of those because in effect, we're just using the division function as we intended. It's even just, we don't use it ourselves. It's being used when we index some of our containers. However, we can do a trick here. But this again is micro optimization to the fullest. So what we can do is we can actually teach LLVM that the conditions to this exception are impossible. If we have a look at the LLVM code that leads up to this exception, so LLVM code is fairly readable. It takes a bit of effort to get used to it, but nonetheless, you can, if you're micro-optimizing a kernel, it's probably even better to have a look at the LLVM level, and it's more readable than looking at the PTX or let alone the shader assembly level. So in order to avoid this branch, we have a look at where it comes from. And as it turns out, this comes from the fact that some of the sizes of our array might be 0. So when we're indexing into our batch, the index is going to get divided by the size of our container, our batch, which may be 0. And in that case, the division operator would have to throw. But in this case, we know, because we initialize our batch on the CPU, we know that it cannot ever be 0. And using the LLVM assume function, we can inject this information that the Julia compiler or the Julia inference otherwise doesn't know of. We can inject this into the LLVM IR, and then LLVM can use that information to optimize away branches. And for example, here, by teaching LLVM that the sizes of our batch, which we're indexing, can never be 0, is going to be able to avoid the branch. If we now have a look at, let's just jump to the LLVM code. Oh. If we have a look at this code, then the throw exception is now gone. And the result of that is that the amount of registers has dropped significantly from 86, I think, to 82. So as you see, this is micro optimization, but it, especially for GPU kernels that are very costly in your application, it might be valuable to insert this additional information in your compilation. Instead of just looking at the LLVM code, you can also look at the PTX code if that would matter, and then you can see all of the PTX code being generated. You can also look at the shader assembly code if that would matter, and so on. So let's have another look at benchmarking our current implementation. After having introduced all of those assumptions. So we're still hovering around 720. So even though register pressure has dropped, if we actually further inspect the max threads, then we can see that it hasn't improved. Now, what we can do is inside compute, there is a tab that shows the occupancy limiters. So I have it still open here. If we go to the details, to the bottom, you can have a look at the occupancy limiters. And if you expand this, you get to see these nice charts that show you what the impact of the amount of registers would be on the occupancy. So in this case, this was still a profile of an older kernel, but with the most recent kernel, we can clearly see that currently we're at 82 registers, and improving it down to 65 wouldn't have any impact on the warp occupancy. And that's because if we read the explanation here, our scheduler is capable of having 8 active warps. However, we are only running 4 active warps all the time. So if we manage to push the register pressure low enough, we might get a boost of 2 times more warps being eligible. And this would be hugely valuable. However, seeing how we're already micro-optimizing the code, it's going to be tricky to go further down from 80 to 64 registers. One common solution here is to split the kernel in two. So counterintuitively, because I've been speaking of fusing kernels as much as possible, sometimes it may be valuable to split kernels, because then you may be able to push register pressure of those individual kernels down enough in a way that they will execute significantly faster than they would if they were fused. But in this case, we're going to perform another trick. It seems like cheating, but we can just tell the compiler to use at most 64 registers. However, it isn't cheating, because by doing so, we're going to spill those registers to local memory. And local memory is just global memory per thread, which means that those accesses are going to be synchronizing. And that's obviously bad for performance. However, in this case, because if we look at the original kernel, we already had some local memory. We already had 8 bytes of local memory being used. Maybe it's worth it. Maybe going from 8 to 24 bytes of local memory, however, being able to launch twice as many warps might be valuable. So let's try it out. We have our implementation here, where, as you can see now, I have added this max regs equals 64. And again, we got this 64 value from this chart inside compute, which told us that we can launch twice as many warps if we only use 64 registers. Let's benchmark this. And it was worth it, because execution time went down from 700 to 630 microseconds. So even though we're now spilling data into local memory, which is very bad because it's synchronizing, at the same time, we're launching twice as many threads, which results in a much better ability for the GPU to hide latencies. So this is a very nice example of the kind of micro optimization that can go on with these kernels. And if we now have a look at the amount of eligible warps, you can see it has dropped to 42, and there's 8 warps active per scheduler, which is great. And in Inside Compute, you can also have a look at the top of this chart. We get the GPU speed of light throughput, where we have some nice overviews of the total GPU hardware usage. And do note that each of those you can expand to get to see much more details and much more charts. For example, with the memory workload analysis, you can see charts of all of the memory going through all of the hierarchies. But now we were just looking at the high-level overview. And if we compare our original kernel, where the duration was 23 microseconds, and we were only using 1% of the compute throughput and 2% of the memory throughput. And our optimized kernel, which only takes 600 microseconds, we're getting 50% of compute usage and 50% of memory usage, which is starting to become great. So this is a nice example of how you can squeeze quite some significant performance out of a kernel if you use Inside Compute to have a proper look at why your kernel is slow. Of course, as I've mentioned a couple of times now, it's only useful if you know that a single kernel is the bottleneck, and most of the time it'll be much more valuable to look at the application as a whole in Inside Compute. This is where more of the performance gains can be found. One last bit that I haven't covered with this root mean square error kernel is memory coalescing. I'd like to discuss memory coalescing, which is a generic GPU optimization pattern, because it matters given how we often use multidimensional arrays in GPU code. So one question I'm often getting is whether CUDA.jl is row or column major. Well, Julia is column major, and CUDA.jl also follows those conventions, but the way you have to use that in a GPU kernel is different than on the CPU. So on the CPU, the general recommendation with column major memory is that the leftmost iterator, the leftmost index, should be the one changing the most rapidly, for example, in the inner loop of a loop nest. And that's because incrementing that leftmost index moves to the next location in memory. And as a result, you benefit from spatial locality. Now, on the GPU, we need to think about spatial locality as well. But one of the key concepts there is memory coalescing. And that's when consecutive threads, meaning thread 1, thread 2, 3, and so on, if those threads are accessing consecutive memory locations, then the memory manager will be able to fuse those memory requests together. It will be able to coalesce them together into a single memory request. And that results in a much faster kernel. And in order to illustrate that, I've implemented a single XP kernel here. So I generate some random inputs. And what my kernel does, it's pretty simple. The kernel function is going to look up a row index by the block ID, column index by the thread ID, and then use them to compute the familiar XP and write it back to Y, just like linear algebra.xp does. If we execute this, we get the expected results. And now let's benchmark this kernel. 30 microseconds. However, this kernel actually doesn't follow the advice I explained earlier, namely that the leftmost iterator should be the one that changes in a way that consecutive threads access consecutive memory location, because here the thread index is used as the second index, and the first index, the one which determines whether you're accessing consecutive memory locations, is changing in accordance to the block index. So let's switch that around. Here, I is being computed as the thread index, J is being computed as the block index. So the thread index is used as the first index, which means that, again, consecutive threads will be accessing consecutive memory locations. So we also switch the sizes around in our launch configuration. Let's verify that the result is still the expected result. And let's benchmark this. So we had 30 microseconds. Now we have 8 microseconds. So this is another very important kind of optimization that people are used to thinking about in the CPU world in order to access column major memory in an efficient manner. And you really have to do the same on the GPU, but instead of thinking in terms of loops and loop iterations and spatial locality across loop iterations, you have to think about spatial locality in terms of threads within a war. Still, this is a fairly specific implementation of the XP operation, and just to show how memory coalescing matters. A more typical way of how we'd implement this kernel is as such. So the difference here is that we're just using a one linear index, because as I mentioned before, Julia arrays can be accessed in a Cartesian member specifying all of the indices, or can also be accessed in a linear manner. And if we do so in a linear manner, then by definition, we'll be accessing consecutive memory locations as long as we're adding the thread index and not multiplying the thread index by a dimension. So in this kernel, I'm also using the launch configuration to make sure that I have an appropriate launch configuration. And interestingly, here I have also generalized my grid stride loop to be able to cope with a higher number of blocks. And I'm doing so, a lower number of blocks. And I'm doing so in order to be able to launch fewer blocks, launch more blocks when the launch API recommends us to do so. So as you can see here, the launch API recommended 1024 by 48 blocks, and this is exactly how we are launching this function. So let me benchmark this implementation as well. Our previous version was 8.3 microseconds, and I don't expect this to be much faster. Yeah, it's 8 microseconds. So a little bit of speed up by presumably using a better launch configuration. So maybe another nice thing to show here is that this is a kind of implementation as how we would put it in CUDA.jl, where, for example, the kernel function is nested in our outer function, so we don't have to pollute the global namespace with kernel definitions. One cute thing we can do is we can actually drop these arguments to the kernel, because it's possible for the kernel to it is possible for the kernel to capture values from the outer function. So why isn't this working? I'm not sure. I'll just leave it be, because it's not a performance optimization, so it's actually not really relevant for this course. Okay, so that's the end of it. A little early, but I propose that you can use all of these recommendations I've made here in terms of optimizing kernels, optimizing applications, how to use all of the tools we have at our disposal, it be inside systems or inside compute or benchmark tools. And for you to have some experience with that, it may be useful to work your way through any of these examples here. And I'll be around for at least an hour still to answer questions or help people with any issues that they have concerning usage of any of these tools or usage of CUDA.jl in a combination with these tools. Thanks for your attention, and see you around.
Thanks, Tim. I should probably turn my camera on too. I think if there is still some opportunity for questions, that would also be good, because I do have some questions.
Of course.
One question that I have is, so once you start optimizing, or generally if you're writing GPU code in Julia, to what extent can you stick to generic code and expect close to optimal performance, and to what extent do you have to optimize for your particular hardware architecture with very specialized code? I'm also asking this maybe with the idea in mind that can I write generic code that easily runs on AMD GPUs too, for instance?
Yeah, so if you generally wait, let me turn on my camera again. Generally, with the array abstractions, it's definitely possible to write generic code that executes across the CPU, the GPU, and different kinds of GPU platforms. It just requires us to implement as many as the array operations that you're using in an efficient manner, which basically is just a matter of having enough manpower to implement those. And with CUDA.jl, many of these operations are fairly well optimized already, or at least the common ones that people are used to using. With AMD GPU, that's another story. The maintenance there is there's no full-time developer working on AMD GPU.jl, so chances are that you run into array operations that aren't optimized, aren't properly implemented yet. If, however, you have an application that requires you to implement kernel functions because it's custom by nature, or for whatever reason you want to implement your own kernels, and then you can do so using kernel abstractions, then you're pretty much guaranteed to be able to write code that performs fairly well across all of these platforms. Of course, the kind of micro optimization that I did here, most of it actually does apply to all of the GPU architectures, and you can pretty well write portable code that works on multiple architecture, at least definitely across AMD GPUs and NVIDIA GPUs, because both are fairly similar in that regard. Maybe if you take Intel GPUs in the mix, we've noticed some performance issues with kernels that used to perform very well on AMD and NVIDIA hardware. So it's possible that with those kind of architectures, there might be too much of a divide to have one unified code base. But currently, as it looks to be, with those powerful AMD and NVIDIA GPUs, it's definitely possible to write portable code, and kernel abstractions is a great tool for that. Conceptually, implementation-wise, there's some issues with the package, but it's not unexpected. It's still possible to iron those out and make kernel abstractions a really solid base for portable GPU programming.
Right. And I was also wondering, you mentioned that a lot of the GPU compiler itself is written in Julia. So is everything written in Julia, or so to what extent is it Julia and to what extent is it LLVM that's doing the GPU compiler work?
Well, we do rely on an LLVM backend, of course. So, but Julia equally so relies quite a bit on LLVM to do the optimization. In the CUDA case, that lowering is actually fairly limited. So the PTX instruction set architecture is meant to be a virtual instruction set architecture, which is then compiled by the CUDA driver to something that's GPU specific. So even LLVM isn't doing much, or that much at least, in the whole CUDA compilation scheme. It's a very useful compiler, and we wouldn't be able to do without, but nonetheless, a lot of work is also being done by the CUDA driver itself. But we didn't ever aim to write all of the compilers in Julia, because just not reusing LLVM, there's not much value in doing so. So the fact that we have all of the higher levels of the stack working within Julia at least gives us the ability to iterate much more quickly on the GPU compiler. And that's well, the fact that we're then still using LLVM to optimize and generating native assembly is not much of a problem, because we get most of the value of having the upper levels of the stack being written in Julia, not the lower levels of the stack.
Okay, cool, thanks.
Well, just to say thanks a lot for this awesome presentation again today. I think this is really highly relevant material for high-performance computing. And so we, as Harman said, we just stay around for another hour or something to answer to questions in the Slack channel. Or maybe you can also speak up here if it's difficult to answer via Slack channel.
Yeah, sure. I'll stay connected, and Slack is open. So if there's any questions, feel free. Maybe I should also highlight some of the community effort here. So every 2 weeks we have a Julia GPU community session, typically on Monday. That's on the Julia community calendar you can find on the Julia homepage. So if you have any questions in trying out CUDA.jl or AMD GPU.jl or any other GPU related functionality, you're always happy to drop by in any of those community calls to ask questions. This course, as well as the Julia Lang Slack, has dedicated GPU channels where you can ask for questions. There's also a dedicated landing page nowadays. It's juliagpu.org. Let me quickly show that. And there's juliagpu.org, where we have a blog which every couple of months, where there's a major release of, for example, CUDA.jl, we explain all of the new features that were introduced in that version, or the breaking changes, and so on and so forth. So this is also, you can subscribe to this blog. There's a feed to do so. If you want to keep track on the ecosystem, this is a great way to remain up to date with new features and changes in the GPU ecosystem in Julia.
Then let me just do like a final conclusion I want to do, because people will then sign out, I guess, like in an open-end way. So I hope that you have enjoyed the course as much as I did. And Tim, this was a really amazing, all this material. It really was extremely well structured and then highly relevant for HPC. That I believe it was a great, like, complementary thing to what we saw in the first 2 days, which was very memory throughput focused and like really applied, a bit pragmatic, right? And here we got a really theoretical, well-structured overview of everything. Then I would like to thank to Harman, who has helped during the whole week answering questions. He helped behind the scenes with solving some last-minute issues to make this course happen smoothly. So thanks a lot for that, Harman. That was really highly appreciated. And then, well, Guillermo is not here, but of course, thanks to him as well for having taken care of the organizational part at most, and also Tim Robinson. He was attentive. He's our Jupyter expert. If something would have gone wrong, he was there. He was listening, being like, he was there, and he would have helped immediately. Now, and he did, of course, this whole great Jupyter setup together with other people. So thanks to this, we could have such a smooth course with Jupyter just working, right? Yeah, so with that, I would like to conclude. And so thank you all for participating and have a great weekend.